Hello everyone, thanks for joining subscribing my YouTube channel. Today we are going to learn about CCNP Core Enterprise Core. This is one of the core paper and there are two benefits. First of all, if you are looking for your CCNP certification, so this paper is must. You have to pass this paper and then you can go and choose any of the elective paper. I'm going to explain this in few minutes so you will understand the new certification track related to CCNP. That's the benefit number one. The benefit number two is now Cisco has removed CCI written. So if you are looking for CCI in enterprise, you have to pass this CCNP in Encore. So anyways, it is very important if you are looking for professional level certification, it's very important and this is a stage number one. If you are looking for CCI certification, this is again very important and this is a stage number one. So please continue, complete this video and gain the knowledge related to CCNP Encore. I'm going to walk you through the CCNP Enterprise certification, and we'll see that what are the changes that Cisco is putting from this coming Feb inside the certification. There is complete strategy change you can see inside the CCNP Enterprise. We know that Cisco certifications are always valuable. You will get much salary hike, means compared to other certifications in the market. You will get much more reputation and they are highly valuable certifications. We have complete sort of certification, means different type of certification like associate, professional and expert. And as per your certification, even you can negotiate with the companies in terms of salary and other aspects. So they, as per your certification, they will think that you have the right knowledge, skill. You are very skilled in the IT. You are a skilled IT professional, and then you can go and ask for the salary because you are able to take the responsibility. So that's the reason the company will pay you. Here you can see that 99% of organization use certification to make hiring decision because these certifications are structured in a way that they are going to test your different level of skills. So for example, if you see the old certification stack that we have, means now it's 28th of Feb. So now this become old, and now in the next slide I'll show you the new that will be available from 24th of Feb. So this old certification, you can see most of the people at the moment, at this point of time, they have we have associate level certification, professional level, then the expert level, and different type of technologies are there. So for example, routing, switching, security, service provider, wireless, others. Now this has been changed in this. So now you can see that certification has been simplified, but on other hand, that will become much more focused. So now this CCNA, that is the associate level certification, this is the basic for all the professionals, and then again you can go for the expert. But CCNA become basic for the professional level. Now this CCNA will serve the purpose for enterprise, service provider, data center, collaboration and security. And parallelly, you may have the expert level certifications in that particular domain. Now again, Cisco has other certification as well, and that is the DevOps. And their track is different, but you can see that 95% or maybe 90% of things relates with associate CCNA and then the professional and then the expert. Now here you can see that if you've done your CCI, so you know that inside CCI you initially, means before this program, you have the theory and the lab, and that is 8 hour very difficult type of exam. And there you must need a very high percentage, for example 75 to 80% of marks in all the sections to pass your CCI. Now, comparative to CCI, CCNP exam is also very highly uh, skilled type of things that they are going to ask you. It means they are going to check your depth knowledge inside that particular domain. Here you can see that you have the enterprise core, security core, service provider core, collaboration, data center core. So things has been grouped strategically inside different type of core. So you have one foundation, you have one core, and then you can choose the uh, expert level, or more precisely the specialist level. So you have the core. First of all, you can see that you have the CCNA, and then you have core in these, say for example, 5 domain. So you need core knowledge, and then you can go and get your CCNP, and then you can go and get your CCI. So from your core, now you can see that you don't have written and a lab exam. Although your core, after your core, you can go and write your lab exam. Okay, so choose between 2 lab exam inside this enterprise core. And what are 2 lab exam? If I go back, you can see that you have enterprise infrastructure, you have enterprise wireless, correct? So like that you have to choose. Now if you are in the security, choose your concentration. Means you do your core, choose your concentration, and then take the lab. Like that you have all the tracks. You can see that from the slide, it's very much uh, clear and what to do at what point of time. Again, here you can see that you have enterprise, security, service provider. For everything, you have core exam, and you can go and have your CCNP. Means CCNP has 2 paper. One is core, and one is the concentration, or one is the focused exam, and then you can go and write the lab exam. So for example, for enterprise, you have enterprise lab related to wireless and the CCI infrastructure, where you have different things like SD-WAN and SDA. Those new things are also added. All right, so now you can see that today means, again, today is 27th or 28th. So now we are in this certification track. So 24th of February, we have enterprise core that is mandatory, and then you can choose one. So either it's advanced routing or SD-WAN or enterprise wireless or wireless implement. Like that, you can choose the certifications. Summary, that Cisco has tried to reduce the number of amount of certificates, and it has been focused and grouped well logically inside single technology, or inside single group. And it's still um, and even they have removed the CCI written as well. So you can do your CCNP core and you can write your CCI. You can do your CCNP core, and then you can go and focus on any of the specialized exam, like say for example SD-WAN or enterprise design, etc. All right, so this is the track. Everyone has a home, everyone gains, everyone maintains their certification, everyone awarded badges. So obviously by the end of day, once you complete the track, you can see that you have different type of badges. You have a specialist, then you have CCNA, then you have CCNP, and then you have CCIE. So you can start your journey, and then you can slowly move your career from a specialist to the expert, and that's the goal. And once you complete your CCNA up to CCI in one particular domain, then you can move to the other domain. Okay, so there is a wealth of knowledge available, and if you want to gain it, if you want to become expert, go to one technology, complete it, and then move to other technology. That will be the strategy. This particular course is focused on CCNP Enterprise, and once we have one of the core topic, then we'll go and check the SD-WAN. Alternatively, we can go and check the other stuffs as well, like design, advanced routing, enterprise automation. But at this point of time, we can check CCNP Enterprise and the SD-WAN, because the combination of enterprise and SD-WAN will give you weightage. At the moment, SD-WAN is very hot in the market. It's very demanding, and if we combine like these two, core plus SD-WAN, so market value will be very good. What are the core skills you need? We'll see that we have complete syllabus. You can go and check. So now this was the past where you have route shoot arc and other stuffs. Now in future, now present, I will tell this is the present. So you have enterprise core batch, you have a specialist, uh, then you have the advanced routing batch, wireless batch. Means for individual exam also you will get that exam certificate, but better that will go and club. So CCNP enterprise with any of the four, correct? All right. So now here again, you can see the summary that you have. Like if you want CCNP enterprise, you do the core and you can do the advanced, or you can do the core, you can do wireless, any of these two. You can do the core and then you can do the design. And here you can see that CCNP enterprise, enterprise, enterprise. Okay, and just try to tell that how it is equivalent to CCNP RNS, CCNP wireless, CCNP DP. So suppose if you want to do CCNP DP, you do the core and then design, and you are the DP. If you want to do CCNP in wireless, the do all these three and then you are CCNP in wireless. If you want to do CCNP RNS, do these two and you are CCNP RNS. If you want to be CCNP in SD-WAN, you do core and SD-WAN and you are the CCNP in SD-WAN. All right, so this was the certification changes, and I hope that you understand that what type of changes, what certifications we have to obtain our new CCNP, and from there we can go and prepare for CCIE as well. In section 3.0, we have infrastructure. That weightage you can see that is 30%, and the topics that we have is belonging to layer 2. So here you can see the layer 2 important topics. Say for example, trunk, VLAN, Ether channel, and RSTP and MST. In layer 3, we have to learn important protocol about EIGRP, OSPF, and BGP. Then wireless, and finally we have IP services. So let's start with section 3 and with layer 2, that is 3.1. So agenda here is that to learn about the VLAN, trunk, and various troubleshooting options that we have. So let's start 3.1, that is the 3.1a belonging to layer 2 troubleshooting, trunks, etc. Let's start 3.1a, where we have to learn about layer 2 technology and few of the troubleshooting steps. So before starting 3.1a, I just wanted to quickly revise about VLAN and trunking protocols. So here you can see in the diagram that when you have two switches, and when you are connecting two switches, obviously you want to allow different VLAN inside that. So that's why the distribution layer switch and the access layer switch, we have 802.1q trunk. Now what is trunk, which type of trunks we have, that I'm going to discuss. So let's first understand that what is VLAN and why we need VLAN. Say, what is the default nature of a switch? We know that by default, whenever a switch there and whenever it receives a frame, so for example, you haven't enabled any type of VLAN, or you're not working, created any VLAN to the switch. So whenever the frame will come and hit to the switch, it will broadcast that particular frame to all the available interfaces, correct? And in this way, number of collision domain or number of collision will increase. Rather than what you can do, that whatever switch you have, you can divide that switch into a smaller group, and that smaller group is nothing but the virtual LAN. So this LAN segment you are dividing into a smaller group, that is, if for example VLAN 10, VLAN 20, VLAN 30. Now in that case, when a request will come, it will only broadcasted to that particular group, because different VLAN they have the logical boundary. So VLAN is nothing but a logical boundary to reduce the broadcast domain. Plus, when we are creating the VLAN, uh, by default, we are providing some more security as well. So VLAN 10 and VLAN 20, they will not communicate until unless we have a router in between, that we can use router on a stick concept, or maybe the switch they are supporting SVI. So they need some sort of gateway to communicate across the VLAN. So here you can see in the diagram that you have VLAN 100 and VLAN 200. They are purely in different IP subnet. So two different IP subnets or two different broadcast domains, they will communicate only if they know how to reach to the gateway, or they have to cross the gateway or the boundary. Now how to create the VLAN? It's very easy. You can go to the global config mode. You can give a VLAN and the number, and then you can give the name. So VLAN number and name, you can define like that. Now here you can see that we are supporting although up to 4K number of VLANs, means you can create up to 4094 VLAN starting from one. VLAN 1 will be default, but this number 1006 to 4094 will be supported in transport mode, means they will be supported inside extended VLAN range. You can go and create up to 1 to 1005, where 1002, 3, 4, and 5 they are reserved for token ring and FTDI purposes. Okay, so we can go and create the VLANs. It's very easy to create. Let me quickly log into the switch and let me show you that how you can create the. So here I am inside the switch, and what I can do, I can go and create, say for example, VLAN 100, and then I can go and give the name as, so for example, servers. Then we can check the VLAN. So here you can see that you have VLAN 1 by default, and all the interfaces by default they are part of that VLAN. Then you have the reserve VLAN 1002 to 1005. But again, you can go and create the VLAN. So for example, I have created the VLAN 100, and I should exit, and then we can go and check that VLAN. So here you can see that now you have the VLAN 100 created here. I will not add any interface, but if you want, we can add the interface as well. So for example, any of the interface, show interface brief. Let's see that what available interfaces we have to this particular switch. These are the interfaces that I can see here, and if I can check the interfaces and the summary, so now you can see that you have these interfaces, because this is the virtual switch. So you are seeing less number of interfaces, but I can go to any of the interfaces, for example, 1/1, and then I can go to switch port mode access. We'll discuss about this mode access and trunk, and then I can go and assign switch port access VLAN 100, and then I can go and check about this particular interface, that is show interface E11, and we have this option of VLAN. Even we have option for the trunk as well. So this mapping will not work, but if we go and check show interface E11 and then trunk, so here you can see that the encapsulation is negotiated. This is non-trunking. What is trunking, what is non-trunking, we'll see. The number of VLAN allowed over this interface is VLAN 100 that we have created. So like that, we can go and check it. So here you have the command and you can check show VLAN that just now we have checked. Now if you want to assign that particular VLAN to the interface, you can go and use switchport access VLAN 100. Again, you can go and check show VLAN. So 100 is assigned to this particular interface. Now, what type of ports we have that we can assign to VLAN? We have access and we have trunk. So what does it mean? It simply means that suppose if we have switch and that switch is connected with the terminating device, means where you are terminating the network. So that particular interface you can put inside access VLAN. Say maybe access VLAN 100 or 200 or 300, etc., etc. And that's the reason in corporate network we are creating certain type of VLANs. So for example, VLAN name data, VLAN name wires, VLAN name sales, HR, etc., etc. So terminating devices generally we are assigning to the access port, but where you want to connect the other networking devices and you want to extend that access VLAN throughout the network, or you want to propagate that VLAN throughout the network. So whenever you're connecting a networking device to other networking device which is non-terminating, that you want to extend the network, so at that point you want to create the trunk. So trunk simply means that can allow multiple access VLAN, or that can allow multiple VLAN. Access means they are part of only one VLAN. Later on we'll see that we have different type of trunking protocols. So here you can see that rather using three different cables over one interface, once you enable the trunk, you can allow different VLANs over that. So for example, VLAN 100, 101, 102. We have trunking protocols. We have ISL, that is Cisco proprietary, inter-switch link, and then we have industry standard, that is 802.1q. Now in this diagram, it is quite clear that if you have terminating devices, so these terminating devices, they are part of same VLAN or a VLAN. Here you can see VLAN 100, here you can see VLAN 200, here you have VLAN 200, like that. And suppose if you want to extend or you want to pass multiple VLANs over the trunk link, then you can go and allow those VLANs over connecting networking devices. Correct? So either we can use ISL or we can use 802.1q. Here we have dynamic trunking protocol as well, which is something you can think that this is uh, dynamically negotiating the trunk or dynamically negotiating two switch properties, although we have option to do this configuration manually as well. So how we are going to do this manual configuration, how we are going to do it dynamically, I'll show you in upcoming slides. Now the characteristic of 802.1q, that is now the standard, and even Cisco also uses 802.1q, is because this is lightweight rather than this ISL that is encapsulating entire frame. 802.1q, the feature or the improvement it has is that they are embedding. So here you can see that they are embedding 4-byte VLAN tag. So they are adding some tag to the frame, and once they add add the tag, then the default size of the frame will increase up to 1518 because they are adding 4 byte of frame, and then it is supporting maximum 4096 VLAN. Now how it look likes? It look like this. So you have the frame. When you add 802.1q VLAN tag, inside VLAN tag itself, you have VLAN ID 12-bit, and that's the reason it is supporting 4096 VLAN, because 2 to the power 12, if you check this number, then you will find it will be 4K, correct? So 2 into 2, if you do 12 times, we know that uh, uh, you can do the math. So you'll find that it is 4K. Apart from that, we have priority bit, we have the protocol tag, we have some bit as well, that is the canonical format bit. Okay, so we have just a overhead of 4 byte, and it is propagating the number of VLANs through this tag. So let me quickly log into the switch, and I'll create a VLAN 200, and then in between two switches, I have switch 1 and switch 2, I will enable the trunk. So let's do that. Mode trunk. And now it is telling that, see, this command is rejected because the trunk encapsulation is auto. If you want to do it manually, you have to do switch port trunk encapsulation. And here you can see that we have .1q ISL negotiate. So I'll do .1q and then switch port mode trunk. Okay, and what type of VLAN you want to allow? Switch port trunk allowed VLAN, say 100 and 200. Although I haven't created the VLAN 100 and 200, I want to create 100 and 200, and I don't want to add this VLAN 10. So I can do remove 10. Okay, now we can go to the interface, say E0/0 and even 0/1 as well. So what command we are using? We are using switch port. First of all, switch port trunk encapsulation.1q. This is that manually I am telling that encapsulation is .1q. Switch port mode is trunk, and we are allowing VLAN 100 and 200. Now same thing I can do to this side as well. I can go to interface range E0/0 to 1, and then now we can go and check show interface E0/1 trunk. This is one very good command. So allowed, here you can see that over E01 the allowed VLAN is this and this. The VLAN allowed over certain interface is this. We can go and check show and interface E0/0. So this is the command that we are working at the moment. I haven't created VLAN 200 to other switch, so I should create that also, but just for demo purpose. This is solving the purpose. So this is the way that we can go and create the VLANs, and then we can create a manual trunking, or we can do manual trunking as well. Next, we have to understand about the trunk and dynamic trunking protocol, DTP. We know that we can create the trunk, or to pass multiple VLANs across two different switch or inter-switch link, we can create the trunk. We have option that we can do it manually, and then we have option that we can do, or we can use dynamic protocol as well. So for example, if you have an interface 2/24, and if you run this command switch port mode trunk, first of all, it will throw an error. It will tell you that first you do the trunk encapsulation protocol, or run the trunk encapsulation protocol, either ISL or .1q. So if you do that, and suppose if you have two switches connected back to back, say I have one switch here, another switch here. Here if I do ISL inter-switch link, and here I do .1q, then obviously they will not form the trunk. So both sides we should give the same protocol, same encapsulation in other words, and then only they will form the trunk. So for example, if I give same encapsulation, so for example 8.1q or 802.1q or .1q, etc., then they will form the trunk. Now here we have the option. Either we want to do it manually, or we want to use the DTP, dynamic trunking protocol. So for that case, what you can do that you can go to one side and you can do encapsulation negotiate. The full command is switchboard trunk encapsulating or encapsulation negotiate, but they will prefer ISL. They will not prefer 802.1q due to these other Cisco switch. So they are going to prefer ISL. Better we can do it manually as long as possible. Now, once you have multiple VLAN and you want to allow it, you have option switchboard trunk allow VLAN, and then you can give number of VLAN or range of VLAN. If you want to remove, you can remove that also, that we have done in the previous section where we have removed one VLAN, we have allowed certain VLANs. Now with this TTP dynamic trunking protocol, that is again the dynamic way to create the trunk. Again we have options. So this DTP has two modes to dynamically decide whether the port become a trunk or not. We have dynamic desirable and then we have dynamic auto. So here you can see if I go to certain interface and if I type switch port mode dynamic and question mark, I will show you in the switch as well. So then I have option dynamic desirable dynamic auto. Now we have one long list that if two different switch, what mode they are running in and how they are going to initiate the trunk. So for example, you can do manual, you can do with help of DTP automatically. So manually, if you are making trunk, obviously they will form the trunk. One side trunk, other side is dynamic desirable. Dynamic desirable means you are sending the packets to form the trunk, means you are sending the negotiating packet. But dynamic auto will not send. So we'll see that. One side trunk, other side is dynamic auto. They will form the trunk. If one side you have dynamic, say desirable, other side dynamic desirable, they will form the trunk. So all these cases, they are forming the trunk. And suppose if you have dynamic desirable and dynamic auto, they will form the trunk. But if you have dynamic auto, they will not form the trunk because both these sites, they will expect that they are ready to listen the frames, but they are not actively sending the frames. So that's why they will not form the trunk. Now suppose if you want to disable DTP, you have option switch port no negotiate. Correct. So in that case, we are not using this DTP to form the trunk. And again, you have the summary slide, whatever we have discussed here. Now, what are the troubleshooting option we have? Suppose if you're forming trunk and this trunk is not coming up. So you should check these things like what's the trunk mode, ISL versus 802.1q with respect to frame tagging protocol. So this is trunk mode will be you should check what is the mode of the interface, say access or trunk, etc. Then the tagging protocol is ISL versus 802.1q. Then do you have a native VLAN mismatch? Suppose one side you are allowing 100 and 200, other side you are allowing only 200. Do you have any VTP domain configured? We'll see that VTP in the upcoming section. And that is only true when you are using DTP to negotiate the trunk. So these things one by one you should go and check. Then we have one very important command here. Here you can see in the bottom that show interface name and switch port. This is actually very important command included with show interface trunk. So these two commands are there for verification, and both side you can go and run, means both side means both the switch. You can go and run this command and you can check that which VLANs are allowed, which protocol is running, what is the mode of trunk, etc. So let me quickly go and log into the switch and we can do some of the verification commands. So I am inside the switch, and if we go and check show interface description, we are just checking that switch 1 and switch 2 which interfaces they are using. So E00 and E01, these are the interfaces. that is connecting to switch 1 and switch 2. And if you go and check show interface trunk, one very important command. So here you can see that E0, 0 and 01, they're allowing these two VLANs, although the management domain, it is showing only 100. Why? Because if you go and check show VLAN, you have only one VLAN. So what I'll do, I'll go and create VLAN 200 as well, and name I will give, say for example, clients. Now if you go and check show VLAN, we have server and we have client. Although we haven't assigned that to any of the interfaces, now we can go and check interface trunk, and now here you can see these VLANs are coming. Okay, all right. Now the status, you can straight away see that 00 and 01, they have status of trunking. Native VLAN is VLAN 1. The mode is on. Okay, now show run interface E0/0. This is the configuration we are using. If I go to other side, so interface and then trunk 100 200, because we haven't created any of the VLAN, so it is not showing anything. Mode is on, encapsulation is at 02.1q. That's okay. Then I can go here also, I can create VLAN 100, name servers, and then VLAN 200, name clients, and then we can go and check show interface trunk, so you'll get the same result. Now next very important thing that we can check, show interface E0/0 and then the switch port. This is actually a nice output that will give you detail about VLAN and trunk. So administrative mode is trunk, operational mode is trunk, encapsulating 802.1q, negotiating of the trunk is on, access mode VLAN, that's the native VLAN, is 1, that's okay. Tagging is enable, voice VLAN is none. We are not using private VLAN at this point of time. Trunking is enable, we are passing 100 200. Pruning is there, means there are some default options as well. All right, so what we can do now, at this point of time, we can check all the DTP option. So if I go to interface E0/0, and once I am inside switch port, you can see that what options you have. So you have a no negotiate if you don't want to, or if you want to turn off DTP, you can use no negotiate. Then if you want to check mode, and then you have this dynamic, you can see auto and desirable, and we have seen that list. So DDDD one side and DDD other side, that will form the trunk. If you have auto both the side, dynamic auto, they will not form the trunk, and vice versa. Okay, so this is the way that we can create the trunks, and we can verify as well. All right, so let's stop here. Next we have VTP, VLAN trunking protocol. And what is the use of VTP? We'll see that. This is something that we want to replicate or propagate the VLAN dynamically or automatically. And this will be useful for the large infrastructure where you don't want to create the VLAN switch by switch or hop by hop. So in this case, we can use VTP as a feature, so that can replicate the VLAN, or in terms of the VLAN database, from one switch to the nth switch. Correct. So how we are going to do this? There are what are the terminologies used and all. We are going to discuss and learn all those things in this particular section. So you have this VTP, and VTP, they have their own features. So what features they have, we'll see that. First of all, they have versions, say version 1 and version 2. Version 2 is quite a bit popular, although we have version 3 as well, which has again some added advantage. So let's focus on version 2, and we'll see what features we have in version 3 as well. VTP version 2 that can do VLAN consistency check. They are domain independent, transparent pass through. Means they are you have some added advantage in version 2. And in version 2, we'll see that how we can configure it. In version 2, what are the key component we have that we'll see in the upcoming slide. Now, what important thing we have in version 3 is that not only version 3 can replicate the VLAN database, but they are able to replicate the other databases as well, such as MST, multiple spanning tree protocol. Apart from that, version 3 can have support up to 4000 VLAN. They are supporting private VLAN. They have improved authentication. Whatever issues you have in version 2, and we have one uh, issue in version 2, that suppose that you have switches and you brought new switch inside the VTP domain, uh, by mistake, if the domain name is same, and suppose if the revision number for that new switch is higher, so whatever database that new switch has, they will go and write those databases or those VLAN to all the switches, and you can understand how big that issue is, how big outage it will be. So there is no database protection mechanism that we have in version 2 that is there in version 3. So here you can see that protection from accidental database overrides by using VTP primary and secondary server, ability to enable VTP on per port basis. Okay, what modes we have for VTP? We have 3 mode, actually we have 4 mode. Let me show you here in the diagram. So here you can see that you have server, you have client, you have transparent, you have off. Server means you can create the database, and from there with the revision number it will go and write to all the clients. Client who is listening those and updating their database. Transparent who is simply passing that information. So here in the diagram you can see that you have server who is sending the information, because this switch is in transparent mode, so he is passing that to the other client who is learning that new information. Likewise, here you can see that server is sending to the other client. If the VTP is off, so they will ignore the VTP update. So in a switch where you don't want that VTP update, you can turn that off, so that particular switch will not get the VTP updates. Correct? So the same thing you have explained in this diagram, and then you have the notes that you can refer. We have version 1 and we have version 2. In version 2, we have added advantages and feature. One of the very interesting thing and important thing we have with respect to troubleshooting as well is the revision number. Now in the lab section, we will see this revision number, the format of this revision number as well. Not only the format, but uh, when you go and check show VTP status or show VTP, you will find that you have the revision number. So at the moment you will add the VLAN, the revision number will upgrade, and then since he has the higher revision number, he will send the advertisement to the other peer switches or downstream switch to update that database that you have added inside the server VLAN. Correct? So that's the reason the revision number is important, because it is one of the component of the VTP advertisement. So here you can see that if you want to change this revision number, because accidentally you don't want to connect any switch by default in a network who has higher revision number, if because by default the switch mode is server, so if revision number is higher, it will start sending the VTP advertisement, and other switch they will think, oh, his revision number is higher, so I should overwrite my database as well. So you don't want to do this. So in that case, the safe thing is that you change the mode to transparent and then change it back to the server or client. So if you made that to transparent, what will happen that they will change the revision number to 0, and this is particularly for the new switch. The other option is that change the VTP domain name and then change it back to the original name. So you can change the domain name and change it back. The best option we have is the option 2, that change the mode to the transparent. Okay. Now we have already discussed about VTP version 3. They have this protection mechanism because they have VTP primary and secondary server. What type of messages we have inside VTP? We have summary advertisement, we have subnet advertisement, we have advertisement request. Summary advertisement, here you can see that it is sending the VTP version, domain, configuration revision, timestamp, and MD5. Correct? So suppose if two switch, their domain name is not the same, means if they are not in the same domain, obviously they will not read those databases, or they will not override those databases. And same is true with the MD5 digest as well. They should have common password so they can replicate the database or understand the database and override it later on. So a switch is sending the summary advertisement and the subnet advertisement. In both the summary advertisement and the subnet advertisement, you will find that you have configuration revision number. So here you can see inside the subset, not subnet, it is a subset advertisement. Inside the subset advertisement, again you have the revision number, and revision number simply means that if you are getting some information from higher revision number, you have to overwrite it. Now suppose um, here you can see that there is one use case of advertisement request. What it is that if switch receive a summary advertisement with a revision number higher than its own. So suppose I am getting a update with revision number 3, but mine is, say for example, 2. So I am lower in the revision number, then I will send the advertisement request that, hey server, my revision number is lower, you write all the VLAN information and update my revision number. So all the devices in a network should have the common revision number. Okay. All right, so how we can do the configuration? It's very easy. You have to do at least two things. Domain, so you have to go and define the VTP domain, and then VTP mode. You define the VTP domain, VTP mode, even we have to define the VTP version as well. So you do a VTP domain, you do VTP mode, you do VTP version, and if you want to do the protection, you can use the VTP password as well. So it's very easy to configure if you follow these configuration steps. So it's easy to do the configuration. How we can verify it? You can go and check show VTP status. So here you can see that its VTP version is 2, configuration revision is 42, maximum VLAN supported 1005, number of existing VLAN is 7, the operational mode is server, the domain name is my domain, the pruning mode is disabled at this moment. We'll see that what does it mean by pruning, and this MD5 digest is also there. Again, we can go and check the VTP counters as well. So now here you can see that we have the VTP pruning. What does it mean by VTP pruning? Pruning means simply that you cut off unnecessary information. That's the prune. Now VTP pruning means that you don't want to propagate unnecessary information to the switches. So here you can see in the diagram. So suppose if switch B will advertise the VLAN information, he will send switch C VLAN 100 200, that switch C anyways is not going to understand, and switch A he will advertise VLAN 300, again he will not understand because he don't have that. So in that case, what you can do, that simply you can cut off these information to advertise in first place. So here you can see that you can go to the switch globally, you can enable VTP pruning, and then once you enable that, then you can go to the switch interface where this interswitch link is connected, and you can do switch port trunk pruning, and you can prune those VLANs. Apart from that, you have other options as well, like VLAN add, remove, etc. All these options we have with the normal trunk as well. So we can prune those unnecessary VLAN to propagate from one place to other place. Correct. Now, if you want to do the optimizing convergence, already we have study about the DTP in the previous section. All right, so this is the VTP pruning, and this is the VTP. If I want to summarize this, how I can understand VTP. So we can think like this, that VTP, if you want to configure, you have to configure actually minimum two things, but four things are required, like VTP domain, VTP version, VTP mode, and password. VTP has version 1, 2, 3. 2 and 3 is most popular to use. Their modes are client server and transparent. Transparent means that simply bypass the advertisement. Server who is creating, client who is receiving. And the common factor in all these modes and things are the revision number. So if the revision number is higher, he has the authority to update the database to the other devices. Correct. And then we have seen that we have the advertisement like summary and subset. And if your revision number is less, you will send the advertisement request to update that revision number. How we are going to configure it, we'll see in the next section. Let us perform the lab task. So we have this arrangement where we have switch 1, switch 2, and switch 3. Let me quickly draw the diagram. So I have switch 1, and then it is connected with switch 2, and then it is connected with switch 3. 1, 2, and 3. Even switch 3 and switch 1 is also connected back to back, but we will make this interface as off, or will disable these interfaces. All right, so switch 1, 2, and 3, what interfaces they have? Say 0, 0 and 0, 1 in between that. And here you have 0, 2 and 0, 3. So it is connected like that. And here it is, say, 0, 0 and 0, 1. And here it is, say, 0, 2 and 0, 3. I'll shut down these interfaces, so I don't want any cross communication in between the switches. So this is the topology, and we want to run this VTP. So what I will do, that switch 1 I will make, or switch 101 I'll make as a VTP server. So let's do this. I'll go and create VLAN 10 to 20, and here you can see show VLAN. So now we have the list of VLAN. A few of the VLANs we have created earlier as well. Then I'll go to the interface range E 0/2 and 3. So E 0/3. Even I can go and give the hyphen as well. These interfaces I will do the shutdown because I don't want switch 1 and switch 3 do the communication. Alright, we can go and check show CDP neighbor, and we can check what switches we have in communication. So here you can see that I can directly communicate with switch 102 or switch 2, and that's the agenda we have. Alright, so let's go and create the VTP, say domain. I'll make this as a my domain, then VTP version. Here you can see that we have the syslog message telling that the domain name has changed from null to my domain. Version is 2, and then VTP, what options we have. Here you can see that we can give the mode, we can give the password, we have the pruning option. We'll see that. So now I can go and give the mode as a client server transparent and off. So this is the server. By default it will be the server. I'll go to the other switch. Here if you check number of VLANs, so it is replicating. Why? Because if I go and check show VTP status, so here you can see that this version is version 2. It is running version 2, although it is able to understand 1, 2, 3. The domain is my domain, and by default you can see that this is also server. What is the configuration revision number it has? That number is 4. Number of VLANs is this. Let's check this in the first switch as well. So means that by default the VTP is on the switches. So I'll go back to switch number 1, and inside switch number 1 we can check the VTP status. Let me run the command show VTP status, and here you can see that you have version, you have mode, and you can see number of VLAN supported. So everything is perfect and correct. There's no problem here. Now if I go here and create one more VLAN, say for example VLAN say 55, and now if you go and check the status, you can see that number of VLAN become 19, the revision is 5, and the same thing should be replicated to the other switches as well. So the revision from 4 it become 5, and now if I go here and check the VTP status, now here you can see 19 and 5, although the mode is server, that I will change it to client, and we'll check the transparent as well. Here if I go and check show VTP status on switch number 3, so let's check that. Now this is also server, and number of VLANs is 5, configuration revision is 0, and he is not able to get the information from switch 1 to switch number 3, because switch 2 and switch 3 even they are not forming the trunk. So what I will do, I'll go quickly here, and we have one interface here, interface E0/2. I can go and manually assign the trunk, or we can do this dynamically as well. That's the DTP. So I'll do this thing, switch port and then trunk. You can see that you have uh, encapsulation, and you have native pruning allowed as well. What I want, that I want to do switch port mode, and that's dynamic. We have desirable option. The switch port mode dynamic desirable, and then switch port mode trunk. Now the flip side of this is this, that if both side you are enabling this, they will go and execute ISL instead of .1q. So the recommendation is that we should do the .1q, correct? So that's the reason. Let me quickly go and do this switch port trunk encapsulation .1q, that because that's the standard, correct? So what we have done over show run interface E0/2 is these commands, switch port trunk, and then I don't need switch port mode dynamic desirable, because I can go and make switch port mode trunk. But anyways, let's go here and run these commands here as well. Interface E0/2. So interface E0/2, then we can check show VTP status. Now you can see that they have formed the trunk, and now multiple VLANs are passing. Next thing, what I want to do here is that the VTP mode I want to change as a client. Okay, and then we'll go and check the show VTP status. Then here I will go and create some more VLANs, say VLAN 6270, and then we'll check the status, show VTP. What options you have, you can see that counters device interface status. and the password. So now total is 30, revision number is 6. We can go ahead and check. Total is 30, revision is 6. Now I can go here and check 30 and 6. So uh, still we can see that the client is sending some information to the server as well, and he is updating his database. Now what I don't want to do this thing. Rather what I want here is that the VTP mode is client first of all, okay, and then I will go and create some more VLAN just to verify, say VLAN 8290, and we can go and verify the VTP status on switch number 3. So now this is 41 and 7. Now in between the switch I will go and make this as a VTP mode transparent, and then we'll check the revision. Now you can see the revision number become 0, although they have this 41 VLAN that they have already learned. So now if I go here and create some more VLAN, say for example 100 to 110, and if we go and check the status, now this is 8 and 51. Here you will see this will become 0 and 41, but it should become 8. Now here you can see that the status is the same. So as per the transparent mode, it should pass the information. Although you can see that revision number is still 7 and the number of VLANs are 41. That should be 51. So clearly we are seeing that they are not updating the revision number in between if we have the transparent. And this is the issue with the virtual devices, but ideally as per the theory they should update the database. So I'll do one thing, I'll go back to switch number 2 and I'll make this VTP mode as a client one more time, and now we should see here. Now they are replicating in the client mode. So server in client mode is working perfectly. Transparent mode, although they are changing the revision number, but they are not propagating the number of VLANs, correct? Now if I go to VTP mode and then I can make this off and we can check the status now. So now revision number becomes 0, and whatever number of VLANs I have, they are learning that. Obviously if revision number is 0, that means that they will not learn those data in case if it is off. So now if I go here and create some more VLAN, say VLAN 150 to 160, so we can go and check the revision number 9262, and here also we can go and check the revision number 9262. Here this is off. Okay, the last piece that we have to learn and understand here is the pruning method. So if I go here and first of all I should enable VTP pruning globally. Once you enable that, so cannot modify pruning unless the VTP is in server mode. So that's a restriction. First of all, the pruning should be inside the server because the server has the authority to create the VLANs and then it is replicating the database. So VTP pruning is on. Now what we can do is that we can go to switch port, and let me go to the interface. The interface is 0/0 switch port trunk, and then you have pruning, and then you can use VLAN, and you have add, accept, remove, none, etc. Okay, now we can go to the switch port interface E0/0, and we can check the switch port related to E0/0. Here you can see that the mode, the encapsulation, the trunking, and you can see the pruning VLAN is enabled. We have made this as a none, so that's why it is showing like that. Okay, so this is the way that we can create the VTP, and we can do the verification as well. 3.1, we have Ether channel configuration. We know that Ether channel is something that we can bundle the interfaces to overall increase the throughput. So here you can see in the diagram that you have core, distribution, and access layer. Generally, where we want to do this bundling or aggregation of the port or interfaces, they are at the level of core and the distribution layer. Generally, that doesn't mean that we can't do at the access layer. We can do as per requirement. So what we are achieving with Ether channel or the port bundling, that we want to give much more throughput whatever we have at this point of time when you are connecting the interfaces back to back. That simply means very simple term, that suppose I have switch A and switch B. So let me try to draw here. Say for example, one switch here and one switch here. If I have 1 gig interface, then obviously the overall throughput is 1 gig. But you can take, say for example, 4 interfaces, and you can bundle and they can work as a 4 gig interface. So overall throughput obviously will increase, will become 4 gig. Now the important thing here is to understand is that this 4 gig interface is per application. Means suppose if you have only one application and you think that one application is getting 4 gig of interface, that's not true. And the algorithm or mechanism behind the scene is that suppose if you have two interfaces, they will do the load balancing. So 1 gig and 1 gig will get load balancing or get load balanced per application flow. That's the key thing we have here. Whenever we are doing the port bundling, that doesn't mean that this become one 4 gig pipe and all the applications are getting 4 gig of speed. It's not the same thing. All right, so we have different type of methodology behind this, and we'll see that we have LACP, Link Aggregation Control Protocol, and we have Cisco proprietary, that is the PAGP, Port Aggregation Protocol. But moral of the story is same, that you are aggregating the port for higher throughput. Now we have to go and check that how we can create this Ether channel or bundle. We have option, we can do it manually, we can do it dynamically as well. Manually, when we are talking, so for example, I have two interfaces, I can go and I can use this command interface range and then channel group 1 mode on, or maybe you can use some other number like 10, 20, 30, 40, etc. So when you are using mode and on, and we have multiple option. So for example, in LACP we have option related to active, passive, and on. So for example, if you are using on, this is a manual thing. Manually you are turning on this LACP protocol or channel protocol. Okay, now once we are running this command, what is happening behind the scene, automatically port channel interface 1 will get created. Now this port channel 1 interface that you are creating, here you have to go and write your logical configuration, or you have to do the coding. So for example, if I have two interface 23 and 24 and I want to run commands related to switch port mode trunk and allow certain VLAN, then I do not have to run the command over the member interfaces. Rather, I have to do it inside the logical interface. So we should understand some of the technical term here, that I have a switch and I have two member interfaces. So for example, 23 and 24. When you bundle these interfaces and you are using manual method turning, so for example, LACP on, so at that point of time, so for example, the group you are using is 1. So you are going to create interface port channel. Here you can see this port channel 1, and whatever configuration you want to put over these interfaces, you should put here over the port channel. The switch port mode trunk and allowed VLAN we should put there. Suppose if you want to create a layer 3 port channel, then you can go to the port channel, you can do no switch port, and then you can assign the IP address as well. Okay, so this is the manual way to do the configuration, although we have the automatic way as well, and we have the protocol as well to do this. We'll see that in the upcoming slide. One important note here, that whenever we are creating the port channel among 2 or 3 or 4 switches, obviously these are point-to-point configuration. So in between two switch, whenever you are creating the port channel, so at that time your speed, duplex, and other hardware related properties should be the same. So what I am telling here, that you are creating port channel here, no problem, you can create it. Like that you can create other port channel here. So for example, number 10 and 20, etc. So these interfaces, so for example, speed, duplex should be same, correct? Otherwise, they will not form the port channel, and constantly they will throw an error as well. All right, so next we have the dynamic way to do the configuration. We have a link aggregation protocol, we have port aggregation protocol. Uh, Now everyone is using LACP, and even in the syllabus also, um, it is recommended that we should learn, understand LACP. Although if we learn one methodology, the second will come automatically. So I'm going to focus on LACP, link aggregation protocol. This is the dynamic way to create the bundles. We have mode for LACP is active and passive. If both side of switch is active, they will form the port channel. Both side is, say one side is active, other side is passive, again they will form the port channel. If both side is passive, then they will not form the port channel, because no one is sending the LACP control packets. So obviously both are the listener for LACP, and they will not auto negotiate the ether channel or the bundle. So here you can see that when you are doing the LACP negotiation, means when you are doing this automatically, so you can go to the interface channel protocol, you can define, then you have to go and give the channel group name, mode active. So suppose one side I am using active, other side I am using passive, so they will go and form the port channel. It's very easy and straightforward. There is no much thing behind this. Now we have some important thing related to LACP, that we can have 8 interfaces inside group, and 8 interfaces we can work as a backup. So 8 plus 8, they are supporting total 16 interfaces that can form LACP, but these 8 interfaces are working as a backup. Now who will work as an active? That depends upon port priority. By default, that will be 32768, and lower is the better. Okay. Now, apart from that, we have other variable as well. Other variable is system priority. So suppose if you have two switch, and which switch will take the active role and which will work as a standby or secondary role. So who is the primary, who is the secondary? So that depends upon the system priority. By default, that is also 32768. and lower system priority is better. So suppose this is 500 and this is 32768. So obviously he is the active initiator and he has to take the decision. So by default, both will be the same, so that again, if you have the tiebreaker, so in that case, always the lowest MAC address will be preferred. So whoever switch having the lowest MAC address, he will take the decision, because by default we are not changing the port priority, we are not changing the system priority. So as per the MAC address in terms of system priority, lowest MAC address will win. In terms of port priority, lowest port number will win in case of tiebreaker. Now once you do the configuration, you can go and check show ether channel summary. That's the nice command. There you have the legends or flags. So for example, D for down, P that they are in the port channel, I for a standalone, S for suspended, R for L3, S for layer 2, etc. So you have the legends and you can check the status. So these devices S stand for layer 2 and U stand for port channel in use. So this port channel is successfully formed. This is layer 2 and up and running. Okay. On Cisco Nexus switch, the syntax is little bit different, obviously, in the Catalyst switch and the Nexus switch, but the concept behind the scene is the same. So this way we can go and create the port channel. Here you have some difference, means what is the difference between port aggregation protocol and link aggregation protocol. In port aggregation protocol, we are using the mode as auto and desirable. Desirable is equivalent to active, and I think there is some typo here. So desirable is equivalent to active. Okay. All right, so it's not a typo mistake, but in the diagram there are different use cases. So manually you can do on, either it's a PAGP or link aggregation protocol, they will work. Now on off, one side on, other side off will not form the channel, that's true. Then one side auto, other side desirable, they will form the port channel. Now here you can see that you have auto. So let me write here auto, and then you have desirable. This auto is passive for LSCP. So for example, PAGP, and this desirable is active. So if both side is desirable, they will form the port channel. Both side is auto, they will not form the port channel, and same is the case with LSCP that we have discussed earlier. So these are the use cases, these are the scenarios we have that will work here to form the ether channel. Let us perform the lab task here. In our lab, so for example, we have switches, and these switches, so for example, switch 1 and switch 2, their interfaces are 0 0 and 0 1 both side. So we'll go and form the LSCP port channel. First we'll try to form with the manual method. Method means you can make this on, and then we will use the LSCP as well. Even we have option for PAGP as well, but we'll focus on manual and LSCP. So let's go and do this. First of all, what I will do, that I will do the default for the interfaces, that we have E00 and 01, because we have done some configuration earlier and I don't want to do that here again. Means I don't want to have the old configuration, so I can go and default the old configuration. Now once I delete this, then I can go here and I can take the range of E0/0 and 1. Let me type it. So 0/0 and 1. And then we have this option of channel group. So for example, channel group, you can see the number is from 1 to 255. I can take 100 and then mode on means we are making this on, we are turning this on. So now here we can see, because this is the virtual device, so maybe we'll get some error. So port 100 invalid group slot number, etc, etc. Let's go back and try to make this 10. Okay, so this is the problem with the virtual switch itself. This is not the problem with the actual hardware. So if I use 10, it took the 10, and likewise I can do one thing, that show an interface E0/0. Let's copy and paste this configuration other side as well. So here interface range E0/0 to 1, and then I can paste the configuration, or we can go to channel group 10 or whatever we have. Let's see that we have created 10 and mode on. So 10 mode on. Now once we create this ether channel, then we have option that we can go and check show ether channel summary. Now here you can see that S stand for switched layer 2 and U stand for up. So we have this is up and running, and ports are in bundle. Now if you want to know detail about this, so we have option of ether channel, and then you have this option of detail. Even you can go and check the load balancing method as well. So I can go here and check this detail as well, and in detail you can check this information in detail as well. So here you can see all these detail options that we are getting. Now this is the manual method. Now suppose if I want to do this with the uh, automatic, or if I want to use any of the protocol, so in that case I should go to the interfaces first. We have the interface range, and then you can go and define the protocol. So this channel protocol is either LSCP or PAGP. That's a Cisco proprietary and the industry standard. Now because they are already in bundle, so we are getting this error. What I'll do here, that I'll exit here and I'll remove that group, or maybe we can go here and then we can remove that statement. So I'll do no here, and then I'll go and remove that statement from the other switch as well. So let's go to the range and paste this configuration, removed. All right. Next, what we can do here, that we want to give this channel protocol as a LSCP. Then I can go and define the channel group, say for example 20, and then you can see the mode we have is active and passive for LSCP, auto and desirable for PAGP. But I want active, say for example active this side, and other side I can go here, and there again I can go and type say channel protocol is LSCP, then channel group is 20, mode is passive. So either it should be active active or active passive, so it will form the port channel. Now if I go here and check show ether channel summary, I can see the ether channel summary. I can see that now we have this, and they haven't negotiated everything, so that's why it was showing as suspended state. Let's see what is the actual code here. So waiting and S and N. So here you can see that you have layer 2 not in use and waiting for aggregation. So still LSCP was not negotiated, and that's why it was showing that it is waiting. Now you can see that 20 has been formed and it is working properly. correct? So this is the way that we can go and bundle the ports. If you want to see more things related to this, so still we have the option that we can go and check the protocol and then enter. So here you have the LSCP protocol, you have group 20, you have that mode is on. So like that, we can go and check this. Now, suppose if we have some issue that is keep coming and coming and coming, so you have the option to do the debug for LSCP. Once you do the debug for LSCP, then you have to check that who is the sender, who is the receiver, etc. etc. Okay, so you need to understand that this debug how it is working. And if you go here and oops, so I can go here and I can debug LSCP events here as well. I can go to conft and monitor, or let's see if I can monitor over the screen, otherwise I have to go and check the logs. If any problem will be there, it will start sending these LSCP related negotiations problem that we can go and check. So I think terminal monitor is the command, console already monitors. All right, now if I go here and do any type of if any type of issue will come, so let's see. And channel protocol is PAGP. So if we create any issue here, and then if we verify this, we can see some problem. So I'll do one thing, no channel protocol LSCP, and then you can go and check the debug. So this is the way that we can go and verify the debug as well. Remember that whenever you are creating the debug, it's not recommended that you should do in the production network. You should have the maintenance window, or if the issue is major, you can take Cisco TAC online, and then you can do the troubleshooting, deep dive troubleshooting. In 3.1c, we have to configure and verify RSTP and MST. So let's start with RSTP, that is Rapid Spanning Tree Protocol. Now it's very good that if we know the other spanning tree protocols as well. So for example, it's good if we know STP, PBSTP, PBSTP plus, and then RST, and then RSTP, and then MST. But I'm going to revise those spanning tree protocol, at least the core behind the spanning tree protocol methodology. What exactly happening when we are talking about the switching network or switching architecture? So in that case, to prevent from the loop, we are running actually STP. So suppose if you have three nodes connected like this, like a triangle, suppose switch A, B, and C. Now here you can see that if you build your network like this, obviously uh, you will find the loop. So frame will be looped across this triangle. So uh, now again, you may think that why we are creating network like triangles or looped network. The answer is for redundancy. We are creating such type of network so that can provide us redundancy. So for sake of redundancy, we are creating such type of network. So for example, if one link is down, still you have one backup link, or maybe you have other links as well. So two link is down, still you have one link, etc. So for sake of redundancy in a switched network or in layer 2 network, we are creating loops, or we are at least creating such type of network design. Now the question here, second question may be that, okay, since we are creating the loop, then what is the loop prevention mechanism? And then the STP is the answer. Spanning tree protocol is loop prevention mechanism. What it is doing, that as per the priority, one of the switch will become root, and then obviously you have second root and non-root. But what is happening, that whatever interfaces that is going towards the root, they are termed as a root port. So you have a root port, and whatever interface you have in front of root port, those are termed as a designated port. So you have DP and then you have RP. Now, what about those switches where you have least priority? They are not root, they are not secondary root. So in that case, they will go and check the priority. If priority is same, then they will check who has the lowest MAC address. So one of the interface will treat as a blocking, BLK, say BLK as a blocking, and other will treat it as a designated port. So this is the blocking port, and then you have the designated port. So the summary of this explanation is that since you have such type of arrangement, so one of the interface is working as a blocking port, and suppose if your main interface is down, so still the traffic can go from this direction, because from blocking it will move to listening, then it will move to learning, and then it will move to forwarding. Okay, so it will take some 30 to 50 seconds to converge, and after that period of time, the traffic will go from the blocking, because finally it will become the forwarding port. Okay, now here, that's the problem, that we don't want to use STP, rather than we want to use a rapid STP. We don't want to wait for this time to converge the network, and that's the solution, is to use the rapid STP. So let's see that what are the things we have in the rapid STP. This is under 802.1W, or rapid spanning tree protocol. It's similar to STP, but there are dissimilarity as well. There are differences as well. We'll see that what are the differences we have. So BPDUs, here also you have bridge protocol data unit. These are the, you can think these are the control type of messages upon which the switches, they are building their STP, or they are building their RSTP. Here also they will select one root bridge as per the lowest bridge ID, that will be 32768. We'll see that in the next slide. Then the root and designated ports are elected and functional identical to STP. These are the similarities. What is not similar? We can see that here you have root port, alternate port, designated port, and backup port. In other hand, in STP, you have root port, designated port, and blocking port. So let me show you in the diagram. It's always easy to understand with respect to diagram. Here you can see that you have the lowest priority, so priority 100, who will become a root bridge. So this guy, and this is with respect to STP, and this is with respect to RSTP. So this guy is the root. Whatever going towards the root bridge is root port. Here you can see these are the root port, and then as per the high uh, priority, one will become block, one will be the designated port. If you have any issue in this direction, then it will move to the forwarding state and packet will flow like this. Correct. On other hand, you can see that in RSTP, he is the root bridge, for example. So these are the root port. We have a designated port, same like STP, but instead of blocking, here you can see that you have alternate port. Correct. And if you have two link, so one link is designated port, other one is the backup for the designated port. So instead of blocking, we have alternate port inside RSTP, and that is one of the reason for faster convergence, but there are other reasons as well. Here you can see that instead of blocking, listening, learning, and forwarding, we have discarding, learning and forwarding phase. So we are not waiting for that particular amount of time, rather than we are moving to the forwarding state as soon as possible, as quickly as possible. Now, initially, a switchboard starts in a discarding state, obviously. Then he has to start his learning. Now, a discarding port will not forward frames or learn MAC addresses, as the name suggests. A discarding port will listen for BPDUs. Alternate and backup port will remain in the discarding state. So you have your alternate and the backup port. They are still listening, but they are not actively participating. So they are listening. Otherwise, if failure will happen, how they will start forwarding the frame. So they are not in the forwarding state, but they are still listening the BPDUs. Now, RSTP does not need a listening state. Instead, if a port is elected as a root or designated port, it will transition from discarding to a learning. So here you can see that now if you have root selection, then in that case, the port will move from discarding to the learning state. Now what will happen in this case? A learning port will begin to add MAC address to the CAM table. However, a learning port cannot forward frames still. So here you can see that you have three state. In discarding, you are listening that. In learning, you are start learning the MAC address, but in discarding and in learning, still you are not forwarding the packet until unless you reach to the forwarding mode. Finally, when you reach to the forwarding state, then it will send and listen for BPDU, learn MAC address, and forward the frame. Root and designated port will eventually transition to a forwarding state. Okay, so once you have the selection of the selection of the ports, like root port, designated port, alternate port, etc., they will move from discarding learning to the forwarding state. Now the main question here, that why RSTP has faster convergence, and now you will see the core difference between STP and RSTP. Why? So BPDUs are generated by every switch and sent out as a hello interval. Switches no longer required artificial forward delay timer. Now what is happening in this case, that all the switches, they are generating their own bridge protocol data unit, and they are forwarding to their peer switch. Okay. Now what is happening in STP? STP code is 802.1d. Now in STP, BPDUs are generated by the root bridge. Now, if switch receive a BPDU from the root bridge on its root port, it will propagate the BPDU to the downstream or its neighbor. This convergence process is slow, and STP relies on forward delay timer to ensure a loop-free environment. So now you can understand that rather in RSTP, switches they are generating the BPDU and sending to the neighbor. But in STP, that is 802.1d, you have one root port, or you have one root bridge election. One switch will become the higher authority, and then he will generate the BPDU, and all the downstream switches will listen as per their delay timer or as per their timer. So you can see here that the default nature of STP is slow rather compared to RSTP. Now in RSTP, switch will handshake directly with their neighbors, allowing the topology to be quickly sync. This allows port to rapidly transition from discarding to the forwarding state without delay. So you have one-to-one handshake, and then from discarding it will quickly move to the forwarding state where they want to forward the packet. Now again, we have some port type in RSTP. We have edge port, and suppose if you know at this point of time about port fast. Port fast is one of the very popular term, that whenever you are connecting the switch with the terminating device, say for example server, so you don't want to send the BPDU. So I don't want to send BPDU, or I don't want to send STP control packet to the device that is non-switch, which is not a switch. There is no meaning of that. So that's the reason this particular interface, we are making this interface as a port fast, means quickly it will go to the forwarding state. Likewise, the edge. Now this edge port is working as a port fast. Immediately it is going to the forwarding state. So there is no listening, learning, forwarding like STP, or there is no discarding, learning and forwarding like RSTP, but directly it will move to the forwarding state. Now second port type, we have the root. Root ports are connected with other switch and has the best path cost to the root bridge. Obviously we know that root port is there. That is, one side you have root port, other side you have designated port, so you can reach quickly to the root bridge. And then finally you have point to point port. What this point to point port is doing, that port that connect to other switch with the potential to become the designated port for a segment. So it can become DP. And now if you go and refer the actual diagram that we have here, so you will understand. So you have root port that is going towards the root bridge, and here you can see the adjacent to root port is the designated port. Designated port adjacent is root port, but here you can see that you have designated port and backup port as well. All right, finally we have some important notes here related to RSTP. So let me quickly cover this. Now if edge port receive a BPDU, it will lose its edge port and status and transition normal through the RSTP process. On Cisco switch, any port configured with port fast become the edge port. We know that. Say edge port, I already explained this, is port fast. Quickly move to the forwarding state. That's the summary for the edge port. Now the RSTP converge process is below. So let's quickly understand the convergence process of RSTP, why they are converging so fast, and we have discussed this in the earlier slide as well. So let me quickly revise this. Now switches exchange bridge protocol data unit to elect the root bridge. This is valid for all the spanning tree protocol. Now edge port immediately transition to forward state because they are nothing but the port fast. All potential root and point-to-point ports are start with the discarding state. So this is actually important. By default, the ports will start with a discarding state. Correct? Means they are actively listening the BPDU. They are not learning the MAC addresses. They are not forwarding the frame. They are learning. So you can think behind the scene. Uh, it's not learning actually. They are listening. So you can think this as a listening active listener. Then if a port receive a superior BPDU, it become to a root port and transition immediately to the forwarding state. So obviously once you learn the BPDUs, then you will move to the forwarding state. Superior means that, suppose if you are getting one BPD, because in this case what is happening, all the switches, they are generating their own BPDs and they are exchanging it. So suppose this switch has low priority, say 32768, the default priority. Suppose this has priority 32769, he has 68. 69 is not a valid number, just for example. So obviously when he receive the PPTU, he will understand, oh, I am getting this with the higher or the superior switch, and then this will become, so this particular point to point interface will become uh, the forwarding state. Okay, for point to point port, each switch will exchange a handshake proposal to determine which port become the designated. Obviously, you can do the handshake and you have to define who is the designated. It's okay. Once the switch agrees, the designated port move immediately into the forwarding state. So here you can see the convergence is like little bit different than STP. So ports, they are starting with the discarding state and then they are moving to the forwarding state. At the moment you get some superior BPDU, it will become the root port. So again, remember, that if he is the root bridge, that means that you are the root port and he is the DP. Okay, so if he is sending the BPDU, it will be superior BPDU, correct? And when he is sending the BPDU, he is not superior BPDU. So that's why it is telling that it will move to the forwarding state, because you have only one blocking type of a state, that is the discarding. So either you will be at the learning or you will be at the forwarding. and you will be at the discarding, but there are less chances that when you have the superior BPD, you are in the discarding state. All right, so this is the summary for the RSTP convergence. Now every switch will perform this handshake process with each of the neighbors until all the switch will get sync. Complete convergence happen very quickly within the second. So all the switches, they are sending their BPDUs, and then switches, they are calculating on basis of BPDU and the superior BPDU. Now, whoever is sending the superior BPDU, he has become the root bridge, and his interface will become the designated port. The adjacent port will become the root port because he has to reach to the superior bridge, and according to that, all the switches will converge. Once they converge, once they sync, then RSTP will up and running to all the switches, and then it will take a few seconds, and that's why it's TCN in STP and RSTP both have different way. TCN is nothing but topology change notification. Now, what is happening in STP, say in case of when the switch move to forwarding state, or in a state of when they are going to blocking or down state, at that time they are generating the TCN, particularly in STP, that is 802.1d. Now that TCN bit will go to the root bridge, because we know that root bridge has to take a decision. Now what root bridge is doing now, that now if they are sending the BPDU, they are setting the TC bit, that is the topology change bit, and then they are forwarding this to all the downstream switches. So all the downstream switch will come to know that the port is going to the forwarding state, or switch interface is going to the forwarding state, or blocking or down state. Correct. Now again, this is little bit time consuming process, rather than in RSTP. What is happening, first of all, only non-edge port, when they are moving to forwarding state, so we know that this edge port are working as a port fast, or they are equivalent to port fast. Directly or quickly they are going to the forwarding state. So only non-edge port, when they are transitioning to forwarding state, they are generating the TCN. Now good thing about RSTP, that all the switches, that they can generate the BPDU and send the BPDU. So in this case, what is happen, that they are not waiting for the root bridge to understand or recognize that particular change, or that particular topology change notification, and then it will send to all the downstream switch, rather than the switch, whenever he got that change notification, he will update the other switch. So that's the reason this process is faster. So here you can see that any switch can generate the TC BPDU, allowing the topology to quickly converge via the handshakes. Now, a switch receiving a BPDU will flush all MAC addresses learned on designated port, except the port where they are receiving the TC, or topology change BPDU. So again, the core thing behind the scene is that all the switches in RSTP, they can generate and send the BPDU, and they can sync the RSTP database, or they can sync the RSTP states. Correct. Rather than they will wait for some max age timer to be expire, or some age timer to expire, or rather than they are waiting for some central authority, say for example the root bridge, to send the updates, to send the updated BPDU to all the downstream switch in the STP. All right. So here again you can see that we have some flavor of RSTP, and next section we are going to do the lab related to that. We'll learn on more on that. Now here you can see that not only the RSTP, their convergence is faster, but they are taking care of two failure. So either it's a direct or indirect failure. We know that the optimization of STP, if you read that STP, you'll find that you have certain mechanism that you can optimize the STP, like uplink fast, backbone fast, port fast is also one of the optimization technique. So port fast is already taken care inside the edge, or the nature of STP or the edge port. Edge port is working as port fast. Then for direct and indirect failure, this is also taken care inside RSTP. So we don't need to optimize because these features are already included. So in case of any direct or indirect failure, the alternate ports or the backup ports, they will not wait. Rather than they will move to the forwarding state. Okay. Now we have two implementation of RSTP. One is rapid per VLAN RSTP, that is the Cisco proprietary. So because we are going to run the RSTP on a Cisco switch, so we will go and use this spanning tree mode rapid PVST. And the other one is the multiple spanning tree that we'll study in the upcoming sections. Okay, so we have our lab setup. Let me quickly show you this lab setup and what we are going to do here. So for example, this is the topology diagram that we have. What I can do in this that, so for example, I have switch 1 and switch 2 and switch 3. So here I'm going to run the RSTP in between switch number 1, 2 and 3 like this. At the moment, I'll not use all the interfaces, all the switches, but this will solve our purpose if we run the RSTP in between that, and then we'll go and run few of the verification commands. Okay, so let's stop here, and in the upcoming section, we have a lab related to rapid PVST or rapid STP. Now we have the lab section. So what we are going to do here, I'm going to run the RSTP in between switch number 1, 2 and 3. They are actually 101, 102 and 103. So here you can see in the diagram that we have the ports that is connected like this, say 1, 2 and 3. So here we'll run the STP and then we are going to verify that. Here are the interfaces E00 from switch 1 to 2 and then 1 to 3 and then 2 to 3. I'll figure out in the with help of show CDP neighbor, and then we'll run that. So what I'm going to do, first of all, I'll go and create a VLAN to all the switches. So let me quickly go and create the VLAN. So for example, VLAN 10, because we know that all the VLANs, they have their own STP instance. So I can go to this script and then I can select all. I can go to conf t and VLAN 10 and then we can exit. All right, so send this script to all the switches. All right, now once we have this, and we can go and check show VLAN. So we have VLAN 10. Now we can go and check show a spanning tree. And for spanning tree, we have a few very important and uh, interesting commands that we used to apply all the time, or we used to run all the time, like show spanning tree detail, show a spanning tree summary. So here I can go and run the show spanning tree summary. Here you can see this summary of all these instances. Here you can see that blocking, listening, learning, forwarding, etc. Now we know that by default we are running STP, so that's why you're getting this result. We haven't enabled rapid PVST. We have to change the mode for that. We'll do that. Then you have the detail command. In detail command, you'll come to know most of the things like the topology change, notifications, the timers for STP, etc. and etc. So here you can see that we are dealing actually with switch number 1, 2 and 3. I don't want to add other switch and the interfaces, but we have so many interfaces that is coming here. So let me try to run few more commands, and then we have, say, interface. This is also very important command. So for example, interface 0/0 and enter. So now with this command, I can see that this particular interface is in forwarding state. The rule is designated, and like that, I can go and check. So basically, say for example, I have three switch, and in this switch, I want to know that who is my root. So suppose I have switch 1, and then I have, say for example, switch 2 and switch 3. They are connected like this. So let's try to figure out first of all who is the root. Okay, so for that I can go again back to the show spanning tree detail, and here we'll see that who is the root for VLAN 10. I am not considering VLAN 0. So let's leave this VLAN 0. Everywhere we are seeing this VLAN 0. So let me quickly go and check that do I have VLAN 10 everywhere. So I can see I have VLAN 10 here, and then I should have VLAN here. So I have all the VLAN, although I haven't added any interface inside the VLAN 10. So what I will do that I'll move some interfaces inside VLAN 10. So let's do that. I'll do show CDP neighbor. Let's check that who is connected with switch number 2 and switch number 3. So here you can see these are the interfaces. I can go here interface range E0/0 to 1, and this is switch port access VLAN 10. Likewise, I'll go and select the range that is from, here you can see 0/2 to 3, and this is also I'll make as switch port access VLAN 10. Okay, I'll go to switch number 2, and here also we'll run sociodp neighbor conf interface range E. Let's see. So we have 0, 0, 0, 1, 2 until like that it is connected. So from 0, 0 to 0, 3, and finally we go to switch number 3, and we'll check that neighbors for 1 and 2. So these are the ports. So I can go here and do interface range 0/0 till 3, switch port access VLAN 10. All right, because we want to verify this only for VLAN 10. So show spanning tree VLAN 10 and then detail. So now here you can see this is telling you the information about VLAN 10. That's okay. And if I go inside VLAN 10 and if I go and check who is the root, so here you can see that the root port ID is this, the priority into the MAC address. So let's verify that this MAC address belongs to which particular switch, correct? So now if you go here and check, your MAC address is AABB C006500. Now if you see this particular output, and what is the priority 32778, why this is 778? Because 32768 is the default priority plus the VLAN ID, so that's why it is showing like this. So everywhere you will find that the priority is 32778. So whoever has the lowest MAC address, that switch will become the root, correct? Root bridge. All right, so let's continue this. All right, so we can verify like this, and uh, because we have two interfaces connected, so you are seeing interface E0/0 up to 0/3. Although if you go to any of the port and you'll see the detail, you can see clearly For example, E0/2 for VLAN 10 is the designated forwarding, that is the DP, whose cost, whose port priority, port identifier, you can see here, they have the priority of 32768 plus 10, that's the VLAN number, and this is the address. Now the designated bridge has priority this is the MAC address, then again you can see the port priority and all other data. Now the question here is that in this scenario, who is the root and then who is the uh, non-root, or maybe who is the root and then what about the designated port and the root port and blocking, etc. Because we are running this spanning tree protocol at the moment. So for that you can go and check show a spanning tree, and then bridge means yourself. So we have two options here. One is the bridge option, that is my, and then what about the root? So I can go and check the bridge address and then the root address, and here you can see that bridge address for VLAN 10, we're focusing on VLAN 10, and root address for VLAN 10, both are same. So that means that this particular switch is the root. Now since this is the root, I want to know that what is the port status. So now if you go here and check, say for example VLAN 10, and say we have option for interfaces as well. Interface wise we can go and check, say E0/0, and then I can check the state as well and detail as well. So interface wise also you can filter. So for example 00 is the designated port. So if you go and refer the topology diagram, we'll find that we have different port from switch that is going to switch 1 to 2, say 00 and 01, and here also you have 00 and 0/1. So this is a DP, that means if you go and check here, this must be RP, correct? Again, whatever we have a study, we are following the same thing. So now if I go and copy this command here, you can see here this is a root forwarding, that's correct. So DP and RP, like that we can go and analyze. Now what we want to know here, I fully want to know the root address and the bridge address. So root address we know that will be 6500, and now again if you go and check the bridge address for this particular switch, what is the MAC address, because priority is the same. Likewise, if you go and check the MAC address for this particular switch, you'll find this is 6700. So as per the lower MAC address, switch 1 is the winner. Now if you go and check this particular interface, that the interface between switch 2 and switch 3, here you will find this blocking. So spanning tree VLAN 10, say for example detail. Now for VLAN 10, you'll find that few of the ports, so this is root, it's okay, 00. You'll find blocking, and you'll find uh, ports here in switch 3. A few of the ports are in blocking stage. Okay, so this is related to STP. All these commands related to STP. So what are the big commands we have, or important commands we have? Show a spanning tree summary. It will give you the summary, the spanning tree, and for that particular VLAN, you can check the detail like this. Then you can check, so spanning tree. So for example, sometimes we used to use filters as well. So for example, I can go and check include, and then um, we can filter certain things here. So for example, designated, or then I can add here designated, and say for example other also if I have. So everything is designated forwarding because of this is the root. So here you can see all the ports, they are coming like this. Yeah, so we have option, we can filter, we can add multiple filters as well. Here you can see that we have only two port address designated. All right, but what we have to do in this lab that we have to go and run the RSTP. So I'll go to the switch and we have to change the mode. So spanning tree mode is, and if I type question mark here, you can see that you have mode MST, PVST and rapid uh, PVST. Now, if you are changing the mode for rapid PVST, you should do this to all the switches, correct? So we'll go here and paste that command to all the switch. Then these switch will get converged. Once these switch will get converged, now we can go and check show a spanning tree, and you have the same options here, correct? So here you can see that for MST you have some other option, but show a spanning tree, and then we can go and check detail. Inside detail you can see that uh, VLAN 1, I don't want to check VLAN 1, but still VLAN 1 is executing RSTP compatible spanning tree protocol. You can check this. Better I can go and run the command show spanning tree VLAN 10 and then detail. So we can check only VLAN 10 commands. Now you will see that the port role will get changed. So DP will be DP. There is no problem on that in switch number 1. But if you go and check this in switch number 2 and 3, as per the rapid STP, the designation will get changed. So this is root, it's okay, designated forwarding, designated forwarding. Now here you can see this alternate blocking. So now you can see that the designations are getting changed. The role of the port is getting changed. So VLAN 10, so a spanning tree, VLAN 10 and detail. Now here also you can see this is the forwarding, alternate blocking, alternate blocking. Alright, so this is the way that we can go and run the RSTP and then we can verify that. Alright, so we can verify like this. Again, if you want to check more options, you can go to show spanning tree VLAN 10. If you want to check root and then other options, here you can see that you have options related to priority, port, hello interval, details, cost, etc, etc. Then if you want to check some other stuffs, here you can see if I go to a spanning tree, again if I want to check the bridge and then the protocol, and if I press enter, so here you can see it is running in RSTP. Same thing that we have in STP, there is no much change, slight change in the configuration, but the verification options are the same for STP as for the RSTP as well. Next topic we have multiple spanning tree, MST. Now why we use MST, and it's very interesting that we should go and check the generation or the evolution of a spanning tree protocol. We have three different type of spanning tree protocol or STP. We have common spanning tree protocol where you have a single instance of STP for all the VLAN. Then to optimize that, we can use PVST or PVST plus, that is per VLAN spanning tree. Uh, Say when we have single instance for all the VLANs, so for example, I have VLAN 10, 20, 30, 40. At the moment you enable the STP, you'll find that that STP is running for all the instances of VLAN or all the VLANs. Rather than we can go and optimize this behavior with PVST, PVST plus, but still further we can go and enhance this process with help of MST. Because the problem with PVST or PVST plus is that you have to maintain a separate STP instance, and that will be overhead in terms of CPU and memory for the switch. So if you have, say for example, thousands of VLAN, so at that time it's actually very difficult for switch resources to manage that much amount of databases. Now what we can do in multiple spanning tree is that multiple VLAN instances can be mapped with one STP instance, or multiple VLANs can be mapped with one STP instance. By default, they will be mapped with MST0, but we can create from 0 to 15, means total 16 instances of MST is possible to create. Now here you can see that each MST instance, that is MSTI, builds their own RSTP topology database, including electing its own root bridge. Now the selection of root bridge and the various parameters are almost exact that what we are doing in the STP. Only the way that you are going to configure is different. So how we are going to configure the MST? First of all, obviously, we have to change the mode of a spanning tree to MST. Once we change the mode, then MST further separates the STP topology into regions, means we have to define the regions. All switches in region must be configured with identical MST parameters. So what are those parameters? We have 32 byte of configuration name, 16 bit of revision number, and then we should do VLAN to instance mapping. Now what all these things you can see here in the configuration, even in the lab also you can understand more about all these terms and terminologies. Now here you can see that important information that if two switches are configured with different MST parameter, they belong to different MST region. We can have up to 16 MST instance, 0 up to 15. So suppose if uh, I just started MST, so what will happen? Obviously, everything will be followed inside MST 0. So if you do not do any configuration, simply you enable the MST, they will fall under the MST 0. We have this internal spanning tree is responsible for maintaining the topology for the entire region and all the MSTs. Only the IST can send and receive BPDU and encapsulate the MST information within the BPDU as an MST record or M record. The IST is always mapped to instance 0. So we have internal spanning tree as well, who is going to map or manage all the record inside the MST0. MST is compatible with other implementation of STP, and MST region is uh, obfuscated from non-MST switch, which will see the entire MST region at STP or RSTP switch. So it's not that, say, once you have multiple VLANs, so for example, I have VLAN 10 to 20, 21 to 30, I can map with MST instance 1, MST instance 2, etc. But it's still they are compatible or backup compatible with other MST as well. Okay, and those information will come as a non-MST region. So it's something like you have MST, STP, and then you have non-MST STP. They are compatible. Alright, how we are going to configure? First of all, we need to change the mode, and then we have to go inside the spanning tree configuration. We can give the name revision, and then we have the instance to VLAN mapping, and that's it. Once we do the instance to VLAN mapping, we can go and check the pending. And earlier I told you that the way that we are configuring the STP, like how you're creating the primary or secondary or root or etc. Likewise, we have to do the things in MST as well. Okay, so the commands are very much similar. Instead of VLAN instance, they will be the group of VLANs or the instance mapping. Okay, so what we are doing inside MST is that we are mapping various VLAN to one instance. So instead of running the commands over VLAN, that is the default nature of traditional or the STP 802.1d, we are running the command with respect to instance. Now, where this instance is pointing to, it is pointing towards the group of VLAN, correct? So this is the way that we can utilize the resources efficiently. If we have the VLANs, we can group those VLANs, we can map with the various instances of MST, and then behind the scene MST will work with those groups, and the overall performance for the switch, say for example the resource utilization, the CPU capacity, memory, etc., will be efficiently utilized. Alright, so let's stop here, and in this section we'll perform the lab task. Let us perform the lab task related to MST. So first of all, what I will do that I'll go and create say VLAN 10 to 100, because we are going to map these VLANs with MST instances. So in all the switch, I'll go and do the same. So now we have VLAN 10 to 100, and we can go and verify this VLAN. I can see that you have these many VLANs that I can map inside the MST instance. So what will be the command number one? That I should go and change the spanning tree mode. So now the spanning tree mode is MST, and I should do this with all the three switches that we have. So let me go and go to the configuration mode and oops, conf t and copy paste this mode command. Again, I'll go to conf t and do the copy paste. Now what we can do that we can go to the spanning tree and MST configuration mode. Once you are here, you can see that what options you have. You can go define the name, revision, instance. So we'll do that. First of all, I'll go and give the name. So for example, my MST, then the revision, for example, revision is 2. Then we have this instance. So instance and VLAN, say for example, instance 1, and then the VLAN range is from say for example 10 to 50. Then then we have instance 2 VLAN 51 to 100 that we have created. We can go and check the configuration with show pending. So here you can see that you have a VLAN instance, and whatever VLAN that we haven't mapped here, you can see that they are mapped with MST0, correct? So now we have two instances like this. Great. Now once we have this, then I can exit and we can run the normal spanning tree command. So we have show spanning tree MST, and then we can check the configuration. We can go and check the detail. So instead of MST, you can think like you are running spanning tree VLAN. So instead of VLAN, you think like MST. That's the command. So we don't need to memorize the commands and all. So here you can see this in detail, and the port ID, priority, and everything is in detail. Now different type of VLANs actually is mapped with the MST instance, so that's why it is looking like this. Likewise, I can go and run this command to other switches as well. So I should go and change the mode to MST, then we should go to the configuration mode and run these commands. So let's do it, and we can verify with show pending, and then we should go here and do this here, show pending, and then we can exit and exit. Now we can go and check show spanning tree MST, And if you want to check the details, we have the detail option. If you want to check any of the interface, we can check that also. If I have my MST, that's the name of my MST. So MST instance list, say for example, if I give a word, and let's verify this. So what word I have here, you can see that show spanning to MST. You can see the output in detail, and this is the name. And if I go here and check the output, say show spanning tree MS-tree, this is not supported here. So if I give, say for example, um, number like MST1, not like that, but we can go and give the instance list that we have. So what instance list we have created, that we can actually verify in the configuration. So we have instance 1 and instance 2. When I'm giving 1, so MST1 is coming like this, and if I give 2, it is throwing error for 2. And if you go and check, so MST in detail, so we have MST0, we have MST0, we have MST1, and that's the reason. So it is showing only 2 instance. Rather, if I go here and check the instance in switch number 1, and if we go and check 2, we don't have information for 51 to 100, like MST2 is not created, but it's okay. This is the way that we can go and map the VLAN to the instance mapping, and then we can go and verify the commands as well. Now one last thing, that if you want to change the priority, because switch 3 is the having the lowest uh, it's the highest MAC address, so its priority is lowest in terms of selecting the root bridge. That's why here you can see that who is the bridge, who is the root. So root is the switch number 1 because its MAC address is the lowest. But if you want to change it, you can go and change spanning tree, MS tree, and then you can go and check the, let me quickly check the configuration. So we can do like this. If you want to change the priority, um, we have, say for example, VLAN 10. You can see the priority is there. Now this method is for the STP, but here we are focusing to MST, and then the instance, say for example, instance is 1, and here you have the priority. So this, we have two options: either we can use the priority command or the root command. I just wanted to make this switch as a root, and we can go and give him a root primary. And now if we go and verify the MST command, so here you will see that who is the bridge and who is the root. So this switch for MST1. So now this priority automatically get decremented, and now that switch 3 becomes the root. Now you can see their port status is changing. Initially it was forward blocking, but now everything will become forwarding, because now my switch number 3 is the root switch. Okay, and same rule is applied for STP as well. In STP, you have to give the VLAN. In MST, you have to give the instance ID. All right, so let's stop here. Now we reach to 3.2. 3.2 is belonging to layer 3 technology. In layer 3, specifically, we have to learn about routing protocols such as OSPF, EIGRP, and BGP. So let's start with OSPF. Now, OSPF, that is Open Shortest Path First Protocol, is a link state protocol like ISIS. Now, what link state protocol is doing that instead of sending the entire topology table hop by hop, they are sending the state of a link to the neighbor device. Now, how this technology is working, and let me try to draw here. So generally, all the link state protocol, they are forming, first of all, the neighbor table. So they are sending the update to all the adjacent device or the neighbor. With help of neighbor table, they are forming the topology table. Sometimes we are referring this as a entire database as well. And finally, they ram the SPF algorithm here. From the topology table, they are going to form the best path, that is the routing table. So we have three different types of table: neighbor table or database table, topology table, and then finally the routing table. Now the mechanism behind this and the theory behind this we'll see in upcoming slides. So OSPF is entirely dependent upon areas. Generally, we are telling that we have one backbone area. So here you can see that you have area 0, and logically all the areas are connected with area 0. Now these areas are 32-bit. They can be a flat number, or you can define like in dotted representation 000 like this. Areas has continuous means area. You can see that you have area 0 and then area 1, 2, 3. Um, so maybe you can think that can't I connect area 3 with area 5 or 4? Yes, we can do that connection, but you can see that area 4 is not directly connected with area 0. So somehow I have to create tunnel, or the area 3. Uh, I have to create area 3 as a tunnel, or we have to use some sort of virtual link. So area 4 can think that is directly connected with area 0. So such type of arrangement we need to do, and then the link state advertisement will flow from one place to other place. That's the LSA, correct? The OSPF send LSA when there is a change to one of its link, and will only send the changes in the update. LSAs are additionally refreshed by after every 30 minutes. So how we can summarize it, that OSPF is a link state protocol dependent upon area. They are sending their LSAs or their advertisement to all their neighbors, and with that they are forming the neighbor table, topology table, and finally the routing table. Apart from that, that OSPF traffic is multicast. They are using 224005 for all the routers and 224006 for the designated router. The theory behind this we can discuss in upcoming session. They are using the Dijkstra shortest path first algorithm to build the routing table from the topology table, and they are supporting the variable length subnet mask. So here you can see that first of all they form the neighbor table, then they form the database, then they do their algorithm, that's the SPF algorithm, Dijkstra's SPF algorithm. Finally, they will form the best path table, that is the routing table. OSPF supports IP routing. Their AD value is 110. Their cost, their metric is cost. They are going to form the neighbor table, topology table, and routing table. Uh, all the areas should be supposed to be connected with a backbone. That's the area 0. If we have non-backbone area connected with any other area, then you have to create tunnel or virtual link in between that. Now, suppose we have such type of topology here. You can see that I have area 0 connected with area 1 and area 2. So now what we are going to tell about these devices, these routers, router A and C, they are termed as a ABR, area border router. They are termed as a ABR, area border router, because they are in the border of different areas. Okay, and we'll see that according to that the routes are also going to get reflected. So when we are talking about the routes, you'll find that you have O routes and then OIA, that is OSPF intra area. So you have two type of route, OSPF intra area route, that is this. Then you have inter area, across the area, that is this, and we'll see that we have E1 and E2 routes as well, that is coming from the external as well. Now if you see this diagram, it's actually very simple, straightforward, that we have two or three routers in area, but assume that if you have 50 or 100 routers in area, and suppose if I have 200 routers and all the 200 routers are inside area 0. So at that time, what will happen? The computation, means to run that SPF algorithm, becomes CPU intensive, rather than if you have a small areas and then you have 50 device, 100 device and 50 device in those areas. So in that case, all the areas, they will run their independent SPF algorithm, and then they will send the update to the backbone. So in that case, the way that we are going to run the SPF algorithm, or in other words, the process, the CPU utilization, the memory, will be optimized and will be used betterly, because now you're running the SPF algorithm across small areas, and then those areas are going to send their LSAs to the core or to the other areas. Correct? So that's the thing, and that when we are that's why we don't have only area 0, rather than we have multiple logical areas, and then we are going to divide the devices or the routers inside the area. Then here you can see that, suppose in case that if you have device and that is not connected with the area 0, so in that case you have to create the virtual link, the device which is separating the area, they are termed as a ABR. Then you have internal router, then you have backbone router. Again, these are just the terminologies. All right, now here you can see that you may have chance that you are connected with non-OSPF protocol. So you are getting the route, say for example, from the EIGRP domain. So in that case, that router is termed as a ASBR, Autonomous System Border Router. So now here you can see that C and D, they are ABR, Area Border Router, but router G is ASBR, because now the routes is coming from the other routing domain to the OSPF. Okay, so uh, here you can see that if you have any other routing domain, that will term as a separate autonomous system, and then you have to do the redistribution. Obviously the router G will do the redistribution from EIGRP to OSPF when it is coming to OSPF, and OSPF to EIGRP when you are sending your update to the EIGRP domain. Now in that case, we have E1 and E2 type of area. Now what is E1 and E2? Here you can see by default it will be OSPF external area type 2, that is the E2. So include only the external cost to the destination network. External cost is the metric is cost advertised from outside the OSPF domain. This is the default type. Then you have E1 that will also have the metric value, that is the cost, but this will be additive, means it will add the cost per hop per router. So include both the external cost and the internal cost. So that's why you have the external cost plus the internal cost to reach uh, the ASBR to determine the total metric, but E2 having only the external cost that will be constant. So in summary, here you can see that you have internal routers, that all router interfaces belong to only one area. You have ABR, you have ASBR, you have backbone router that is inside area 0. Okay, so this is the baseline summary for the OSPF routing protocol. In the upcoming sessions, we will learn more about OSPF terminologies, and we have to perform the lab as well. So what type of LSAs we have in OSPF? OSPF has a long list of LSAs. We are going to discuss the top 5 at least, because these we are going to use more and more in the course. So we have LSA here, you can see type 1 and type 2. Now these type 1 and type 2 LSAs are reside within the area. They are very much area specific LSA. Then we have type 3 and type 4 generated by ABR, area border router. They can flow from one area to other area. We'll see in the upcoming slide. And then we have type 5 LSA that is generated by autonomous system border router, means non-OSPF protocol. They are going to generate that. Now here you can see the detailed explanation of all the LSA. Type 1 is LSA and type 2 as well. They are within the area. The use of type 1 LSA is that they have the link, obviously the status and the cost of all those links, and they are generated by all the routers in a network. So you can think that type 1 as a default LSA generated by all the routers within that area. Then we have type 2 LSA generated by DR in the OSPF network or OSPF domain. Again, this is also specific to the area. When we have the broadcast type of network, obviously that time the DRBDR will come into the picture. Then we have the network summary LSA, that is type 3. What it is doing, that generated by ABR, and this can be used for inter-area communication. We'll see that all the places you have this inter-area link. So you have area 0 connected by different areas, and all these ABR shown in the diagram, they are going to generate type 3 LSA to do this inter area communication. Then we have ASVR summary. Now the next question here is, suppose from OSPF inter area you have to reach to non-OSPF domain. So for that reason we have autonomous system border router summary LSA, means somehow you need to reach, or somehow you have a route to reach to the non-OSPF protocol. Then we have external LSA type 5. Now this is generated by the ASBR, and this information will be flooded inside all the areas. So all the areas, if obviously you have the redistribution, all the areas should know how to reach to the autonomous system border router or the network behind the ASBR. We have type 6 as well, that is the multicast OSPF, type 7 as well, that is not so stubby area. And this type 7 is actually very important, and we'll discuss this later on. Now here in the diagram you can see that you have area 1, area 0, area 2. So belonging to area 1, area 2 and area 0, you have this router and network LSA, means type 1 and type 2 LSA will be generated in that. Then you can see that router C and D, they are ABR, so they are going to generate the type 3 and type 4, and then router G is belonging to ASBR, he is going to generate type 5 LSA. Okay, great. Then how this OSPF is going to form the OSPF neighbor relationship. So if you go and connect two OSPF or two routers in between, so suppose for sake of simplicity I have only two routers connected in a network. So in that case what will happen, suppose I have router 1 and router 2, and these two routers are connected, or they are inside area 0. So obviously these routers, because they are within the area and suppose if it is a point-to-point network, then they will send and receive the router LSA. Correct? So what will happen that they are going to send their hello packet in the point-to-point network, or in the broadcast network. This hello timer is 10 second and dead timer is uh, 40 seconds, so it's 1 into 4. And in the broadcast network, actually, in the NBMA network, that will be 30 second, and then the dead timer will be 30 into 4, that is 120 second. So they will send and receive, they will exchange their hello packets, and if they are matching certain criteria while sending and receiving the hello packets, then they are going to form the neighbor relationship. So here you can see that what are the things inside the hello packet, what are the fields inside the hello packet. They contains area ID, area type, prefix, subnet mask, hello interval, dead interval, network type, and authentication. Basically it is termed as that they have 8 field inside hello packet, and you should match at least the area ID, the subnet mask, hello and dead interval, authentication, etc. So some fields are mandatory that should match in between two routers to form the neighbor relationship. Okay, so here you can see that a neighbor table is constructed from OSPF hello packet, which includes the following: the router ID, the current state, directly connected interfaces, and the IP address of the remote interface of each neighbor. We'll see that in the lab section, and we'll go and we'll run the command show IP OSPF neighbor, and then we can see the specific about the neighbors. Now the next topic here is that OSPF designated router and backup designated router. So what is happening and how they are going to form the DR BDR, or how they are doing the selection for the DR BDR. Let's discuss about that. So here you can see in the diagram, first of all, these devices, they should have their priorities. So let me show you what I try to tell here. I should have slide for that. Yeah. So here you can see that that these devices, they have their unique identification. That's the router ID. All the routers in a network, they have the router ID. We can configure it manually, or suppose if device has the loopback interface, or they have the physical interfaces. First of all, they will check the loopback interface if you are not doing it manually. So that loopback interface will become the router ID, or the highest physical interface will become the router ID. So they should have the router ID. That will be by default if you are not doing it manually. Once they have router ID, then they are going to do the DR-BDR selection, and this selection will happen only in the broadcast network. So here you can see in the diagram that if we have router ABCD connected with a shared network or the broadcast network, so at that time they will go and select the DR and BDR. Okay. Now, what will be the selection criteria here? The DR-BDR selection are determined by the router's priority, which is configured per interface basis. The router with the highest priority becomes the DR, and the second highest will become the BDR, and the rest are DR to others, something like DR, BDR, others. Okay. Now, if there is a tie in the priority, whichever router has highest router ID, that will become the DR. Now we can go and set this priority like this also, like we can go to the interface and we can set IP OSPF priority, and then we can force to make certain device as a DR or BDR. Now by default the priority will be 1, so obviously the selection will happen with respect to router ID. So whoever having the highest router ID in the network, that will become DR, BDR, etc. like that, in that manner. Suppose if you don't want that certain routers or device will take part inside the DR, BDR selection, so you can go to the interface and you can set the priority as a 0. So if you set the priority as a 0, that device will not take part inside the DR, BDR. Okay, so what are the important things we have studied in this video? That type of LSA, then how they are going to form the OSPF neighbor relationship, what are the important fields you have inside the hello packet, all the devices they are sending the hello packets to the peer devices or the neighbor devices to form the neighbor relationship, then how they are going to form the DRBDR selection. Again, the router ID will be important factor here, and as per the router ID they are going to form the DRBDR, because by default we are not setting the priority. By default the priority will be 1, and according to the router ID they will select who is the DR, who is the BDR. Let us learn more about OSPF neighbor state, and then I'm going to perform one small lab task where we'll understand more about the OSPF process, OSPF actually neighbor process, and even the baseline commands of OSPF as well. So now when the OSPF, the first stage is that they have to form the neighbor relationship. When they are forming the neighbor relationship, at that time they are exchanging, or they are going through a process, or they are going through multiple steps. So what are those states we have? Here you can see that they will start with a down, init, two-way, etc. So in down state indicates that no hellos has been exchanged, but the actual process will start from the init state. Init state, the devices they will start sending their hello packets. We know that inside hello packet we have some important fields. Few of them are mandatory, like the area, like the authentication, uh, the network subnet, etc. So few of the fields are mandatory, that two sides or the neighbors, they should match those mandatory things. Then they will go to the two-way state. By the end of two-way state, uh, the devices, if they are in the broadcast network, they have to select the DR and the BDR. And by the end of two-way state, the devices, they are forming the neighbor relationship. Okay, then we have the external start and external exchange. Now external start and exchange is a state where the devices, they have to select that who is the master and who is the slave, so they can exchange their databases. So obviously the devices, they are sending their link state or LS information to each other to build the database. Once they have the database as per the uh, master and slave entry, as per the master and slave role, they have to exchange their LS type. Correct. So someone may sending say link state advertisement. Someone may asking link state request. So LSA, LSR, those things are going in depth when we are talking about the exchange state. Then we have loading, where all the devices, they have to sync their database, and by the end of this loading state, the OSPF process, they are forming the topology table. Remember, we have three important table. We have neighbor table. So by the end of two-way state, they will form the neighbor table. We have topology table. By the end of loading, the devices will form the topology table. And finally, once they have the topology table, on top of that, the devices will run the SPF algorithm, shortest path first algorithm, and then they have to form the routing table. We'll see that if we have the broadcast network, then they will have the rules like DR, BDR, and DR other. All right, so here you can see that suppose in broadcast network, if we have these rules, this DR other, they will go and stop at the level of two-way, because what is happening in that situation, in that case, is that we are giving the authority to DR and BDR to exchange all the LSs with all the other, rather than all the other DR others, they are exchanging their database packets. So that means they will stuck at the two-way state, means all the DR others, they will stuck at the two-way state. They will not have the full authority to exchange the databases. Correct? All right. So we have a small lab topology. In this first lab, just to start with, what we are going to do that we will go and initiate the OSPF process. So let me show you this. Although we have this master lab topology, what we can do as per our requirement will go and use it. So what does it mean that we'll go and make these devices, say for example R1, R2 and switch 101 within area 0 at the moment. So they will be the part of area 0, and this switch that you are seeing here, switch 105, that I will make as a switch only. Later on we will make this as a L3, but at this point of time I assume that I have R1, R2 and switch 101, and the IP that I am going to use, the IP will be, say, let me write here the IPs, and according to that I am going to configure the lab. So the IPs that I want to use is, say for example 10.1.1.1 and 10.1.1.2 as per the name of the devices, and here, say for example 10.1.1.101. They are inside the same broadcast network, so you can see that they will go and form the DR and BDR. Loopback addresses I will give like 111, and then this I can give 2222 as the name of the device, and this I will give as 101 101 101 101. Okay, we are going to initiate the OSPF process inside area 0, and then we'll see that how they're going to exchange all those hello packets and the important ls type. All right, so let me go and log into the lab devices. All right, I logged in, and we know that we have other interfaces and links also connected that I don't want. So this is the topology that we have. What I can do here, that I will start with 101 E1/2. So let's do that. I can go to, first of all, let's see this neighbor, and I want to shut down few of the interfaces that I don't want to use. So for example, I want to use only interface 1/2, so 0001 and 1/2. So 0001, so I can do one thing, interface range E0/2 to 3, shut down, interface E1/0, shut down, because I want to use 1/2 only. So rest of the interfaces I'm making shut down, like that. 1 also I want to make shut down. If I go and check show CDP neighbor, so I have 0001 and 12 that I want to use. Now next I will go to switch number 2. So switch 2 is not required in this particular lab, so leave it. Then I'll go to switch number 5, and we should check this E1/2 configuration as well. So I will go here and check E1/2, and what is configured here, nothing is configured. If nothing is configured at this point of time, at least what we can do is we can make this interface as a switch port. Correct. So here you can see this capabilities R, S and I, and that I don't want. I'll make this as a switch port. Then we'll go back to the switch number 5. Here you can see, and the interfaces we have is 0, 0, 1, 2, 3 and 10/0. So apart from that, what I want, that I want to make other interfaces as a shutdown. And we have so many interfaces here, you can see. Even we can leave it as well, just to check the configuration for any of the interfaces. Say so run interface E0/0 that is connected with router number 1, and then router 2. So these are the interfaces connected. I don't want to do anything. Rather, I will do one thing, that interface range E0/0 up to, for example, 4 maybe, and 3. I'll make this as a switch port and no shutdown. And then interface E10/0 that is connected with switch number 1, that if you see here, switch number 1, what interface we have here, let me scroll up, 10/0, yeah. So I can go here, interface E10/0. I'll make this also as a switch port, no shutdown. Alright, so we are very much good with switch number 1 and switch number 2. Here again I can go to interface E1/2. I'll make this as a switch port, no shut. Alright, so let me quickly see here that what I exactly required. So E1/2 should not be switch port. It should be a routed port. So I'll do no switch port, and then I'll assign the IP address. So for example 10.1.1.101, and then I'll create one loopback, say loopback 0, IP address 101 and 101.101. So what I have done here, we can check show IP interface brief. So I have interface E1/2 and one of the loopback interface where I have assigned the IP addresses. Okay. All right. Great. So now we can go to R1 and R2, and the interfaces you can see here. So I'll go to R1 first, and I can go to interface E0/0. I'll assign IP 10.1.1.1, and then I can do ping just to check that the far end switch is reachable or not. So it is reachable, then I'll go and create one loopback, say 0, and IP address I'll give 111 to that loopback. We'll go and check the show IP interface brief, so you can see that we have the IP configured here. Now let's go to R2, and inside R2 we have interface E0/0. I can go and give the IP like this, and then I'll create one loopback 0 where I can give IP related to as per the diagram or as per our schema 22222, and then let me try to ping. First of all, within the same network, obviously everything is inside the same network for this example. So what I'm doing, that I'm pinging to all the devices from R2. So now we have the baseline IP address connectivity connected. The thing here is that we are going to enable the OSPF to all these devices, and we are assuming that all these devices are inside area 0, correct? So let's do this, and let me go back to the lab. Yep. So before doing that, at least one of the device I want to enable the debug. So I want to enable the debug OSPF packets and events, debug IP OSPF packets, and then I want to enable the events as well. Okay, let's do this OSPF configuration. So we can go to router OSPF, and then you have to define the process ID, say 1 I'm giving at this point of time. Then I should go and advertise the network. So network is, I have two network, one is 10.1.1.0. I can go and give the wildcard bit inside area 0. So this is the format that we can go and enable the OSPF. And at the moment I enable that, you can see that we have event because we have enabled the debug as well. You can see that this router using this multicast address, and the router ID is get selected as 11111. We have discussed this earlier. If I go and check show IP OSPF, you can see the red router ID is 11111, and we have the other information as well. Okay, so we have the OSPF configuration, and periodically he is sending the hello packet. We can go and check the configuration for that, what we have done. So we have enabled the OSPF process, and then we have advertised the network, correct? So likewise, I can go here and initiate the OSPF process here as well. Then I can go and I can assign the router ID via the CLI command as well, means manually as well. But if you do not do this, automatically they will take this loopback, highest loopback address as a router ID. So then I have network 10.110.0.0.0.255 area 0, and then I have network 2222, say 0.0.0 area 0. Alright, and let me see that what configuration I have done here. Now they try to exchange this neighbor relationship. From there they will go and form the topology table, and finally they will go and form the routing table as well. Okay, so let me quickly see that what command I have given here for the network, because we have used /32, that's why I have given 0.0.0.0.0. Now somewhere you will find that you are moving to loading to full state, and here if we can see that information in the log message. So we have enabled the debug and OSPF authentication is 0. We haven't put any authentication, so it is telling that OSPF authentication is 0. And here you can see that we have this loading to full message. If you go and check show IP OSPF neighbor, then you can see that you have DR BDR selection already happened. For router 1, he is telling that router 2 is BDR. Now if you go to router 2 and if you check show IP OSPF neighbor, you can see that he will tell who is the DR. So for router 2, this 11111 is the DR, what is the interface, what is the IP address that we have discussed earlier. Now I'll go to switch number 1, and here also I'll go and do this router OSPF say 1, and then I will put the network, for example the loopback address that we have 101.101.101.0.0.0.0 area 0, and then I'll put the network that we want to form the OSPF relationship. So we have a network, and with the wildcard bit 0.0.0.0.255. All right, and within area 0. At the moment I'll do this, I can go and check show IP OSPF neighbor. Now you can see that he is seeing that who is the DR and who is the BDR, correct? The third device. Now if you go here and check the OSPF neighbor, you can see clearly that DR other. So now this IP is DR other. We haven't assigned the router ID manually, but here you can see that they can detect it. Means the router process can go and assign what will be the router IP or router ID for these devices. We can go and check like this, show IP OSPF, and you can see the ID. Now if you want to filter and use that, I try to do with this command. Simply you can go and check the ID. That will tell you who is the router ID. Alright, so this is the way that they are going to form the DR and BDR. And if I have one more device in the DR other, then you could find that the process will stuck as two-way state. Okay, so what I'm telling here is that if I am here and if I have one more device connected to this guy here, and that is also working as a DR other, then these two devices, they will form the they will stuck as a two-way state. They will not exchange the entire topology and database tables, etc. All right, so let's stop here. In this session, I'm going to cover OSPF network type, metric, and passive interface. And next section, we'll do the lab related to this. Now, if you go and check the syllabus, so let me quickly show you the syllabus. In this syllabus, you'll find that in 3.2, you have to learn about OSPF and you have to compare with EIGRP. So for that, what I'm going to do, that I'm going to cover EIGRP in different series of videos. So once we know OSPF, once we know EIGRP, it's easy to compare. Then in 3.2b, you can see that we have to learn, understand more about OSPF. And that's the thing we are doing at this point of time. So let's quickly understand the network type, OSPF metric, and the usefulness of passive interface. Now, OSPF is supporting a wide variety of network type. Here you can see that in OSPF, you have these many network type support. Now, how to memorize this, because you can see it's a big number, this network type. So you can think like this, that you have point to point and you have, see here, so point to point, and then you have point to point, point to multi-point, broadcast and non-broadcast, like you can think. So you have network type broadcast, and then you have network type non-broadcast, and then again if we add with point to point and point to multi-point. So now point to point, obviously we know that point to point is just point to point network, two devices are connecting with each other, it's a point to point network. Then what about point to multi-point? So here you can see that point to multi-point non-broadcast. So you can think that you have point to multi-point broadcast and non-broadcast. Okay, so that means you have 1, then 2 and 3. Apart from that, you have network type broadcast. So you have network type broadcast and you have network type non-broadcast. That means you have total 5 different type of network support. Now again, if you go and check the nature of the broadcast and non-broadcast, so if it is a broadcast, that means the DR-BDR selection will happen and the neighbor will form automatically, means you don't have to write the manual command to form the neighbor relationship, correct? But if it is a non-broadcast, and suppose if DR-BDR is forming, you can see that the hello is unicast multicast. When you're seeing unicast, means you have to go and use the neighbor command. So you have to manually form the neighbor, correct? So once we know about the broadcast and non-broadcast, and again you can see the timer as well. For broadcast network is 10 and 40, and for non-broadcast is 30 and 120 seconds, correct? Now same concept we can use here. So here you can see that point to multi-point, you can think this is a point to multi-point broadcast. So that's why it's a multicast. Hello. They will not form the DRBDR because again it's point to point, and you have so many points to point means point to multi-point. You can think like this. So whenever you have point-to-point network, you are not going to form the DRBDR because just two devices. Why you will form DRBDR? Then I get point to multi-point non-broadcast. Now this is non-broadcast, so that's why you have to go and use the neighbor command to form the OSPF neighbor relationship. That's the whole summary we have for the OSPF network type. So let me go back to the theory. Now here you can see that it's a broadcast. So it will do DRBDR selection, then it is using these multicast addresses. Because this is the broadcast, they will not form the neighborship manually. Automatically they will form point to point. No need to define the neighbors because you have only two ends. They will form the neighbor relationship. Their timers will be 10 and 40 seconds. They are going to use the multicast address. But again, point to multi-point as well. Everything that is valid here for point to point, it will be valid for point to multi-point as well. Okay. Now, then we have non-broadcast. Whenever we are talking about non-broadcast, then you have to go and form the neighbor relationship manually. Now, OSPF will elect DR and BDR, but neighbor relationship will be manual. And that's why we have this summary. This summary, it's easy to memorize. Even no need to recall, but just will make a point that okay, you have point to point, point to multi-point, non-broadcast, point to multi-point broadcast, and then you have broadcast and non-broadcast network. How we are going to do the configuration? Configuration part is actually very easy. Only one command is there to define the network. You have to go to the interface. Suppose you are over this serial interface, you go to the interface and use this command IP OSPF network. Suppose if you go and type question mark, then you'll get all the options. So is it a broadcast? Is it a non-broadcast? It's a point to a multi-point, etc. Each and all these options you will get. And if it is using unicast method, means if it is a non-broadcast, then you have to go and define the neighbor. Otherwise, rest of the configurations are standard OSPF configuration. So for example, NBMA, non-broadcast multi-access. So here we are going and defining the network type is a point to multi-point, and if it is a non-broadcast, then you have to go and define the neighbor, right? So just refer this summary and things will become easier. Now OSPF is using cost as a metric. Here you can see the speed and the cost. So for example, for fast Ethernet and EPUB, your cost will be 1, and then you can see for token ring for Ethernet, for token ring 4 Mbps, you can see the cost. Now the lower is better. So if lowest cost is there, that will be the preferred path in the route selection. How we are going to do the basic OSPF configuration, although we have done one lab. So there you have seen that you can go and initiate the OSPF process. You can define the router ID, otherwise it will take the highest loopback or highest physical interface if it is not configured. Then you can define the area, and that's it. So this is the baseline configuration. Now here interesting thing is that we are defining the wildcard bit. And now it is recommended that if you know the exact subnet, so according to that you can use the exact wildcard as well. So suppose if I am using point-to-point network, so I can use, say for example, 172.168 1.0. So here it's 17. So 172.171.0, and then I can use wildcard 0.0.0.3. So like that we can go and use the wildcard wisely. What will happen if we go and initiate the OSPF process, and once we start advertising the network, or once we put this network command, then they will send the hello packet. The neighbor relationship will start working. We know that as steps down init, two-way, X start, exchange, loading to full. First they will form the neighbor table, then topology table, and finally they will run the SPF algorithm and we'll get the final OSPF routing table. Correct? Now the final thing here in this recording, as was the theory, the passive interface, the concept of passive interface. Now, suppose if you don't want to form OSPF relationship, then you can go and make any of these interface as a passive interface. So suppose if I make this interface as a passive, then you can see that the passive means the command prevents update from being sent out or received from this interface. So if I go here in this example, it is showing this interface. So if you go and make this particular interface as a passive or any interface as a passive, they will not participate in OSPF neighbor relationship. Means they will not send or receive the updates. And that's the usefulness of passive interface. But generally how we are using this command is uh, we will do this thing no passive interface E0. Here you can see first of all we'll make all the interface as a passive. So the command one is passive interface default. Suppose if you have 10 interface, that means all the 10 interface you're not sending and receiving the updates, and then you will go and add the interfaces one by one where you want to send or receive the updates. Okay, we have one important note here that the passive interface command will prevent OSPF and EIGRP from forming neighbor relationship out of that interface. No routing updates are passed in either direction. So this passive interface is true not only for OSPF, but this is true for EIGRP as well. So we are going to stop here, and in next section, I will show you a few of the things that we have a study here, like network type, how you can go and change the network type and you can enable the passive interface. Let us do the lab. Here you can see the topology. uh, we have router 1, router 3, and switch 101. I'm using in between switch 105 as a L2 switch, so that means I have area 0. So this big blue circle is area 0 and the network is 10.1.1.0/24. Then I have switch 101 and 102 connected. That is inside area 2020, and the network is 10.1.102.0. So 101 is dot 1 and 102 is dot 2. I have already assigned the IP address. So what we'll do, we'll go and enable the OSPF process. Then we'll go and check the default network type, and then I will make any of the interface as passive interface inside area 0, and then again we'll verify the OSPF neighbor relationship. So let's do this. I can go to router OSPF 1, and even if we are here, we have option that we can run the script as well. So if you are doing the configuration over empty putty, you have this option for a script, say conft router OSPF1, and then you can advertise the network as well. I can select the devices and then I can send the script. Now once OSPF is configured, then I should go and assign the, or I should advertise the network, or should I can use the network command. So what you can do here, you can go and check the IP route, your connected interface, and in the network command, actually, you can go and use it with wildcard bit, and we should check this 10.1.1.0 is part of area 0. So we know as per our topology this is correct. Then we have one loopback here that will be depend that in which area you want to put. This also I'll put inside area 0. And then I have one more network, that is this guy here, connected with area 20, area 20. So these are my network command. Likewise, I can go to switch number 2, and I can go and check the connected routes. I can use my network command. First of all, I'll advertise my loopback inside area 20, and then I have my network that is connected, that is inside area 20, because the bottom switch is actually everything is inside area 20. So that's why area 20, area 20. All right. So at the moment we run this command, you'll find that both the switches, they are now interfaces are part of area 20, and they will run the OSPF, and here you can see that the OSPF uh, loading to full means all the states are completed. So I can go and check show IP OSPF neighbor. You can see full BDR and the interface as well. Then we can go and check show IP OSPF, actually show IP route OSPF. So here you can see that you have the metric value and you have the AD value. AD is 110 and the metric is 10 plus 1. So that's why it is 11. We know that for Ethernet interface that is 10, and then 1 is for loopback. So that's why it is showing like this. Alright, here you can see the Ethernet. So for that we have 10, and then generally 1 it is using for loopback. Alright, next thing that I want to check here is that is show IP OSPF interface, and that is E0/0. Now here you can see that interface where the network type is broadcast. So what I can do that the switch is connected over E00, I can go to the interface E00 and I can make that IP OSPF network as point to point. Now here you can see that you have broadcast, non-broadcast, point to, multi-point, point to point. And if you go to point to multi-point and type question mark, you have point to multi-point. By default, it will be broadcast, and then you have the non-broadcast like that. So I'm interested to make this as point to point, and both side I should do like this. So other side also I should go, and I should go here to E0/0 network point to point. Now you can see that again OSPF process is running. It is going from full to down, and the SPF algorithm is running one more time. And then we have the new tree, SPF tree, and from there we have new routing update or routing table. Show IP OSPF, and the interface is E0/0. Here you can see this network is now point to point. You can see this cost as well. There is other information as well related to timers, non-stop forwarding, etc. All right. So we have done this task with these two switches here. Likewise, I will go and initiate the OSPF process, and I will advertise the network for R1, R2, and only R1 and R2. We don't have any R3. All right. So let me quickly check here in switch 101 what is the complete OSPF configuration that we have done. So these three network, one network is belonging to the network that we have connected with R1 and R2, that is nothing but the area 0. And then these guys have one loopback address 111, inside area 0. And likewise, I'll go here and then I will use 222 area 0 and then this. Now if I go ahead and check show IP OSPF network, here we have 3 devices who is forming the OSPF relation. If I go and check show IP OSPF interface, I want to check the interface E0/0. So here I can see that again the network type is broadcast. Now in our topology, either I can use network type as a point-to-point or broadcast, but we have seen that chart that as per the topology, suppose if you are working or dealing with frame relay, then you can use NBMA and then you have the mode for NBMA, correct? I don't want to make this as a non-broadcast. If you make this non-broadcast, so suppose if I go to R1 and R2 and I should know what is my neighbor, show IP OSPF neighbor, and if I go to interface E0/0 and if I make this IP OSPF network is non-broadcast, then I need to add the neighbor command manually. So now if you check your neighbor, you can see it's a down, because in this case you have to use this neighbor command. So you have to go to router OSPF1 and use the neighbor command. Who is your neighbor? So this guy is your neighbor. Then use the neighbor command. This guy is your neighbor. So manually we are adding the neighbor now, and here also it is detached. So these are my neighbors. I'll go to interface E0/0. IP OSPF network is non-broadcast. Then router OSPF1. We'll go and add the neighbor this, and again I'll go and add one other neighbor. Then we can go and check show IP OSPF neighbor. Still this is down. Show IP OSPF interface and then E0/0. So now it become non-broadcast, but we are seeing here that the network is down uh, because we are using the wrong network type here. Uh, if we have the NBMA type of, or if we have a non-broadcast type of network, then we should go and use here. Again, you can see this hello and dead timer is changing. Okay, so what I'll do here that I'll go and make this interfaces again backup. Interface is 0/0 and IP OSPF network is, say for example, broadcast. So one side is broadcast and other side is non-broadcast at this point of time. And now you can see it is forming the relationship with the switch 101. So if I go and check do show IP OSPF neighbor, you can see it is forming this. Likewise, I'll go here and again interface is 0/0. IP OSPF network is broadcast, and then we can go and check show IP OSPF neighbor. Alright, so now we have to test the final piece, that is the passive interface. So suppose if I go and make one of the interface over R1 as a passive, so let's do that. I can go to router OSPF1. You can see that we have this command passive interface default, and then you can go and make no passive interface. So once you do this command, all the interfaces become passive, means your neighbor is down. So here you have to use no passive interface, and that is the E0 slash 0. E0 slash 0 is the interface. I want to make no passive interface. And again, if I go and check the neighbor, so here you can see this is up. So that was the lab related to whatever we have studied in the previous recording. You can refer this particular lab. Next, we have OSPF authentication and virtual link. So let's start with OSPF authentication. Now, actually, it's very easy to configure and it's different than RIP and EIGRP. What we can do, first of all, we can go to the area. So here you can see I'm over OSPF, I'm inside area, I am putting area 0 authentication. Then I can go to the interface level and then I can go and give the authentication key. So we have two things. We have the plain text or clear text, and then we have MD5. Now same way we can go and configure the MD5 as well. So again you have to go to area 0. Here you can see that I'm over area 0 here and the authentication message digest. Then I will go to the interface and then I can assign the message digest key. So it's very easy and straightforward. I'm going to show you in the lab section about the message digest key, this authentication. So more we can discuss in the lab. Now next thing here is what about virtual link? Virtual link is again one of the use case we have in OSPF, that for example, due to any reason the customer network they are not able to directly connect with area 0. We know that all the areas should be connected with area 0. So suppose you have area 1, 2 and 3. For example, later due to some reason you are connecting area 4 with area 3, not with area 0. So in that case we can create the tunnel in between area 0 and area 4. So the router inside area 4, they will think that I am part of area 0 or I am directly connected with area 0. And that's the concept of virtual link. Again, you will see the configuration here. The configuration you'll find it's a very much like we are creating that tunnel. So router, the area 1 is working as a transit, and then I have tunnel in between, say for example, area 0 and area other area. So let me go back here. So here you can see this is the classical example that you have area 0, area 1 and area 2, and then you are creating the virtual link in between that. Okay, now there are possibility that you may have area 0 and in between you have area 1, and that's again the possibility is less, but still you can create the virtual link in between that. Now once we create the virtual link, then over the area 0 we have put the message digest. So same key we can put over virtual link as well. Okay, so we have seen all these steps, and let's perform the same task in the lab setup. So we'll understand more about the authentication and the virtual link. Let us perform the lab related to authentication and virtual link. I have done the change in my setup. Here you can see that now we have R1, R2, and that's R2 but switch 105, then switch 101 and then switch 102. So R1 switch and then again switch and then the switch 102 in the bottom. Subsequent network IP addresses I have changed. So we have network 10.1.1, 10.1.2, 10.1.3.0, and then we have respective area like area 0, area 1 and area 2. Now in lab number 1 we'll go and um, create or run the OSPF in between area 0, and then we'll do the MD5 authentication. In the same lab later on we have to create the virtual link and we have to make area 1 as a transit. Alright, so let me show you this IP addresses assignment here. You can see that we have created an assign the IP addresses only so far as per the diagram. So oops, these are the IP addresses assignment related to R1, R2, related to R1 and all the switch. So now let's just start with area 0, that is R1 and switch 105. I'll go here and enable router OSPF1. Then I have network, say for example 11111, and then I'll put this inside area 0. So let me do that. Then I have network 10110. This also I'll put inside area 0. Alright, now we'll go to the switch, that is switch 105, and we can go and check the network. First of all, we'll go and initiate the OSPF process. Then we have one network, that is 10110, but we have 105 network as well. So let me quickly do that, and 00000 area 0, for example. Then we have the rest of network. So now you can see I have enabled this, or I ran this command, but it's still I can't see that OSPF is coming up and running. So I should go and check the IP over E00, and we should have at least IP reachability. So E00 here, it is correct. If I go and check the interface configuration for this switch, so let me try to check 0/0. Wow. So we have this command configured and protocol is up. So if I do the ping, so let me do the ping from here for 10111. That's the router IP. And I can see that ping is working. If we could go and check show IP OSPF neighbor, show run section OSPF. So here you can see that I have this network inside area 0, and then I have my network, that's the loopback, but still I can see that they are not forming the neighbor relationship. So now what I'll do, I'll go here and make this network as a 10.1.1.0 area 0, and then I'll remove this network statement. You can see that the problem here we have. Then again I'll go back and delete this and add this. So let me try to do both at a time. In router number 1, okay, and let's try to check show IP OSPF neighbor. Now they are in two-way dweller state. They stuck in dweller state. Alright, and if I go here and check in this, because we haven't removed OSPF from here, show IP OSPF neighbor. Okay, so the reason maybe now it is up. Maybe the network type that we haven't changed, but now it is showing it is up and running, so that's okay. Now we have the OSPF relationship over area 0. What I want to do now, that I want to run the authentication. So I can go to router OSPF1 and then area 0 authentication. Here you can see that you can do plain text if you want. You can leave with this authentication, or if you want to do the MD5, that is the more secure, then you can go and use this. Now at the moment I have done this, you can see that the neighbor is up, but we are getting one problem here that authentication key, you don't have any valid key. So now what I'll do, I'll go to 00 and then IP OSPF authentication. You can see that you have authentication and message digest option. So I can go and put the key as a CCNP. You can see here that you can go to authentication and key, and then you can see here that you have option say unencrypted. This is not that I'm looking for, so I can go and give the message digest, but I want to put the key as well. So let's see, IP OSPF authentication, and we can give the authentication if it is a plain text and authentication key. And suppose if I'm using authentication, then I have this option for message and digest. Actually, that is quite a confusing option that Cisco is giving to you. So, because obviously natural thing is that we'll go and check IP/OSPF of authentication, and then whatever authentication will be there. But in case of message digest, you should go and check IP/OSPF, and then you have this option of message digest key if you want to put your key. So I'll put key as the CNP, but let's see, yeah, MD5, and then so this is the long command that we need to put here. Now if we go and check show IP OSPF neighbor, we can see that neighbor is down because of mismatch of the, or we don't have the key configured to the other side. So here also we can go to router OSPF1 area 0 and then the authentication message digest, and then we'll go to interface E0/0 IP OSPF message digest key. Now we are getting this error MD5 CCNP. So now you can see that the neighbor is coming back up. So this is the way that we can go and do the authentication inside area 0. Now what I want to do here, that I should go to the I should first of all do the OSPF rest of the configuration, and then we'll create the virtual link. So let me do that. R1 is okay. In R2, let me check show IP route and what network that we have configured so far. So we have router OSPF1. We should have one more network, that is 10 dot let's see the network. That's 10.1.2.0. So 10.1.2.0 0000255, and that is inside area 1. Correct. So this network is in area 1. Now we have switch number 101. So let's do the configuration for switch number 101. And what network we have? We have network 10.1.3.0, that is in area number 2. Then we have network say 101, 101, 101, 101. So for example, I'll put this in area 1, and then finally I have 10.1.2.0. that is inside area number 1. Alright, so we are very much done with this OSPF configuration. Finally, we have switch number 102, where we have 10.13.0 network. So I'll go here as well and should enable OSPF, and then we have network. Say for example, first of all, I'll advertise the loop back, and this is inside area 2. And finally, we have network 10.1.3.0, that is again inside area number 2. Now here we'll see that after running all these commands, we go and check show IP OSPF neighbor. So he has neighbor that is 102 and 105. Now if you go here and check uh, to the switch 105, you will find show IP OSPF neighbor. So he should also have two neighbor, but if you go and check show IP route for OSPF, you'll find that he is not getting 102 because it is never getting tunneled or passed through the area 1. So in this case, we should go and create the virtual link. Okay, so let's create the virtual. So I'll go and create the virtual link here inside area number 1. So first of all, 105 and then 102. So already we are here, and router OSPF1, area 1, and then the virtual link. What is the ID? So we know that the neighbor ID is this. You can see here that we have option for message digest key as well, that I'll put later on. But that's it. Area, virtual link, and then the peer device router ID. Now I'll go to 101. I'll go here and router OSPF1, area 1, virtual link is what's the router ID you're looking for to make the tunnel. That's sorry, not this one. This is 105. Okay, so I'll go and remove this, and that's it. So once you do this, then if you go here and check the OSPF, you'll find that you will start getting the routes. Now what is happening here in this case, that since you don't have key configured, so inside area 0 we have the key configured. You should go here and give the key so it will work properly. Go here, and here also we'll go and we should give the key, say CCNP, and now you will see that they will start getting the routes. So if I go here and check show IP OSPF neighbor, now show IP route OSPF, you should get 102 102 102. That will be the final valid verification for this. So after running this command, I can't see that anything is happening. And let me go and check here as well. You can see this configuration is 100% correct. You're creating virtual link with this, and in router 1 also the configuration key, everything is correct, but it's still they are not forming this. So what we can do here, that we can go to router OSPF one more time. Router OSPF1, area 1, say for example the authentication is message digest, this belongs to area 1, and here also we have area 1 as well. Let's see the final configuration. SPF. Now, invalid key for 10/0 that we can verify. So what is happening actually here, that if you go and check the configuration, you'll find that once you are putting the key here over the virtual link, now this belongs to inside area 1. These are the interfaces where you have to put the authentication key. So for example, as a MD5. But when we are creating the virtual link, actually, in that case, that is going to propagate area 0 only. So it's not required to put the key there. Okay. But just for the uh, security purpose, I'll go and put the key over 10/0 and E1/2 as well. So E say 10/0 and IP OSPF, or maybe IP, yeah, OSPF message digest key 1 MD5 CCNP, correct? And then finally I can go here and interface E2/1/2. Wow. So this much configuration we have done. And now if you go and check show IP OSPF neighbor, first of all we should have the neighbor. And if I go to R1 and if I go and check show IP route, so here you can see that it is getting the route as a uh, O routes, as it is directly connected with area 0, and we don't need to put actually authentication over the area 1 interfaces that I have done, but for sake of security we want to put the authentication key at all the places, so you can go and put the authentication keys at all these places. Alright, so this was the authentication. And the next important section, we have OSPF summarization, different type of areas, and the default route concept. So let's start and understand the summarization. Now clearly you can see in the diagram that you have area 0 separated by area 1 and area 2. And for example, if you're getting routes, say 10, 1, 0, 0, 1, 1, 1, 2, 3 up to 7, and other side you can see that is 8, 9 up to 15. Now we are sending all these routes to the core router. Here you can see all the individual route, and hence the database or the topology table of the inside the area 0 will increase. Rather than what we can do, that we can summarize the area 2 as 10.1.8.0 and area 1 as a 10.1.10/21/21, correct? So in that case we are sending only one update, and our routing table will be efficiently utilized. Doing so, we can reduce the load over the router CPU. So this is one of the interesting use case we have with inter-area OSPF summarization. Now what's the command? Command is very easy and straightforward. We can go to the router, and over the router you can go to the area, and then you have to use the keyword called range, and then you can use the address and the subnet mask, and then this will be done. Now there is one important point to mention, that suppose if you have some of the routes in between that is not part of subnet. So for example, If I don't have 1.5, 1.6, is still I am using this summarization, that is 10100/21. So in that case, what we can do, we can use the concept of static route null zero, and we can point out this summary route towards null zero. So that means that anything that is not matching, that will be garbaged, that will be bit bucket, correct? Now here you can see that note that after 12.16, and now we are running the modern or advanced version of operating system, even this command is not required. It was required for the earlier version of iOS. Now the second point related to summarization we have is, suppose if the summarization is coming from the external system, it's not related to inter area routing, but it is coming from outside. Now at this point of time, we should go to the ASBR. Suppose router B is ASBR, who is connected with non-OSPF domain or non-OSPF routing protocol. So in that case, you can do the summarization, but syntax will be little bit different. So in this case, instead of doing area, the command is summary address and then the network and the subnet mask, means whatever network we want to summarize. Correct. So now this concept is very much like we are doing the aggregation, and we have two type of border. We have ABR and we have ASBR, and like that we can easily do the summarization. Now here you can see that we have one use case in case of ASBR summarization, that if you don't want to advertise certain prefixes, so in that case, you can go specifically to that particular network and you can use the keyword called not advertise. If you use not advertise, obviously these networks will not be advertised inside the OSPF. Okay, so this is the concept related to summarization. Now, next important concept we have is the OSPF area type. Now I have one summary chart as well where we can go and summarize the OSPF area type after a few slides. So here you can see that you have area type called backbone, non-backbone, stub area, totally stubby area, and not so stubby area. That is NSSA in short. So let's learn and discuss about the area type. Now starting with the basic area, that is the normal or the standard area. We know inside that area we have LSA type 1, we have LSA type 2. So here you can see that we have all the LSAs inside the standard area, say type 1, type 2, type 3 and 4 generated by ABR. Then we have type 5 as well, that is generated by the ASBR. So it is able to understand all the LSA. That's the standard area. Now the second thing here, that when you are making a stub, at the moment you will make the area as a stub, the stub will not accept type 3 and type 5. But remember, they will automatically inject the default route. Now doing so, we are not, while doing so, you can think like this, while doing so, we are cutting off the SPF calculation. And who is doing the SPF calculation? My CPU, my process. So that means that we are cutting off the intensive cycles, CPU cycles, and hence we are providing good type of optimization in terms of CPU and memory. Correct? Now, what's the command? Again, the CLI command is very easy and straightforward. You can go to the network. So here you can see a router process. First go to the router process, and then you can go to area 1 stub. At the moment you do the stub, that means it will start stopping type 4 and type 5, although it will get router, network and ABR generated LSA. That is type 1, type 2 and type 3. And other thing is that it is generating the default route. Now the third concept we have is the totally stubby area. Now what totally stubby area even will do, that will accept only type 1 and type 2. It will not accept type 3, type 4 and type 5 LSAs, although it will go and generate the default route for type 3, 4, and 5 LSAs. Again, the use case is that we are saving the bandwidth, we are saving the CPU core, process cycles, etc. Now the command here is interesting that here we have used in a stub area, we have used area 1 stub. For totally a stub area, you have to add one more keyword, that is no summary. So the command is area 1 stub no summary. It will stop LSA 3, 4, 5 and it will generate the default route. Okay. Now the fourth one is not so stubby area. Now, why we need not so stubby area? Here you can see that you may have chance that area 0 is connected with external network, or you may have chance that area 1 is connected with external network. Correct. So in that case, we'll see that when you have area 1 connected with external network and you want to filter some sort of LSA, you are going to use the not so stubby area. Means it's a stubby area, but it's not fully stubby area. What it will do, here we'll see that like a standard stub area, NSSA area routers will share type 1 and type 2 LSAs. Okay, they are not blocking type 1 and type 2. NSSA area will also accept type 3 LSA. So they are going to accept type 1, type 2, type 3. But NSSA will not accept type 4 and type 5. Okay. Now we are going to introduce one new LSA, that is LSA type 7, that we haven't discussed so far, but not so stubby area is linked with LSA type 7. And what's the use of LSA type 7? Now we'll see. So if an ASBR exists within the NSSA area, this is ASBR will generate type 7 LSA. Again, NSSA areas are almost identical to a stub area. If area 1 was configured as NSSA, it would not accept any external route originating from router G as ASBR outside area 1. So here you can see that they are not accepting any type 4 and type 5 LSA. Rather than we have type 7 LSA. So here you can see that it will not accept, this is the router G, it will not accept any external network, external non-OSPF domain network. Correct? Great. However, area 1 also has an ASBR within the area router A. Those external route will be flooded into area 1 as type 7. So here you can see that you have area inside area 1, you have router 1 and who is getting the uh, external routes, and that will be flooded inside area 1. Now these external route will not be forwarded to other area as type 7 LSA. Instead they will convert it into type 5, and that's the key, and that I'm going to summarize. Type 5 LSA by area 1 ABR router C. So what is happening here when you are creating not so stubby area, in that case you are getting type 7 LSAs, and router C, what he will do, he will convert type 7 LSA to type 5 LSA, and then it will flood it into the other area, or the other area will calculate as per the type 5 LSA update. The configuration is very simple. What you have to do, you have one keyword, go to the route process and then area 1 NSSA. Okay. All right, and final concept we have is totally not so stub area. So let me stop here, and remaining concept we'll discuss in the next recording. But here you can see the summary, and in this summary, let me try to highlight backbone LSA 1, 2, 3, 4, and 5. They are not getting LSA 7. Non-backbone like area 1, area 2, etc. They are also getting all the LSA stub area, LSA 1, 2, and 3. Totally a stub area, only LSA 1 and 2. Remember, they are going to generate the default routes. Then not so stubby area type 1, type 2, 3 and type 7. This type 7 will be converted to type 5 and then it will be reaching to area 0. That's the overall summary we have with this recording. So let's stop here and next section will continue from here. Let us continue where we have left off. Now next concept we have is not totally not so stubby area, that is TNSSA. So what is the main difference between a stub and totally a stub area? The same difference you'll find between not so stubby area and totally not so stubby area. Totally not so stubby area will allow LSA type 1 and 2, and he is going to filter type 3, 4 and 5. Here you can see the configuration is very straightforward. You can go to OSPF area and then you can give area 1 NSSA. The keyword is no summary. And here we have the summary just for your reference. Now the next topic we have is OSPF and relation with default routes. We know that when we are generating to a stub area and totally a stubby area, at that time the OSPF process, they are generating the default route. But in case of ABR and ASBR inside a standard area, we don't have default route. Now suppose you are sending LSA type 3 from router C and you are expecting that you are getting say LSA type 5 from router 1. So you are getting LSA 5 from router 1 and it will go to router C and then other areas. Likewise, LSA type 3 will go to B and A and actually B and then A and then the external network. At that time, suppose for the external network, you want to create the gateway as router A, so we can go and create the default route. So here you can see that additionally force router A to generate a default route, including itself as the next hop for the external network and injects into this inside area 1. Okay, what is the command? Command is router process, go to router process and default information originate. So this will inject the default route. But in case suppose you want to force it, so for example, if a default route does not exist in its routing table, router A can still be forced to advertise a default route using always command. So in that case, if I want to force the default route, in 3.2 we have to study about border gateway protocol. Although the syllabus, you can see it's very small, that we should configure and verify eBGP and do some path selection or learn best path selection criteria. But I'm going to start with zero. I'm going to start with the beginning of BGP. So what is BGP, what is IBGP, eBGP, etc., etc. So let's start. What is border gateway protocol? The first question arises is that already there are protocols, routing protocols, there is still why I need one extra protocol. Now the answer for this is that this is the exterior gateway protocol. Means this will override or this will run on top of any of the underlying protocol, any of the underlying IGP protocol, and it will work such as the application protocol. And that's true. If you see the port number that BGP is using, this is using TCP port number 179. Generally, applications, they are using TCP port numbers or they are using TCP or UDP. So BGP is a type of application protocol generally built to run over the over any of the protocol and cross the one or one autonomous system. Again, the autonomous system is one region, so cross one region and then it can go to multiple regions. Or if you want to control multiple region routing or the network advertisement or the routing control you want across the multiple region, then that's the protocol. Or in other words, we are telling that it's a protocol for internet. It's a highly robust protocol, and it has so many tuning options. It has so many attributes, so we can uh, tune it, and that's the thing. So it says advanced vector protocol with high level of tunability that can go across the regions. It is a type of application protocol, and the final point about this is that it can interact, or it can hold, actually it can hold a big amount of a routing database or routing table. Okay. Defined by the AS path, we know that autonomous system to autonomous system, it has its reachability. It is a distance vector protocol. It has the autonomous system number defined here. You can see from 1 to 65K. Few of the numbers are private and reserved. Nowadays, we have dotted notations as well for the BGP. Now, here you can see that why you want to use BGP. So when you have multiple connection exist to external autonomous system, means you have multiple exit, or you have multiple ISP connected with you. Either those multiple connections with the same carrier or provider, but connect via routing policy. The existing routing equipment can handle the additional demands. So it is highly tunable. So if you want to do some sort of preference, path preference, some sort of load balancing, etc., etc., so those things are achievable with help of BGP tuning capabilities. Okay. Now, one very important point here is that BGP true benefit is to controlling how traffic enters the local AS, local autonomous system, rather than how traffic exit from it. So the true benefit is that how you are controlling the traffic when it is coming to you, when it is coming to local AS. Now we can have two type of neighbor. We can have IBGP, or we can have eBGP, exterior and interior BGP. IBGP means within the autonomous system. So in this diagram, router B, C, and D, they are IBGP peer, or they can be IBGP peer. And then different autonomous systems like AS 100, 200, 300, they can be eBGP, exterior BGP peers. Now we have options that what type of IBGP relationship I want. Do we have full mesh, or what other tuning options we have? We'll go and check later on that we have multiple options when we are talking about the internal neighbor relationship or interior neighbor relationship. Generally, when we are creating the IBGP relationship, we should create fully meshed. Otherwise, there are some other options to uh, do the advertisement for the network that one IBGP peer is getting and advertising to other devices. Now, one device can have only can be part of one autonomous system, and if you want to make part of multiple, it will throw an error. We have the AD value fixed for eBGP. For eBGP, the AD value, the administrative distance is 20, and for IBGP, it is 200. Okay, so that means the eBGP routes are preferred than IBGP routes. So 20 versus 200, lower is better. That thing we know. Now the BGP peer messages, we have BGP peer messages. What type of messages we have? So we have open message, we have keep alive, we have update and notification. Now open means that I want to form the relationship with my neighbor, and here you can see that an open message is sent between peer to initiate the session. The open message has several parameters like version, local AS, BGP router ID. Then you have the keep alive. Keep alive is something like you are sending the keep alive message to your neighbor that you are alive or not. In BGP, by default, it is sending that keep alive message after every 60 second. A 60 second into 3, that is 180 second, is the hold down timer. So after 3 keep alive message, if you are not getting response, that means your BGP neighbor is dead. You will mark this as a dead with help of notification message. So now this notification message is sent when there is a fatal error condition. If a notification message is sent, the BGP peer session is toned down or reset. Anyways, if your peer is down, that means you will send the notification peer is down. Then we have the update message that are used to exchange the route between the peers. Now here in BGP state machine, that is the finite state machine, we have some other messages as well. So what exactly this is, that when a BGP peer session is forming, at that time, if you go, suppose if I have two routers and I want to form the BGP neighbor relationship in between that, so you will find that they will exchange some sort of messages. Those are idle, connect, active, open send, open confirm, established. Correct? So idle means that it is initiating the BGP state, then connect, that you are waiting for the remote peer, active, that you are actively initiating the connection. Obviously this connection is TCP. Then open sent. Open sent means you have sent the open message. Once you send the open message, then BGP listen for a reply, keep alive. So you have sent the message, you got the acknowledgement, that is open confirm, and then the finite state machine will establish the connection. Correct? So it's very easy. Idle, connect, active, open send, open confirm, and they establish. Now if peer is stuck in active state, the potential problem may be that maybe you have password mismatch, maybe ACL is blocking port number 179, maybe you have incorrect AS, maybe you have incorrect neighbor statement, and so on. So if it is stuck in the active state, that means it is not good. Correct? Then you have to troubleshoot and make this as a working. Now how we are going to configure it? We know that one router can be part of one BGP autonomous system. Go to the router BGP, and then the autonomous system. If it is a eBGP peer, remember, if it is a eBGP peer, they have the TTL value of 1. So they are always thinking that their next hop is, or their peer is one hop away. So in that case, you don't need to modify the TTL value. You don't need to modify anything, any other thing. Means router B of AS100 and router C of AS900, they have to give simple command, router BGP, neighbor and remote AS. That's it. Now, if it is a IBGP pair, then you can go and you want to update the source. So for example, generally we are using a loopback as a router ID. So in case of IBGP neighbor relationship, you need this update source loopback command, correct? And I'll come to that eBGP multi-hop option as well. Suppose if you have eBGP relationship and it is multiple hop away, then you can go and use the eBGP multi-hop. So for example, 200. So in this example, it is showing simply that suppose if you are using the loopback address instead of this physical address, if you are going to use the loopback address, that is again one hop away, then how you will form the relationship? So in that case, say for example, the router C is using the neighbor 1111, and we can see that who is 1111. Obviously this router B loopback address is 11111. So in that case, that will be hop away. For that we should go and use neighbor 111 eBGP multi hop 2. So you should count how many hops away your peer is, and then you can use this multi eBGP multi hop command. Finally, we can go and use the password with the neighbor command. So for that, we have the neighbor password, and so for example, Cisco. We have other option as well, that if we want to change the keep alive timer, we have discussed this about that the default keep alive is 60 seconds and 180 seconds is the hold down timer. But suppose if we want to use some aggressive timer, we can go and use timers BGP. 30 and 90. And in that case, we can go and set the BGP timers. All right, so let's stop here, and in the next section, we'll perform the lab, whatever we have covered in this section. Now we have to perform the lab related to BGP. Here you can see in the diagram that I have router 1 in AS100. So AS100 and AS200 router and switch 105, they're going to form eBGP relationship, exterior BGP, and in between AS200, say for example switch 101 and 105, they are going to form iBGP relationship. Okay, so let's start the configuration for R1. If I go to R1, I can go and I can initiate the router BGP process. So for example, AS is 100. Then what is your neighbor? Now for neighbor, I can go and check the directly connected neighbor. So that is directly connected neighbor is this 10.1.1.1.10.1.1.1.0.5. So he has the neighbor 10.1.1.1.1.0.5. And then what is the remote ACE? So we should go and give the remote ACE. Say for example 200 I'm going to configure. Then here if I go and check show IP BGP summary, you can see that state is idle, correct? So it has initiated, and if I go and do some debug IP BGP, what type of packets I want to debug. So for example, I don't want all, but if I can get events and monitor. So I can go here. Yeah, I can see some of the messages. So already we are monitoring over the screen. It's showing some of the events. If we debug IP BGP, just wanted to see the TCP number. So all address families and import in IPv4, keep alive, don't want that, out in, etc. Okay, if I do all, then it will be big output. Okay, now one other command we have. So here you can see that at least I'm getting this message, active went to active to idle. It's tried to move from idle to active, but it is not. And then here you can see that you have the TCB. So if we go and check show TCP, TCB, and then enter, show TCP, and if you want to see the brief, you just wanted to see the open ports if you have, and if you have any other option related to that. So you have the TCP TCB. Actually that's the command. TCP TCB is the command, and if you know the TCB address, that will work. Anyways, so let's move on and go to the other side. Here I want to initiate the router BGP process 200, and then the neighbor is a 10.1.1.1 whose remote AS is 100. That's it. So now if I go here and if we see the packet, here you can see, let's stop the screen. So here you can see that you have the open capability is open, and then a route phrase, then open again, active went to open send to open confirm. These exchange we have actually checked in our session, and then you can see the neighbor is up. And now if you go and check the TCP TCB, So now you're getting this established session, and you have the address as well. And let me do let me undebug, and now you can see the output for this. You can see the port number is this, so local port is this, the foreign port is this. Great. So most of the information we are getting from here. All right, so now the eBGP relationship is up and running. Now what I want, that as per our diagram, I want to create iBGP relationship as well. So for that, I know that neighbor is say 101, 101, 101, 101, and whose remote AS is the same that I have. But since I am using the neighbor command, which is the loopback address, so I want to do the update source loopback 0, and I should check sure and interface loopback 0. So yeah, that's correct. Now I'll go to 101. So let's go there and let's do the configuration for this. First of all, let's enable the BGP 100 whose neighbor is 105, whose remote is the same that I have, and then the neighbor this update source loopback 0. Now if you go to 103, we go to 105, you will get one message, show IP BGP summary, that you have two neighbor, both are up and running. So one is up and running, that you can see here. You have a 0 prefixes, straight is up and running. Now if everything is okay and correct, in between 105 and 101, so 101 and 105, then they should form the BGP, but it is not. So let's quickly check the BGP configurations, show run section BGP. So here you can see that I am part of 200, and this is also part of 200. So here you can see that directly you can see that problem, that we should have correct configuration. This is part of 200, and now you can see that we are getting some sort of uh, notification messages. We have seen that this is something when you have some error notification messages, we are getting some malform uh, construct. And if you go here and you check the summary neighbor idle, like that it is coming. Let's go back and let's change the AS, and we'll come back to 10. All right, so let's complete the basic lab. Now here, if you go to 101, we can see that the BGP AS is wrong. So I will go and do the changes. We'll go and change this to 200, and then rest of the configurations are correct. All right, now once we done that, we can go and check the summary. You can see this is up and running. Likewise, if you go and check show IP BGP summary, that is up and running. All right, so now once we have this, what we can do, we can check other basic stuffs as well. Now, for example, that we are going to continue the lab, plus I'm going to add few topics more in the lab section. We'll go and check the BGP neighbors once we enable run the BGP. Then we'll go and check the BGP neighbor. Plus we have one concept related to BGP synchronization. what does it mean by BGP synchronization. Although our lab setup is different, but I'm going to take same type of structure, that I have one device for eBGP and few devices for iBGP, and then already we have checked the iBGP and eBGP, how we are going to form these BGP tables. Now what is happening, that once we have the neighbor table, then it will build the BGP table, and then we have the routing table, correct? But one of the important table we have is the neighbor table. We have this command show IP BGP neighbor, where we can go and check the BGP neighbor details. If you want to check the specific detail to a specific neighbor, then you can go and use this command show IP BGP neighbor and the neighbor address. Next, we have the BGP synchronization rule. Now this is important. What is happening, that the general rule for BGP, or the golden rule for BGP, is that if your BGP is there inside the autonomous system or within the autonomous system, so you should enable iBGP rule, or you should do iBGP full mesh capability inside the autonomous system. Suppose if you do not do like this, so what will happen? Say, for a example, in this diagram, uh, this AS wants to reach to this network. Now suppose if I have iBGP relationship here, so here I have obviously the eBGP, and here obviously we have the eBGP relationship. So the traffic or the update will come to B, and then B it can go to D, because remember, in BGP the iBGP neighbor relationship, it is not mandatory that they should have physical connectivity. So these BGP relationship can form over non-connected interfaces as well. Okay, so that means that I can have the iBGP relationship in between B and D. Now then it will go and reach to E. Now at this point of time, the router C, he don't know about this network 10505 etc 10500. Next time if the return traffic will go and hit to D, and again suppose if it will go to C, since C is not having the update related to 10500, or he don't know how to reach to 10500, he will be working as a black hole. He will start black holing the traffic. So what is the rule then? Then the rule here is that you should have eBGP relationship, should have iBGP relationship in between all the devices, correct? And that's the rule you have. You should have this type of mesh a rule or the topology, and that's the reason we are using uh, some sort of other technology like configuration or route reflection. Because say if you have so many devices within autonomous system, and if you go and turn on BGP, and if you do this full mesh iBGP relationship, then obviously the CPU, the core utilization, memory utilization will increase. So this is not the optimal design solution. This is not that all the routers could achieve this target, because obviously they have to think more, because they have more number of control packets to process. The same explanation here. What we can do for BGP synchronization, uh, the local AS is not a transit, so in which case you don't need, if your AS is transit, or all routers in the transit AS run iBGP and are fully meshed. Okay, so the question here is that when you don't need the synchronization rule, answer is when your AS is not working as a transit. Second, when you all the devices in the transit, they are running the iBGP rule. How you can disable the synchronization? The command is no synchronization, and you can see that 12 0.28T synchronization is disabled by default. So in latest code, the synchronization rule is disabled. All right. So let's stop here and we'll go back to our lab section, and whatever small and basic verification commands are there, first of all, we'll check that before moving further. Now we are going to perform the lab task. You can see in the diagram that we have AS100, we have AS200. Inside AS200, we have devices that are going to form the IBGP relationship, and in between AS100 and 200, we have the eBGP relationship. So let me quickly log into the devices. We are going to perform some of the tasks that we have covered already in the theoretical section. So let me quickly show you that what configuration I have over these devices, and obviously let's see the IP addresses as well over these devices. So if I send this script, you can see over switch 101, we have this IP. Let me show you this diagram as well. So here you can see the diagram and the IP schema. Router 1, that is inside AS100, having loopback 1111. All the switches, they have loopback as their name. So for example, here you can see the loopback IP, then the interface IP, then the interface IP. All right, so you can refer the diagram that we have, and as per our diagram, we have assigned the IP addresses to the interfaces. All right, now next thing that we should go and check the BGP neighbor. So I can go and check show IP BGP summary to all the devices. Now here I can see that as per our diagram, uh, we have eBGP relationship and the IBGP relationship. Now, if we have this type of topology, still what you want that switch 103 and 105, although they are not directly connected, they are indirectly connected, they should form the neighbor relationship. In that case only they have the full mesh, correct? So suppose even I have the back-to-back connection here, although I don't have, but still I can go and form the neighbor relationship in between the 103 and 105, because underlay we have EIGRP up and running. So before doing that, you can see here that all the devices, they have their eBGP and IBGP relationship running on. eBGP in between R1 and 105. So 105, one interface having eBGP relationship, other one is having IBGP. Now suppose if you want to know detail about that particular neighbor, so what we can do, we can go and check show IP BGP neighbor. And first of all, let's see that in this neighbor command, let me see that uh, what outputs you have. So you can go and simply check show IP BGP neighbor. Obviously it will show you all the neighbors. So here the neighbor ID is this, belonging to 100 as a autonomous system, the router ID, the establishment, what time the neighbor got established, what type of messages they have exchanged. Here you can see open, notification, update, keep alive, and route phrase. So like that we can get the details. Now if I am very much specific to a certain neighbor, then I can go and run the neighbor command related to that particular neighbor. So I have one neighbor 10.1.1.1, and I can run and I can verify that. Okay, so what I will do first of all, that I want to show you that we can form the IBGP relationship in between 105 and 103. So let's do that. I'm already inside 105. I can go here and router BGP 200. I have my neighbor, for example, 103, and whose remote is the same. Then for this neighbor, I can go and use update source loopback 0. Now again, I will go to the 103 and we can run the same command. Then we have the neighbor, say 105, 105, 105, 105, and the remote is the same. And then the neighbor update source is loopback 0. Alright, so we can see here now show IP BGP summary that we have one new neighbor added. So not only my directly connected neighbor, but my indirectly connected uh, neighbor is also there. That's the true power we have with the BGP, because this is working as a overlay type of protocol. All right, so once we have all this information, then what I want, so I want to have a, so for example, in router 1 and 105, if you go to router 105 and you want to put the password, suppose if I go to neighbor, say neighbor 10111, and you can give the password, the Cisco. So if you put password from one side, other side also you should go and check the password, router BGP 100, and just to show you that it will take some time because we know that keep alive is sending after every 60 seconds and the hold down timer is 180 seconds. So it will take some time to tear down the neighbor relationship. Still your neighbor is up and running because BGP is meant to be slow protocol due to various reasons. So if you wait, it will take some time because one side your neighbor having the password, other side we don't have the password. So I'll wait till the timer will expire, and then I can come back here and I can set the password. Meanwhile, we'll go and check the other option. So we have timer option as well. So for example, I can go here to the router process and then I can check the timers for BGP. Oops, timers, BGP, and then keep alive. I can give 30 and then hold down. Suppose if I 10 and 30, keep alive 10 and hold down if I give 30. That means for all the neighbors it is true. Now suppose if you are specific and you want to change the timer for a specific neighbor, so for example 105, 105, 105, 105, then also you can do that. So where we can go and check the timers here, you can see so many options we have. So for example 20 and 60. So it is telling that you should go and specify the keep alive, say for example 20, and the hold down is 60 as a peer group. So then it will take that command. uh, we can check later on about the peer group as well, so we can leave it, but yeah, we have option that we can go and specify over the uh, per neighbor as well. Okay, so let's quickly see this BGP configuration. So here I have the neighbor with some timer, and then if I go here and check, and we can go and check show IP BGP neighbor 10.1.1.1. So here you can see that we have the neighbor established time. It is showing that what is the hold time timer and the keep alive. Although if you go here and check show IP BGP neighbor 105 and what is my neighbor, that is 10.1.1.105, and here you can see that still it's this because maybe the command that we have run is uh, okay. So here you can see the timers and the neighbor command. When we are running this neighbor command earlier, so let me show you that we are getting some error because that was not my neighbor. So that's the reason it was throwing an error, correct? Because my actual neighbor is uh, 10 11110 not 105 105 105. So what I'll do now, I can go here and I can do this neighbor and then 10.11.105 timers. I can specify say 10 and 30, and that's it. All right, we'll go here as well, and I can go here router BGP 200, neighbor is 10.111, timers are 10, 30, and then we can go and check show IP BGP summary, clear IP BGP say star. I'm clearing the BGP table, and now if we go and check the neighbor table, so let's go and check the summary. Now you can see that after clearing that, we have the authentication issue because we haven't put the password for one side, and here you can see the password issue is there. So I should go and show this neighbor and with the password. So I can go here and give the password as Cisco. Once I do that, you'll see that it will get converged and the neighbor will come back up. Now it is up. So we know that in BGP, first of all, it will form the neighbor table, then it will go and form the BGP table, then it will go and form the routing table, or those things will go and get added inside the routing table. Okay, so let's stop here, and next section we'll discuss more about all these behaviors. We have very important topic, BGP best path selection. We know that BGP has a long list of attribute, and with help of these attributes, BGP used to uh, provide best path. So what are those? Let's understand those first, and then next we have series of lab, and we'll test all these attributes, at least the important path selection attributes in the lab section. So how BGP providing the best path selection criteria? BGP contains multiple routes to the same destination. It compares the routes in pair, starting with the newest entry and working towards the oldest. Now, if you see that how it is going to determine, so suppose if I have multiple paths to reach a certain destination, and then I'm going to check, means BGP is going to check criteria A, B, C, D, etc. in order to provide, okay, if this criteria, so I have to go via this path. If this criteria, I have to use this. If this criteria, I have to use this, like that. So this is in the order. First of all, it will go and check the highest weight. Then it will go and check the highest local preference. Now the weight and local preference we'll see in the lab section as well. We have following lab with that. You'll find that weight and local preference, at least local preference, is one of the attribute that is mostly used. Now both the weight and local preference, they are dictating the best outbound path. So what we are doing, we are applying the weight and local preference, um, say attribute values or these values in the inward direction. So we are going to apply to the inward direction. That's the key actually. So where you're going to apply these and to whom he is going to affect. So we are going to apply in the inward direction, inbound, and then they are going to dictate the outbound path. So that's the important thing that I want to cover. Now here you can see the order. So let me go back. Weight, local preference, locally originated route. We know that if it's local originated route, their next hop will be 0000. That means it's the self-originated route. Then the AS path. Now AS path and MED, the metric value, both are again important. So remember, weight plus local preference, both are very much similar. Then AS path and MED. These are the attributes that is used more and more in the production network. So AS path, we know that BGP is dealing with, or BGP is a distance vector protocol. And as per the AS, so you think that one autonomous system has a router for a moment. And then if you have to cross more number of AS or more number of hops or router, that means it is not preferred. So if I am reaching to certain destination with 3 AS versus 1 AS, that means that 1 AS means via the path I am reaching with 1 AS, that will be the preferred. So shorter AS will be preferred. Then the origin code in the number, so IGP over EGP over unknown. Then MED, again I told you that this AS path and lowest MED, both are very much similar, and even we have lab as well for these. Then BGP route type, eBGP over iBGP. eBGP will win. Then the age of the route, who is the oldest is preferred. Then the router ID, who has the lowest BGP router ID. Then the peer address, which router originate from the router with the lowest IP. So everywhere you will see that except weight and local preference where the criteria is high. Apart from that, AS, MED, then age, everything is lowest or the oldest. Correct? All right. So here you can see that weight and local preference are applied inbound, dictating the outbound. That's the key actually. So these 3-4 lines are the key. Inbound dictating outbound path, and AS and mid are applied outbound dictating inbound. So what does it mean? So at least in case of MED, and let me draw here. So suppose you have ISP1, ISP2, and then you have your local AS. Now in case of MED and AS path, if you want to prefer ISP1 versus ISP2, so then you will go and apply the either MED or the AS path, AS prepend. That's the key. Because you have to choose, because you are choosing the outbound, so you have one subnet XXXX and you want to prefer either ISP1 or 2, you can use this method. Now when we are going to use the local path, so in that case, say when you are going to dictate the outbound path, so suppose if you have two exit and you want to choose one exit via versus second exit. So that in that case, you are going to apply the either weight or local preference. Obviously, I'll go and clarify these terms in the upcoming lab, and we are going to check the scenarios as well. So here you can see that you have one situation, one scenario that you have one route. So for example, 192.1.1.0, that router D is also getting, router B is also getting. Now what I want, that I want that route should come or should preferred via router B. So in that case, what we can do, that we can go to router A, say router A, and then we can give neighbor and then the wait command. That's the one way. The other way, nice way, is that we can go and use the route map. So then what we can do, we can create one ACL or prefix list or access list, and then we can create the route map. We can match the prefix list, and then we can set the weight, and then we can go and apply to the neighbor. So here you can see the direction. Direction is in for the outbound traffic, correct? So to reach this network, I have applied weight to my neighbor, and that neighbor, so that means router A will prefer B to get these routes, correct? Again, you have the local preference. In local preference, the same thing, only the way that we are going to do the coding will change. And here you can see that um, we are going to apply now. Local preference has little bit difference with weight. What is that difference? So unlike weight attribute, local preference is passed on to IBGP peers and sending updates. Local preference inform IBGP router how to exit the ACE if multiple path exist. So now what we can do, that local preference, even I can go and apply to these guys. So suppose local preference here, if I put 200, and if I put local preference 100 here, obviously this path will be preferred, correct? So that's the use of local preference. And here you can see that we have the example, but here we'll check the route map way of applying the local preference. Again, you can see here the direction is inbound, so here we are at router D or maybe at router B also, there's no problem. So what we are doing for router B and D, here you can see that B and D, lower is better. So here, if B is 200 and D is 300, obviously the traffic will come via this B, because his local preference is 200. Likewise, you can see here in the policy, we can create the policy for B and D as well in the upcoming lab section. So I have this route. Same way we have created the route map and we have applied it. I'm matching this, and then I'm setting the local preference as so for example 300. Okay, and then I'm applying in. So here you can see that is 1.2, that's my neighbor. Then I'm applying in. Likewise, I will apply with local preference of 200 to router B. So obviously router B will prefer. Okay, so here you can see there's difference between weight and local preference. The local preference is passed on IBGP peers when sending the update. So that's actually the main reason you will not find use of weight more and more, because anyway the weight is Cisco proprietary as well. So mostly you will find the use case with local preference. The same thing we can do with weight with local preference. So better use local preference. And in the lab section, so we have the lab section. In the upcoming session, I will go and perform this task of weight and then local preference, and we'll see that how we are applying the in rule to affect the outbound traffic, correct? All right, so let's stop here. We'll start the lab now. Let us perform the lab task. In the lab, what we are going to do, first of all, I'm going to show you the entire setup that we have. Here you can see that we have four different autonomous systems, say AS50, then AS100, AS900, and AS200. Now from AS200, you can see the iOS, the router is router 7, for example. There I have one loopback, and that loopback is loopback 7777. 7.7.7.7, and that particular network I'm advertising with BGP network command. So they will go and reach to AS 900, and then it will go and reach to AS 100. Inside AS 100, it will go and reach to router number 2. So before showing a complete path and how it is reaching, let me quickly go and show you the uh, configuration that we have. So if I go here and check the configuration, show run section BGP, uh, here you can see the configuration, and these IPs that you're seeing over the interface, these IP addresses, you can refer the topology diagram as well. So router 1, here you can see the router 1 has very minimum configuration. It has one interface, and then we are advertising one of the network. Then router number 2, you can see the BGP configuration, where we are running EIGRP inside the AS, and then we have two neighbor peer command, router 3 and router 4, and obviously we have one eBGP with router 1. Likewise, the configuration, BGP configuration for router 3. So let me do this. So here you can see the configuration for router 3. Router 3, in the diagram you can see that it has eBGP relationship as well. So on the top you can see eBGP relationship with AS900. Likewise, we have router 4 configuration for BGP. Then we have BGP configuration for router 5, and then you can see router 6 and 7 as well. This is router 6 configuration, and finally router 7. Now what we have done, you can see that inside router 7, we are advertising one of the loopback with the BGP network command, and then we are going and seeing that how it is reaching to router number 2. So if I go and check show IP BGP, first of all I'll show the BGP table. So clearly you can see this AS is getting prepended. So the originator for that is AS200. So here you can see this 777. So the originator, then next is 900, and then it is reaching to AS100. Now here you can see that you have valid and best path, and who is the valid and best path? So it is telling 172.1.7. Now if you go here and check 172.1.7, so this is the best path. Via this it is going and reaching here, although you have the alternate path as well, that is 172.1.6. So 172.1.6, that's only the star we have, and the star means valid. So that means if I go and check show IP route for this particular network, and let's see. So here you can see that it is coming via 172.171.2, and they have learned this is the router tag and how many hops, etc. Correct? So it is learning via this. So what I want at this point of time, that it should go and learn via this particular neighbor, not via this neighbor. Other thing that we can see here, that is this changing the next hop? So if I go here and check the diagram, so obviously whenever it will go and move to the eBGP, then it will change the next hop, correct? So from here, either from router 3 or router 4, it will go and reach to router number 2. But suppose behind router 2, you have one other router in the same AS. So at that point of time, you can see some differences. So you have to do some next hop self command, correct? So suppose if I go to router number 1 and if I check show IP BGP, now since this is the eBGP relationship, so for this route, who is the next hop? So he is saying that his next hop is changing. That's okay. But if router 1 will be also inside AS100, then it will be the problem. Anyway, so what is our target here? We want to have, or we want to learn this particular route from this next hop or from this peer. So let's use the wait attribute. Before that, I want to create IP prefix list. So IP prefix list, say loopback 777 is the name of my network. Even I can go and give the uh, a sequence number, and then I can use this if I want. So sequence 10 and then permit 7777/32. All right, then I'll go and create one route map. Say my wait permit 10. What I want here, I want to match. So let's see, match the, let's see what is the option we have. So match the IP address, and that is the prefix list. What is the prefix list we have created? This loop 777. All right. Now what I want to do with this, I want to set, what I want to set the wait, say for example 8989. Then I will give one default statement for route map where I will not match anything. Say for example 100. We can go and check the route map configuration. Say route map. So what we have done, that we created one IP prefix list. We have matched with the route map. Then we have set the width for that. Now we should go and apply this to the neighbor. And which neighbor you want to apply? So you want to apply this with 172.161 dot, oh, sorry, we want to apply with this neighbor, that is 10.1.1.2. So I'll go and apply with say 10.1.1.2. And what's the route map we have? The route map name is my TT. Because this is wait, so I want to apply in the in direction. So here you can see that it is telling that okay, so this is not the configuration that we have done. If you go and check, we have created the neighbor with the loopback, correct? So we should apply the loopback statement. So here you can see, so I should go neighbor, and the neighbor is router number 4, that is 444, and then the route map, and that will be in the my wait in the in direction. All right, now if you go and check show IP BGP, now clearly you can see that uh, the next hop is not get changed. So for example, that's a problem actually with IBGP, and that's just to prevent from the loop. So that's a loop prevention mechanism. So what does it mean? That here you can see when the routes are coming, say 77777, and when it is entering to this AS, they are putting their uh, IP as a next hop. When it reaches here, it should put these IPs as a next hop first of all, correct? So we should go and do a small changes in the configuration. So let me go and do the small change in the configuration. So let's do this. I can go to router number 3, say router BGP 100. I can tell neighbor 222222222 next hop self, and likewise we can go to router number 4 as well, and then we can tell router BGP 100 neighbor is next hop self. Now if you go here and check show IP BGP, you'll see that next hop will get changed. Otherwise I'll force this BGP to converge. Here you can see at least next hop is not get changed, but the priority, I can see that wait update has been done and it is going via the uh, bottom router. So here you can see that wait has done his effect, but it should change the next hop as well. And now you can see that they have changed the next hop. That's the correct actually. Wait has been changed, next hop has been changed. So this is the way, this is the use case with the wait. Now what we want here, that instead of wait, the same thing I want to do with the local preference. So first of all, I'll go to router BGP 100 and I'll remove this command. I don't want this wait, for example. So we don't need this wait, and next what we want, that we want to use the local preference. So for local preference, let's go and check the route map as well. Route map, because now for local preference I want to create one route map as well. Now this time I don't want to apply this policy to R2. Rather than I want to apply this policy to R3 and R4. So how the local preference is working, that they are much more intuitive than wait, and their attributes can flow inside the AS. That's the key we have. So what we can do here, first of all we'll see that how the 777 is getting reached to router number 2. Then here over router 3 I will set the local preference as 300, and router number 4 I'll set the local preference as 150, because I want that it should go and prefer this direction. Or suppose what we can do, that I'll go and create one more network here. So for example 88888 as well. Already we have 7777. I'll create one more 8888. So 77777 for example should go in this direction, and 888888 should go in this direction. So how we can do that? Okay, so let's think that and let's try to perform that task. All right, so the target here is that 7 should go via router 3 and 8888 should go via router 4. So primary, secondary, secondary, primary, like that. So what I try to explain here, let me go and show you here. First of all, I go to router number 7 and I'll create one more loop back and I'll advertise that as well. So I can go here and create say loopback 8, IP address 88888, and then let's go to router BGP 200, and then we have the network 888 with the mask of 255. Now if I go here and check this same BGP route here, so now you can see that 8 is also coming and getting here. Now it is coming 3 and 3. So both the update, they are coming via router 3 that we don't want. For 7, so for example, I want that it should come via router 3, backup will be router 4, but 8 should come via 4 and 3. Okay, so primary, secondary, and secondary, primary, like that we want to use. What we can do here, that we can go to now to router number 3 and we can create the prefix list first. So I'll go and create IP prefix list, say loop 7777, sequence say 10, permit 777732, and then I want to create one more loop back because the deterministic criteria, I want to put some condition inside the route map. So I can go and create the network statements like this. Okay, so I have two different IP prefix list, and even I can copy and paste the same configuration to 4 as well, just to save our bandwidth. Alright, so once we are here, then we should go and create the route map. Say local pref, what I want to this route map. Say permit 10, match IP address, and that is the prefix list 777. For this, I want to set the local preference, say for example 8888. Okay, then I'll go to the other statement, that is say for example 20, and then I'll go and match the address, that is this guy here, and then I want to set the local preference a little less. So for example 88. Okay, and then I have another default route map like this. All right, so here you can see the strategy for 777. We have the higher local preference. Likewise, I'll go and I'll create one more route map here to router number 4, where I want to match the 888. So statement number 1, I'll go and match the IP address, that is 888, and then I'll set the local preference, say for example 9999, that is very high, and then I can go to the other statement where I want to match the address, that is this guy, and then I can set the local preference 99. So the idea behind this is that for one of the prefix list, say for example for 888, what is the local preference? Very high. And here for 888, what is the local preference? Very low. So just the condition for 7 we have high, uh, for 777 we have high local preference, for 8888 we have low local preference, here the reverse, correct? Now we should go and apply this to the neighbor. So let me see that who is the neighbor. It's the neighbor IP router BGP 100. My neighbor is this guy here, and then the route map is local preference in direction, correct? Now here also I can go and check router BGP 100. My neighbor is this guy, and the route map that we are going to use is the local pref is the name and then the inward direction. All right, now if I go here, so for 888 the 4444 should be the best path. So here you can see, now we can see clearly that they are losing the backup. So here you can see that now the routes are converging and they are getting set with the correct local preference. But still, if you want to clear the IP BGP star, you can go and do that, and then you can go and check show IP BGP. So it will take some time, but it will build the route, and clearly whatever our target was, we are able to achieve that target, correct? So this is the way that we can go and apply the local preference. In 3.3, we have to learn and understand about wireless technology, basics of wireless, the AP, how the APs are going to join the WLC or the control plane, how we can do and do the baseline troubleshooting. So let's just start with the basics of wireless. Now, wireless is very different than wired technology. We know that in wired technology, you have routers, you have switches, you have cables, modem, endpoint systems where you have the NIC card, you are connecting the interfaces, and this is the way that network infra built. Apart from that, wireless technology is free from media. That is not 100% true. Free from medium is still in wireless technology. You have air as a media, or you have some sort of transport, but not the physical transport. So maybe air, maybe wire. Inside wire also, the wireless waves can go from one place to other place, but that is again not the exact use case we have. We'll see later on in this course that we have different type of frequency range or different type of wavelength for different wireless frequency, and which particular range we are going to use in the LAN. So it's actually broad thing, and in that broad we are using one is small spectrum or one is small slice of that wavelength for our wireless networking or for our wireless use. So let's start with a very basic, and then slowly we'll add um, things in this. We'll add some more and more concept in this. So here you can see in the diagram that you have sender, you have receiver. That's the uh, normal way of communication. So if there is receiver, if there is sender, if they are connected, then only the communication will happen, correct? Now in case of wireless, here it is showing that you have a rope in between sender and receiver, but you have invisible media, say for example in wireless, but you have the waves. So for example, I'll use the term wave. So here you can see that you have the electric and magnetic field, In the diagram, you have E and M, and they are propagating inside the air. So air is the media where it is propagating. Now, if this wave is not constant, so suppose you start one pulse and stop, so that will not reach to the receiver. So that means your wave should be constant. So it should have constant height and down. So here you can see you have up and down, means the flow of the wave you should have to reach to the destination. So at this point of time, with this slide, you'll understand, okay, um, we have media air, and then we have the wave. That construction of wave is with electric and magnetic. So we have electromagnetic wave. Now again, you can see that you have one sender who will send, and then you have a receiver who will receive. So at this point of time, I assume that everyone knows that we have the access point. We know that you have access point nowadays in all the networks. So you have access point who will send the wireless say waves, and then you have, for example, you have laptop where you have the receiver, so he is receiving, and the access point who is sending. Okay, so in that the communication will happen. Your receiver should have capability to receive, and the sender, now the sender can send in all the direction. Later on we'll study about antennas and all, and we'll see that what what is the use case of the direction of sending the frequencies, or sending the wavelength, or sending the signals. Okay, so you have sender, you have receiver. All right, then what is frequency? Frequency is the up and down cycle in 1 second. Okay, so let me show you the definition. I have taken the definition as well. So here you can see that frequency, the number of times the signal makes one complete up and down cycle. So when you go up and down in 1 second, so suppose if you are making 4 up and down in 1 second, so that's 1 second, your frequency is 4 hertz. Now again, what is hertz? Obviously, Hertz, this is one of the scientists who has done research and developed, or given his thesis and paper related to electromagnetic wave, and wrote so many books. All right, so Hertz is the most commonly used frequency unit and is nothing other than 1 cycle per second. So now you are sending the wave. Remember, you have rope and you are sending. So you are sending the wave, and in 1 second, how many up and down you have? That is 1 hertz. And suppose if we have 1,000, or if we have tens of thousands, or hundreds of thousands, etc., or thousands of thousands, so that will be determined as a hertz, kilohertz, megahertz, and gigahertz. We are very much specific about gigahertz in our wireless LAN network, that will go and discuss. So now this is the thing I told you, that we have wide range of a spectrum. So we have cosmic rays, gamma rays, X-rays. We know that some of things are coming from sun. Some of the rays are spreaded in the space. Some of the rays we are using for medical healthcare as well. Ultraviolet light, microwaves. We know all these things. But what we are going to use, we are going to use, here you can see, in terms of gigahertz. So if you see the spectrum is starting from 0, I am focusing upon, or I'm focusing here, let me focus the spotlight, 1 gig to 10 gig. Okay, so 1 gig to 10 gig slice that we have. So in that we have 2.4 gig wireless and 5 gigahertz wireless, and then again you have the bands for that. So we are going to focus on these spectrum, and these frequency actually we are going to use inside our wireless network. Okay, so for example, for 5 gigahertz, you can see it's starting with 515 and going to 5.825. Remember, this is in gigahertz. Now if you convert this into mega, so that means that 100,000 megahertz. And let's make this easy. So say for example, you have 10 then 10.3, then 10.6, and let me make this as 10.9 if I'm not wrong. So 10.6 is your mega, 10.3 is your kilo. So this is your kilo, this is your mega, and this is your gigahertz. Okay. Now suppose this is the range you have. So for example, 5.15 to 5.250. So what is the difference? So difference is actually 100.100 gigahertz. And now if you convert this into meg, so what will happen? Maybe 1 megahertz, because then you have to multiply this with 1, 2, and 3. So that means I think 10 megahertz. 10 megahertz is 0.1 gigahertz, correct? All right. So that's the difference of 10 actually we have. So everywhere you will see that here you have 10 meg difference. Again, if you go and see this, so 0.100, 10 megahertz, etc., etc. Means that's the band we have. Let me show you in the next slide. We have some examples related to that. So here you can see that all the spectrum range that it is shown here, and the same thing, there's a difference in between the spectrum, and that is defined as a channel. So suppose for this particular range, that is 2.4 gigahertz, starting with 2.412 gigahertz, reaching to 2.484 gigahertz, we have 14 channels. Now for one channel, what will be the difference? So this difference will be, say for example, 2.417, although it looks very small, but the value is big. 412, that is 500. This is in gigahertz. That means that you have 5 megahertz. So again, if you multiply with 1000, you will get 5 megahertz. Okay, so these are the calculation we should know. uh, Again, it's very much mathematical, and little bit physics is also involved. So what about the channels? Here you can see the channels and the difference in between that. Let's continue. So here you can see that you have 14 channel, and in between that gap is 5 megahertz. Now again, if you see the overlapping and non-overlapping channel, you'll find that there is one condition. So if the signal bandwidth less than, or it should be less than, the channel width. So here you can see the signal bandwidth and the channel width. If signal bandwidth is less, there is no overlapping. But if you can see that signal bandwidth is more than the channel, so in between 1, 2, 3, 4, you have a small channel width. So in that case, you have the overlapping. Okay, so these things should be considered. Again, what's the concept of phase? Phase means how much shift there in the actual cycle. So suppose in the first diagram you can see that there is 0% shift or 0 degree of shift. So that's why the two line is showing in parallel. But suppose if you have shift of 30 degree or 60 degree or 180 degree, then you can check the phase shift. Okay, so again, these are purely terms related to physics, some sort of electrical and magnetic signals. Again, we are studying in the networking. All right. So what are the terms that we are going to use more and more and more? So you will find that frequency, the hertz, then the wavelength, then the channel width, etc. So one of the key term we have is the wavelength. Now, what is the wavelength? Wavelength is the length for one cycle. So the wavelength measured of the physical distance that a wave travel over a complete cycle, and that will be represented by lambda. So lambda define the wavelength. For 2.4 gigahertz signal, the wavelength is 4.92 inch. For 5 gigahertz signal, the wavelength is 2.36. Okay. So again, this is the mathematical calculation, the length for one cycle. That's the wavelength. Likewise, how we are going to measure the power. So here you can see that RF power, and that is in dB, decibel. If you see the diagram, you'll find that the power is defined, or this amplitude is defined in between two um, peakest, two peak. One is in the positive direction, for example, one is in the negative direction. So the maximum length in between two peak, that will give you the amplitude. And this amplitude we are going to measure, or it will be measured in either watts or milliwatt. So again, you can see a new term, and terms are coming more and more. So when power is measured in watts or milliwatts, it is considered to be absolute measure. Again, we have one mathematical formula. We're going to discuss about that. But important thing here is that for wireless LAN, the power will lie in between 100 milliwatt to 1 milliwatt, and if you convert in watt, that is 1.1 watt to 0.001 watt. So better will go and measure in milliwatt. So power will be in between 100 to 1 milliwatt for wireless LAN. But for other services, you can see that for AM radio station broadcast, this is 50,000 watt. So you can see how much power it is. So for example, 16,000 watt for FM radio. This is huge power, correct? All right, so let's focus only on the LAN side, on the wireless LAN side, and let's try to understand the mathematics behind that. So suppose if we have three transmitter 1, 2, 3 in the diagram below, and you want to check the relative power between 1 to 3. So you can see now we have one mathematics. Better we'll go and check the mathematical formula. So what will be the power difference between T1, T2, T3? For that, it will be measured in decibel, and decibel is a mathematical formula in the logarithmic function. Now if you just completed your graduation in mathematics or BCA or maybe engineering, then it's very easy and convenient for you to check this formula in dB. So when we have say 10 base 10 P2 by P1, that means that this is 10 log 10 P2. Actually, divide means P2 minus P1. So you can think like this. It's not the exact say 10. I can take 10 as outside because 10 is common. So this means log 10 P2 minus log 10 P1. And suppose if we have some formula, so for example P1 into P2, so that means plus. That's the log function we have. Suppose if you have formula something like this, log P2 into P1, so that means we can take 10 outside. This means log 10 P2 plus log 10 P1. Okay, and absolute means that either it's a plus and minus, we are taking the magnitude of that or the module of that. All right, so now let's try to understand. I'll come back and resolve this, that if we have power 1 and power 10, so what will be the difference? Now we are not going to do the difference of power, rather than what we can do, that we'll go and measure the dB. Okay, so dB means so for example T2 by T1, and then you have log 10 and then you have 10. That means that will be 10 log 10 to the 10. That means this will be 1 as per mathematics. So the difference is 10. Okay, I'll come back to this. We'll discuss more on this later on after one or two slides. So let me go and complete the slides first. So then we have three different law for zero. Suppose if we have same power, so the relative power difference will be zero, because if for example 10 by 10 will give you 1, and log 10, um, this is the base, so 1 base 10 is 0. Suppose what is the law of 3? Suppose if we have a difference of 2, So if you are getting the value log 10 base 2, this, that will be 3 dB. And if you have 1 by 2, minus 3 dB. Okay, so what does it mean? It means suppose 10 by 5 and log 10, and again you have 10, that means you have 10 base 10, and this will be log 10 2 here. Finally it will come to 3 dB. This is again the formula. No need to mug up at this point of time, but if you want, you can take the reference. You can check any mathematical book related to uh, decibel. Okay, all right. So say what is happening actually here. So this, what at this point of time we can mark this thing that this value is 3. Okay, and 1 by 2 means minus, so this value will minus 3. Later in this same section, after one slide, I'll discuss more about that. Then we have law of 10. What does it mean? So if we have 10 base 10, that will be 1. Okay, so 1 into 10, obviously 10. 1 by 10 means minus, so then you have minus 10. Okay, great. So now we understand the law of 0, law of 3, and law of 10. Let's try to solve some of the questions. So here you can see, first of all, we have the summary table. So if difference is 2, then the power difference will be 3 dB. If it is 1 by 2, minus 3 into 10 plus 10 dB divided by 10 minus 10 dB. But again, what does it mean? So from this example, it will be 100% clear. So you can see in the bottom that A, B, and C, their power consumption in milliwatt, 4, 8, and 16. Now B is how much more than A plus? Okay, so let's try to understand. Now if you go and do B by A, you will find 8 by 4, that will be 2. As per the formula, we know that log 10 2 is 3 dB, correct? So that means B is equal to A plus 3 dB. Now what will be C? So C again, you can see 16 by 8, that means 2. C will be B plus 3 dB. And what is B? B is A plus 3 dB plus 3 dB. That means A plus 6 dB. Okay, so this is the way that we can go and calculate. Now you can think that, oh, it's a very easy example if I have some complex calculation. So for example, in this diagram, you can see that you have 5 and 200. Okay, so how I can resolve this 5 and 200? So what we can do in this, that you can go and check, sorry, you can go and check like 200 and divided by 5, so that will be how much? 40. Now this 40 will be, the calculation will be 2 into 2 into 10, correct? So 2 means 3 dB plus 3 dB plus 10 dB, correct? So that means that E equal to 6 plus 10, so E equal to D plus 16 dB. So little bit of mathematical calculation if you do, then you can go and check the relative power between two of the transmitters or two of the antenna. Alright, so these basic knowledge are required when we are going to learn some other wireless technology. So what is dB, what is hertz, what is amplitude, what is wavelength, etc. Alright, so we have three modulation technique that will come under 3 spectrum. So we have FHSS, frequency hopping spread spectrum. DSSS, direct sequence spread spectrum, and OFDM, orthogonal frequency division multiplexing. Now you can see that name itself is big, and we are going to discuss about exactly where they fit in the wireless LAN and which standard match which particular spectrum, correct? So if you go and check the technical detail, like the physics and the electronics behind that, you'll find that there are so many things to understand one spectrum. So behind the scene, it's a complex mathematical and physical structure. Uh, so those things we are taking inside our digital world, in our networking world, and we are using it. So let's see that what exactly we are using. Although everyone, most of the engineers are using wireless technology, but we are not aware that behind the scene which particular spectrum or the modulation technology we are using with which particular standard, IEEE standard. So first of all, we have the FHSS, that is the early ones, means with the evolution or with the beginning of wireless LAN technology, we have this methodology, we have this modulation technique, uh, we have this spectrum. So here you can see that it has a 79 channel, and you have problem as well, and we have some benefit as well. So what is the problem here? You can see that the frequency hopping will follow this rule. So channel 2 will move to 25, then 64, then 10, then 45, like that it will jump. Now here in the diagram you can see that first of all it is supporting 2.4 gigahertz spectrum, and then you can see in the diagram that 2, then it is going to 25, then 45, then 64, returning back to 10, and vice versa. Now what is the problem? The problem here is that they are limited to 1 or 2 mbps speed. Okay, that's one of the big problem, because nowadays we are looking for a speed, and this is one of the biggest problem. Now what is good thing is that whenever we are talking about first evolved technology, it's actually easy to set up and use, etc. Now all other technologies, modulation technologies, are also easy to set up and use, but behind the scene, the circuit, the chip, the coder, encoder, etc., it's a little bit complex, and because it is evolved from one technology to other technology. So what is the solution? So then we have the next approach, a spectrum approach, that is DSSS, direct sequence spread spectrum. uh, it can give you higher throughput. So for example, we have one summary slide by the end of this slide, so we'll see that. So it is going to give you, say for example, 11 mbps of speed. That is still not enough, correct? And this is also falling into 2.4 gigahertz band. So here you can see FHSS and DSSS, both are falling in the same spectrum band. Their speed, overall throughput is, although 11 mbps is good, but it's still, nowadays we are working in digital workplace and all, still it's less. The other disadvantage it has, that because their channels are overlapping, so they have only three non-overlapping channel 1, 6, and 11. Now what is the technology behind? So let's try to understand. Here you can see this technology, this diagram, that how the bits are coming, they are getting coded, means they are getting arranged, again they are getting packed inside the block, and then it is getting modulated, and then it is going outside as a signal. So how it is? So first of all, we have the scrambler. What it is doing, the data waiting to be sent in first scrambler, means whenever any request is coming, it's up to a scrambler. It will do some scrambling, and then how the data will go. Now next is the coder, and it's important what coder is doing, that they are converting data into multiple bits. So coder use is to convert the data, whatever it is coming from the scrambler. So here you can see that data bit is coming, and then coder is converting that data into multiple bits, each of new coded bits are called a chip. So here you can see in the diagram, uh, all these bits are called as a chip. Now here we have DSSS uses two encoding technology. So maybe somewhere you have seen this short form. We have Barker codes and we have complementary code keying, CCK. That's a coding methodology. Now next we have the interleaver. What interleaver is doing? Again, it's important that whatever input you are getting, so obviously the data bits that you are getting from coder, the interleaver will spread this into separate block. So you have data, then you have bit, and then you have block. Data, bit, block. Finally, we have the modulation. Once the modulation will happen, then it will flow in the air as a RF signal. Okay. Now, more or less, the DSSS and the next technology, that is the OFDM, both are using same technology behind the scene, but in OFDM, you can think that you have parallel processing. So suppose that DSSS or DSSS, that they have this modulation technique for one stream of data. Now, if you do 64 parallel processing, or for example 48 plus 4 parallel processing, obviously your overall throughput will increase. So now suppose if you have 11 Mbps, you can multiply 11 Mbps by, say for example, 52. So that much throughput you can get in terms of Mbps. So next technology we have, because we are looking for higher throughput and speed. So we have the OFDM modulation technique. What OFDM is doing, that it helps in parallel processing. That's the main thing. So here you can see that in contrast with OFDM sends data bits in parallel, that's the key, over multiple frequencies, all contained in a single 20 megahertz channel. Now there are technology, so they have guard for 12 subcategory, pilot for 4 subcategory, and data for 48 subcategory. Now guard will be there, but this pilot and 48 subcategory for data is going to be used, and you can think that you have that much parallel processing, or that much parallel signals in a row you have. So here you can see that you have 48 subcategory, and that's huge, correct? Great. So now sometimes you might see that OFDM, and again these are the theoretical things, having 52 subcategories, 48 for data and 4 for palette. This is because 12 guard frequencies are not actually transmitted, but they are silent in the channel spacing. So that's why we have the modulation for each data into 52 times. So you have 52 times subcategory. Now let me go and show in the diagram. So here you can see in the diagram that you have coded data, then you have 48 subcategory, and inside subcategory you can see, and then you have the channel. So you have 20 megahertz channel, and it is a spread across 48 subcategory. Now OFDM, obviously they have to use a scrambling, coding, interleaving and modulation, but for all subcategory, and that's why it's a parallel processing. So whatever we have studied in DSSS, the same thing is happening, say for example 48 times parallelly. Okay, we have IEEE standard. So let's see that what a standard we have. First of all, this 802.11 was introduced on 1997, and then after 2 years, 802.11b has been introduced. Here you can see that it is supporting 2.4 gigahertz band. The modulation is DSSS, and the data rate support is up to 11 Mbps. Now, 11 Mbps is not a big speed nowadays in the digital world, so that's why we need some higher throughput. So next we have 802.11g, where they are also in the band of 2.4 gigahertz, but here you can see that the data rate start from 6 mbps going to 54 mbps, so it is giving much more throughput with compared to 802.11b was introduced in 2003. Now still the problem here in this 802.11g, here you can see that although you have the bands, different bands, so we have a note here that G and B use complete different transmission types. One is using DSSS, one is using OFDM, and these technical details we have discussed in the previous section. So that means the devices who are supporting these transmission types, they will not communicate because they have the different communication channel. They have different signals. Okay, and the other thing that they have very less non-overlapping channel as well. So that's why we have 802.11a, although this will also support 54 mbps, but it is using different channel. It is using actually different band, 5 gigahertz band, but it has long range of non-overlapping channels. So here you can see that band is different for 802.11a, that is 5 gig band, and they speed from 6 mbps up to 54 mbps. Now at this point of time, still we can see that 54 mbps is not that digital workplace actually looking for, because now we have say 100 of mbps of LAN speed. We need fast throughput. We have different type of devices in the workplace. We have IoT based devices. We have so many mobile devices. We need fast speed. So that's the evolution or the introduction of 802.11n, that is supporting 600 mbps. That is the theoretical maximum, but it is supporting a huge bandwidth. The data rate is huge, and they also have very much non-overlapping channels. The good thing about 802.11n is that here you can see in the summary that they are supporting both the band 2.4 and 5. So in this list, you can see that 1997 we have 802.11, where we have both DSSS and FHSS. We have a study about this in our previous section. The speed was 2 Mbps. After 2 year, 11.B came into the picture, whose modulation is D triple S, which is supporting 11 Mbps. Then we have 11A, which is using OFDM, 54 Mbps, but you can see the band is different. So 11A and 11G, you can see the band is different, but they can have the same modulation technique, and their overall throughput is 54 Mbps. Now again in 2009 we have 802.11n, where they are supporting both the bands. Their bandwidth, you can see their modulation is OFDM, but the throughput can be theoretically 600 Mbps. All right, so let's just stop here. Next topic we have interference and effect of physical object. Now interference is nothing but the noise, and this noise, that means that you are sending some signal and it has some overlap. Now here you can see that overlap maybe with the same channel, so different transmitter having same channel and they are overlapping. Now in real world, this co-channel interference is often a necessary evil. It's too bad, means your signal will get degraded as much as. So we should plan it. We should put the access point in a proper manner, so there should be less interference or no interference. Now that's the one thing. So here you can see that two nearby transmitters should never be placed in the same channel, because their strong signal would be more likely to interface. That's the one case. The second case we have that if we have the neighboring channel interference, so what is happening that now I have transmitter A with channel 6 and transmitter B with channel 7, and they have the overlap. Even in the 5 gigahertz band, still we know that it has long list of channels, means it has so many different channels that the way or the chances that they can overlap is less. Still, the best practice suggests that you should avoid placing a neighboring access point on nearby, even it is a 5 gigahertz. So if you think that is still there is chance of doing the interference, but still we should plan the placement of the access point in a way that they should not object or interference the signal of each neighboring access point or the channels or bands. All right. Next topic we have the effect of physical object. So what is happening? Say you place your access point and then it is in contact with a surface who is reflecting the wave. It's very much like light. We know that how the light wave are reacting. If you put light wave in front of mirror and if you put that in a certain angle, it will reflect. Even if your surface is smooth, in that case, the RF signals will also reflected or get reflect. Now, you can see in this diagram that, okay, there may be chance that the receiver is MIMO, multiple input, multiple output. So here you can see in the diagram that the sender is sending the signal with three different direction, and receiver, because he know that how to get from the multipath, he can get it. Still this situation is okay, but suppose if you have single uh, radio chain, or the receiver has only single radio chain capability, means they can take the signal just from one source. So in that case it will become worse. Obviously you can see the signal will get degraded, say in case of A and C, if we have one A B C, like that. Okay, so second thing we have the absorption. What will happen in absorption is that the signal will get reduced. So you have some dense media, and behind that dense media you have put your access point. So in that case the signal will get reduced. We should not place our access point in a way that it will get reduced. Then we have the scattering. If you have some sharp surface, so at that point of time, if the signal will land, it will get reflected. Obviously the distortion of the signal will be there. Then we have refraction. Refraction means that again your signal will get distracted. The actual physical meaning, or if you go and check the physics book, you'll find that when RF signal meet the boundary between media of two different density. So if one place you have higher density, other place you have some lower density. Say for example, air and water. So air has low density, water has higher density, and if the signal will travel on those media, obviously it will get refracted. Okay, so these are the evils we have here. You can see that you have reflection, you have absorption, you have a scattering, refraction, and then finally we have the diffraction as well. So suppose on a line of signal, if you have some opaque or if you have some void in between that, so in that case the signal will get distorted, it will get refracted, diffracted. So suppose an RF signal approaches an opaque object, or one that is able to absorb the energy. So that's the case, you have the diffraction. Obviously, the signal will get degraded. One of the important concepts we have in this is the Fresnel zone. What is this zone? Before going to that, you can see one of the example of diffraction, that you have the obstacle, you're sending the media, you're sending the frequency, the waves, and you have the media in between who is diffracting the signals. Obviously the signal is getting diffracted, that's the one thing. So what is the solution for that? That you can use line of sight wireless signal. So two big towers, in between that there is nothing. So there is nothing means there is no object or uh, abstraction in between that. So here you can see you don't have big tower in between that, in between two buildings. So your signal can transmit it from here, receive from here. That is one of the solution. But again, what Fresnel law is telling is, according to Fresnel, the rule is even narrow line of sight signal can be affected by diffraction even if an object does not directly block the signal. There is elliptical shaped volume around the line of sight that must also remain free of obstruction. So what is mean? and that's called the Franzen. You can see here that I have transmitter and receiver in the diagram, but when you send the light, or when you send the signal, not light but our radio frequency signal, so when you send the radio waves, at that time what will happen, that it will create some sort of cylindrical volume across it, because still you have air in between, still you have the gravitational force, still you have some invisible, you can say, abstraction in between that. Maybe in some places we have um, so much pollution, so maybe the heavy particle they can um, collide, and there are so many factors for that. So in that case what will happen, they will form this cylindrical type of structure. In between that again you can see that you have a small building in between that, so it still is going to degrade the quality of signal. Okay, and then you can see that this curve is showing that you should not have the anything, any abstraction in this curve, and that's again coming from one of the formula. Okay, so these are the things related to the interference and related to the objects, physical objects in between. And again, if you go and check more and more about the reflection, refraction, absorption, and all these things, very much taken from the physics. We have learned a lot in our maybe 12th or in our graduation about all these theorems and theory related to various diffraction and the transmission of signals. All right, so let's stop here. Next basic topic we have is the antenna and type of antennas. So let's understand about antennas as well. Now here you can see that we have different type of antenna, and actually different type of requirement is there, and that's why we have different type of antenna. So sometimes we need focused beam, sometimes we need smooth and surrounded or equal spaced RF frequencies or beam. Sometimes we want long range radio frequencies. Sometimes we need short range radio frequencies that will be inside the room. So that's the main reason you can see here that we have different type of antennas, because the requirements are also different. According to that, we'll go and check that what type of antennas are available and what is the frequency range they are available with. Before that, let's try to understand few of the basic things. So first of all, here you can see that we have the isotropic antenna, uh, where we have, say, example, here in the diagram you can see that you have x, y, and z direction. So at this point of time, suppose if I have two section, one section I have in x direction, that is the horizontal, and one section is in, say for example, y direction, x and y direction is vertical. And suppose the requirement is that I need equi-space type of radio frequency. So what does it mean? That it simply means that you put the access point in the center, and then from that access point going forward in a circular manner, you have the radio frequencies. So whatever object that is coming in that circular radius in that particular premises, they will get the radio frequency equally. That's the whole idea behind that about the isotropic antennas. But the problem here is that to make isotropic antennas, and that isotropic antenna will fit with all the requirement, is actually not possible. So that's the reason we have different types of antenna categories. Now here you can see in the diagram that you have horizontal direction, that is azimuthal, and then we have the elevation plane as well, that is the E plane. So we have two plane basically, H plane and E plane. And according to that, if you go and do the cross section, so if you go and do the section here in the diagram bottom, let me try to highlight. So here you can see that how the frequencies in terms of dB, that is increasing as we are going outside to the circle. So here you can see that the outermost circle usually represents the strongest signal strength, and the inner circle represents weaker signal strength because they are in the minus. So minus 30 is less than minus 5. Minus 5 is obviously bigger than minus 10, and etc. Correct? So outer circles representing higher signal, and that's one of the important point that we should know. So now we understand about the isotropic antenna, and that's actually not possible to build. We have different type of antennas. Then we have the azimuthal and the E-plane. Then we know this point that okay, while going forward, your signal strength will increase as per this section, as per E and H or E section. Then what is gain? Now gain is nothing but it's the um, focus. So suppose if you have antenna, and that antenna, what is the focus, what is the focal, so that's the gain. So again, what does it mean? It simply mean you can think like this. We know at this point of time that we have seen the antennas. If suppose if you have parabolic antenna and then in center you have the central knob, or you have the center in between, means you are focused on something. So your frequency where you are putting the focus on, that's actually termed as a gain, and we'll see that different antenna what gain, what capability they have. Okay, all right, so here you can see in the diagram that different type of antenna, either isotropic, omnidirectional, directional. You can see the gain because the focus is changing, and that's why the gain of the antenna is changing. Again, the new term we have is the beam width. So what is the beam width? Many manufacturer list the beam width of antenna as a measure of antenna focus. Okay, so again, two term. Gain is a measure of how effectively it can focus RF energy in a certain direction. So that's the gain. You focus in certain direction or your energy in certain direction, and then the beam width. Beam width is nothing but the focus. So your focus and energy in that particular focus. So your focus is your beam width, and energy RF signal in that particular focus is nothing but the gain. All right, so understanding these many terms, now what we can do that now we can understand the types of antenna. We know that we have the polarization, so that electromagnetic wave is nothing but the polarization. Earlier we have discussed that we have the electromagnetic wave and the magnetic wave. So we have electromagnetic wave, magnetic wave, they are in the 90 direction. So in between, the angle between these waves is 90 degree. All right, so knowing these many facts, now what we can do, we can go and learn about the antenna. Again, if the electromagnetic wave is in the horizontal direction, that is horizontal polarization. If it is in the vertical direction, that will be the vertical polarization. Okay, and that is shown here in the diagram. So if vertically, if signal is going vertically, you can see the signal received, this is vertical direction, or it can be in horizontal direction. Great, so now let's focus on antenna. We have two types of antenna. I will see that subcategories inside these types. So we have omnidirectional and the directional. Now omnidirectional, as name suggests, that it will be equidistance, correct? So let me quickly show you one of the example for omnidirectional, that is the dipole antenna. Dipole antenna, again you can see in the diagram that from the center they are in the equal distance, and their gain is around, again we know what is the gain, so the gain is around plus 2 to 5 dB. Okay, again you can see the E and H, the horizontal is azimuthal and the E elevation plane, and the cross section here in the diagram. Now again in omnidirectional, so here you can see that omnidirectional, one example for that is a dipole, and again in omnidirection the other example is the monopole. Okay, one of the Cisco is a big vendor for the networking, and one of the AP inside Cisco, they have 6 tiny antennas 6 tiny monopole antennas in their access point. Uh, by the end of this section, we have this summary of whatever we are going to discuss here. So in the summary section, we'll learn more about that. Now, what is happening in the, say for example, in monopole antenna. So let me quickly show you the summary I have. So here you can see the summary. In omnidirectional, we have dipole, monopole, and integrated. Dipole, we have discussed that the gain is 2.2 up to 3.5. Monopole, you can see that 2.2, 2.2. So we have two spectrum, 2.4 and 5 gigahertz. Obviously, in 5 gigahertz, you will find much more signal strength. 2.4, you have less signal strength, but there are vendor made access point, maybe Cisco or any other vendor who is making this access point. Those access point, they are supporting both the standard 2.4 and 5 gigahertz. Okay. All right. So then you have the monopole. After that, we have the directional antenna. Why we have the directional antenna? Because in certain direction we need much more gain. So here you can see that we have the Cisco patch antenna, and the gain for that Cisco patch antenna is 6 to 8 dB. Okay, this is supporting 2.4 gigahertz. The gain is 6 to 8. In 5 gigahertz, they have 7 to 10 dB support. And here you can see the diagram. In this diagram, clearly you can see that focus is in one direction. Correct. If you go and see the other direction, you can see they are equidistant. Mostly they are equidistant. Say in case of omnidirectional, again if I go back, mostly they are equidistant. But if you go and check the directional antenna, you'll find that the focus is in one direction. So for this antenna, that is the patch antenna, you can see the gain. Next, we have the Yagi antenna. Again, the name of the inventor is the Yagi, so that's why this is the Yagi antenna. In Yagi, again, you can see this is very much focused on one direction, and the gain for these antennas are 10 to 14 for 2.4, and we can see the um, list as well. Cisco does not support or offer 5 gigahertz Yagi. Cisco is not supporting 5 gigahertz Yagi, so that's why it is not there for 5 gigahertz, but here you can see that's 10 to 14 for Yagi. And if I go and check the list, so you can see, so 5 gigahertz Cisco is not supporting, so it is not listed here. All right. Then finally, we have the parabolic dish antennas. Again, the gain will increase because the focus will increase in certain direction. So in this case, you can see the linear type of azimuthal and the elevation plane, the horizontal and the E plane, elevation plane. Now the focus, it's quite linear, but again you can see on other hand what gain we have. The gain is 20 to 30 dB, and that's a big. Now again in this summary slide, you can see the directional antenna, the parabolic, for 2.4 gig they have 20 to 30, and 5 gig also they have 20 to 30 gain in this range. Okay, so you can take this particular chart as a reference, and we have discussed about, first of all, the term used inside the antenna, like what is beam width, what is gain, what is polarization, what is azimuthal, what is E plane, etc., etc. Then we have gone through and checked the types of antenna. In omnidirection, we have dipole, monopole, integrated. In directional, we have patch, Yagi, and parabolic antennas. So what type of wireless network we have? Let's understand different type of wireless network, and then we'll focus on wireless LAN. So here in the diagram, you can see starting from a small WPAN, and then wireless LAN, then WMAN, and then WWAN as well. You have the personal area network. Example is Bluetooth. The distance is from 20 to 30 feet or 7 to 10 meters. Then we have wireless LAN that we are going to study in this particular course. That range is 100 meter, and we know that we have band 2.5 and 5 gigahertz band. Apart from that, we have the metropolitan area network as well. WiMAX is one of the example for that. Obviously, it is for wider range. And then we have the wide area wireless network as well. That is again is for broader area. Example is the mobile services, mobile towers, etc. Okay, so let us focus on wireless local area network. Now we know that we have transmitter, we have a receiver, correct? A transmitter, they are going to send their electromagnetic wave. Receiver, they have to be in the line to receive those signals. If in between there is any interference, any obstacle, any problem, any type of object, then the signal will be degraded, the frequency will be degraded, and the overall performance will be degraded, correct? Now we may have one-way communication, we may have two-way communication, and suppose if we have more number of devices in a group, in a particular wireless area, LAN group, then there is so much interference and the problem. So just to mitigate from this particular problem that we have, we need one central device that can work on behalf of all the devices, correct? And that central device name is access point. Now here in the diagram you can see that all the devices, all the wireless devices or endpoint, they are going to associate with access point. Now there are so many different terms and we should understand at this point of time. So in the diagram you can see that first of all you have one circle, and that circle is nothing but the so for example this point of time this is the uh, wireless area. Like in OSPF, you have area. At this point of time, just think that this is one of the area set. This is one of the area. For example, area 0. Inside area 0, you have different endpoints and you have the AP. So this AP, the BSSID is nothing but the MAC address of the access point. And obviously MAC addresses are unique for the physical devices. So the physical ID that this device has is the BSSID. Here you can see that you have the basic service set. So complete area 0, you can think that the standard inside complete area 0 is basic service set. So we have the basic service set, we have the access point, we have BSSID. Now what is happening and what is important here is, like routers, what routers are doing, they are advertising their network. Same way, what access point will do, he will advertise his network, and his network identification is nothing but SSID. So SSID, he is advertising, whoever endpoint will associate that particular SSID, that will be become part of that group, part of that set, correct? And that's actually the truth. So here you can see that you have the basic service set BSS. Inside BSS you have the BSS ID, that's the API ID, and this API is advertising its network, and all the endpoints, they are going and connecting with that particular network. Okay, and that network is nothing but the service set identifier. Again, the endpoints, that's the member, they will go and associate with that particular network. Obviously they will do some sort of negotiation in between that, and then they have to associate with that particular network. Now from AP, if you want to do some sort of access control, that we can do. So here in the diagram you can see that certain group of devices can communicate, or certain members can communicate to each other, certain members will not communicate with each other. Later on we'll discuss more about the packet type and communication, etc. All right, so far we understand that what is AP, what is members, what is SSID, what is BSSID, what is BSS. Now very important thing here is that for each and every wireless network, you should have the core, and that core is nothing but wired network. So behind every wireless network, we have the backbone wired network. And that backbone wired network is termed as a distribution system, DS. So here you can see in the diagram that you have DS, and again behind that you have router, switches, firewall, etc., etc. So how the connection is? We have BSS that is connecting with DS, that may be any L2 or L3 switch. And suppose if we have multiple VLANs, so suppose one VLAN representing one of the SSID, other VLAN representing other SSID, or maybe you have multiple VLANs across your SSID. Depends upon what design you have. Now in that case also, the BSS and DS should have trunk link in between that. So we know this concept from our VLAN concept, that if you have multiple VLAN, so there should be trunk in between to allow those VLAN frames. Okay, so that's the concept of DS and the connection with BSS. Now the next concept we have is the extended service set. So what does it mean? Now if you see the diagram, you'll understand. So for example, you have two BSS, BSS1, obviously BSS means BSS having BSS ID. So that means they have their unique MAC addresses. Uh, in very easy term, that you have two different access point, and these access point having same network. So their network is nothing but SSID, SSID. So SSID is same, and they are connected with the DS, distribution system, or a switch. So now the BSS, so collection of BSS, you can think as an extended service set. So BSS or N into BSS is equal to ESS, extended services. Now if I have one user here who is associating with one of the AP, and then he's going to the other AP, and he is associating with other AP, so at that time the concept is termed as a roaming. So user is roaming uh, across the network, but we can say that throughout you, it may have different AP, correct? You can see that it has different AP, but they are part of same network. So that concept is nothing but the roaming. All right, so let's stop here. We have covered the basics of the wireless LAN so far. Next, we have 802.11 frame format. Although we know that how 802.3, that is the IEEE MAC based format, how it is working and how it look like. So here you can see that you have preamble, the source destination address, and then you have the data field plus FCS. Switch used to learn all these end host machines, and then depending that do we have L3 communication or L2 communication. For L3 communication, again, if you are crossing the boundary, then the router will come into the picture. But that's the way that the LAN and the broadcast network used to work. In wireless networking, the communication is very different. Why? Because we know that all these end system, first of all, they have to learn the SSID. SSID is nothing but the advertised network from the access point. So they have to learn and associate and authenticate this SSID. After that, they will start the communication. Because we have SSID into the picture, because we have different type of wireless client or different type of end systems, they are part of wireless network, and they can communicate to each other as well, or they can communicate to the machine that is behind the wireless. So wireless will connect with wire, and then wire is connected with some other host machine. So the bottom line is that you may have various mode of communication, and depending upon what type of communication you are doing, that's why we have different type of addresses. So here you can see that you have four different address 1 2 3 4. Then you have the duration ID. Why it is? Because this technology based upon congestion avoidance. See, the Ethernet LAN is something like collision detection, and this is actually a collision avoidance, not congestion, collision avoidance. Now, in case of collision avoidance, what is happening? That you wait, you have some timer, you have some back off algorithm, and you will see. So if it is clear to send, I will send. If the media path is not clear, I will wait till that particular point of time. So that's why it's the collision avoidance mechanism. Now here you can see that you may have end system. Uh, those are the wireless client where you are doing the communication, or you are doing the communication with the machine that is behind the behind this AP, that is in the wired. So wired versus wireless, and that's why we have this DS bit set. So either 0 or 1. So if you have 2 bit, then you can have 4 condition. Say a 0 1, a 0 0 0 1, 1 0, and 1 1. Now this 0 0 means that two hosts are doing the communication. They are purely part of wireless network. Now this 1 0, you can see that you are doing the communication from wireless to wired network. Then you have this 0 1, that means the bits are coming, the frame is coming from host from the wired network to the wireless. And finally, if you have access point A and access point B, and if they have some communication, that will be 1 1. Okay, so let's try to understand what about these so many addresses types. Yes, we have 4 different type of address type. Here you can see that first of all, they must have TA, transmitter address and receiver address. Now this address one field always contains RA, that is receive address, though its exact contents may vary depending on where the frame is headed. Likewise, address 2 is always contains TA. So two addresses fixed, address 1 is receive, address 2 is transmit. Correct. Apart from that, obviously when you are sending the frame, then you should have the actual source address, you should have the actual destination address, etc. So let me try to explain this in a diagram. Here in the diagram you can see, and we are going to understand all the address types, address 1 2 3 and 4. Remember, in this diagram I don't have AP to AP communication, so that's why address 4 is blank. Okay. Now we have one case that host 1 wants to communicate to host 2. So what will be the source and what will be the destination? So here you can see the source address is uh, the transmission address is this, and the destination address is this. So actual source, actual destination. Now who is the receiver? At this point of time, the access point is the receiver, so that's why his MAC address. Okay, so clearly you can see first of all the addresses, and second the bits. So since you are sending 1 to 0 means wireless to wired, so that's why you can see here that this is going to hit. Okay, and here you can see the address 1 is BSSID, address 2 is the TA, and then the address 3 is the destination. Okay, now then the host 2 will respond. When host 2 will respond, then source and destination address will get changed. So now who is the source? He is the source. Who is the destination? This guy is destination with respect to host 2. Now what about the MAC address of the BSSID or the AP? That will be the transmit address. So he has received the address and then he is transmitting. You can think the logic like this. That is the transmit address, rest the receive address and the source address, they are going to be changed. Now which is the use case? This one. So here you can see address 1 is RA, who is going to receive. Address 2 is BSSID, who is going to transmit, and the address 3 is the source address. Correct. And who is the source? So this guy is the source. Although this is a bit of tricky, so you can pause the recording, you can take snapshot, and you can do your mapping, but this is the way that the frame format look like, and the fields inside the frame format representing these addresses and these DS bits. Let us understand the 802.11 frame types. As we know that we have three different type of plane, normally in SD-WAN also or in routers also. So we have the control plane. We have, as you can think that for frames also we have management frame, control frame, and data frame. Now, what is the use of management frame and why it is important? So let's try to understand all these options that we have. First of all, starting with management frame. Now, this management frame is there to advertise the BSS and its capability to the clients. Now, what are those? So first of all, you can see that you have beacon, and beacon is something that will be sent via the AP. At this point of time, you can think that okay, beacon AP is sending the beacon to all of the clients, and if client will go and open and check their wireless network, they can receive those beacons. Now it's up to client that they want to join or not. Correct. So if I go to my laptop and if I go and check my wireless connectivity, I can see a range of SSID or BSSID. Generally, those are SSID, not BSSID, but I can see all those SSID. SSIDs are nothing but the network advertised by the AP or the wireless network. So that's nothing but the beacon. That's the one of the management frame. Then probe. What is probe? Probe is something, suppose you want to join to the AP and then you are sending the request to the AP that AP I want to join. That will be the probe, and that's why this is the passive. So beacon is a passive scanning and probe is active scanning. Okay. Next we have the authentication and deauthentication. Now in wireless networking, we have this authentication option that the clients can authenticate with the AP, and even they can do the de-authentication as well. So the first stage you can see on your laptop that oh, you can see n number of SSID or so many SSID. Now next thing, if you go and click there, it will ask you some password. What is the password? If you put that correct password, it will get authenticated. If you do not put, it will not get authenticated. Correct. So those frames are actually the management frame. Then we have important terms: association, de-association, re-association. So suppose once you are able to discover the network, then you are able to do the authentication, then you are going to do the association with the AP. Now, in this association phase, the access point, they are sending a unique association identifier, AID, to the clients who are going to do the association. Suppose if you want to leave, you can do the de-association. If you want to change one AP to other AP, you can do the re-association. So different terms are there related to association. Now we have the action frame as well. Suppose you want to roam or you want to extend the wireless capabilities. So at that time, this action frame will come into the picture. So here you can see that you have this management frame. Then we have the control frames. Although there are 9 control frames, but these 4 are important. So control frame are again, it's not the payload, it's not the data. It's the control mechanism. Uh, so for every frame, we are getting the acknowledgements, and that will provide you. So for example, reliability in the channel, we are getting the acknowledgement for block of data as well. Okay. Then we have this power save poll. So what does it mean? That a frame sent from client to AP to request the next frame that was buffered while client's radio was power on is something like a power saving mode. Then finally, and the important one, we have the RTS and CTS. RTS and CTS is something like a timer. So it's something like request to send or clear to send. These are the terms. And why these terms are become important? Because request to send and clear to send RTS, CTS, They are not only providing the timer to send the frames, but they are used for collision avoidance as well. Okay, so the RTS CTS are a mechanism to do some sort of collision avoidance in the channel as well. So finally, once you have your management done, once your control done, the next thing is to send or receive the data. For that reason, the data frame will come into the picture. At this point of time, we know from our previous lessons that we have four different type of address field. So the source address, the destination address, the AP address, and then you have the destination behind the wireless, that is in the wired network. So you have these four addresses, and then the actual communication of data can be happen. Let's understand the client scans for AP and roaming feature. We have already discussed about beacon and probe. We know what does it mean by passive scan. So passive scan means the access point. Here you can see that they are sending their beacon to the host with some time duration, that they are offering their network to the host. Now it's up to host that he can go select that network and then do the authentication and association. That's the passive scan. Now, this passive scan is good, but still the drawback there is that the host, they have to wait for certain time duration to get the network or to get the advertised network from the access point. Next, we have the active scan, in that the client itself is sending the probe, and he's asking that, say, who has this network, and then the access point, they are responding, okay, I am there. You want to authenticate, you want to associate. If you associate, you will get the unique association ID, AID. Now how the host will go and join a particular AP. So here you can see that we have several steps. Step number 1 to 5. That's first of all, the host will do the authentication request. Then he will get the response. Then he will do the association request. He will get the association response and unique AID, association identifier. And then finally he will go and join that. Okay, and all these steps are listed here. So for example, uh, point number 5 is the response also contains the AID that uniquely identify host 1 as an associated client in effect to AID is host membership, etc. So these are the steps: authentication, obviously request response, association, request response, and then finally they will get the unique AID. Now, if a host or client want to leave it, so he can do the deassociation. Remember here that deauthentication and deassociation are different things. So if you are deassociating, doesn't means that you're deauthenticating or you have to authenticate again next time. You can be deassociated, but you're still authenticated. Correct? Now, next very important topic is roaming. So far, we have studied that suppose if you are moving from one BSS or one area cell to other area cell, that means you are roaming. And suppose different AP having same SSID, so you can roam from one place to other place as per the signal capability. You will go and get the you will go and associate the access point. That's the technical term, association. Now here you can see all the listed steps what is happening in the roaming. First of all, say your signal strength is getting weak, your signal to noise ratio is getting weak, it's time to roam. If you are not getting proper signal, here you can see the client is there on the edge and he's away from the AP, but he's near to the other AP, or if you roam, he can get near to the AP and you want to go and associate with a new uh, high bandwidth, or he want to get some high frequency signals. So that's why he want to roam and go to the other SSID. Now in this case, what is happening, that the client will send the probe. Now he will get the probe response. Then here you can see that the association request will initiate. Okay, association request will get initiate, and I want to highlight this point number 5 here, and it's important here. Now, in this case, when two device, in this case, when client is doing the uh, roaming across the AP or across the wireless network, so at that time, point number 5 is important. So whatever buffer, whatever information that AP1 has, he will go and pass the information to AP2, and then he will use the DS, distribution system. He will go and use the wired media to bypass or to relay the buffer information, and then finally this client number 1 will get associated with AP2. Okay, so you can see all these steps. uh, if you have single access point, we know what are the steps. You will do the authentication, means you will do authentication request response, association request response, and you will be the part of the network or SSID. In case of roaming, when you are getting some issues, you roamed, then you do the probing, and then again you will do the association. Then this APs, they will sync their buffer data, and finally you will be the part of the new access point network, correct? All right, let's try to understand this wireless architecture. Inside wireless architecture, you'll find that we have several type of architecture, and what is suitable for enterprise level we can discuss. We have some popular one like cloud-based architecture or split mac. So let's understand all different type of architecture. So first of all, here you can see in the diagram that we have autonomous architecture. Autonomous architecture means that you have access point that is working independently. Okay, so here in the diagram you can see that you have access point connected with the distribution system or connected with the switch. The problem with this design is that although you can manage the SSID, but suppose for all these access point, you have to manage their own management IP. So there is no central authority from where you can manage the common work, or you can manage the common security framework. You can manage the management IPs, etc. So if the network will grow in this case, in this fashion, you'll find that it's difficult to manage, and it's not a good design for a big enterprise network, or even when your AP's number of AP will grow more than, say, for example, 30 to 75 or 100 or 200, etc. It is okay, although for very small type of infrastructure where you have less number of endpoints, where you don't want any third party or any controller type of device that can manage all these access point. So for that reason, it's okay. So this is the first, that is the autonomous architecture. And then next, to reduce the complexity, we have cloud based architecture. One of the popular cloud based architecture we have is Cisco Meraki, where you have the cloud hosted controller, and then you have your Meraki based access point situated in the branches in the LAN area network, etc. So here you can see that you are responsible, means the APs are responsible for the data plane traffic, but they are getting all the control information from the dashboard that is hosted in the cloud, or we have the cloud hosted control plane. Although the good thing about this, that manageability is easy, we can easily manage our infrastructure. Even from one single place we can go and log in and check various reports, various configuration, etc., from one central place. That's the key we have with the cloud hosted control plane. Again, when we are talking about cloud based controller, we have the control plane hosted in the cloud, and with the control plane we can do various operation, like we can configure, manage, monitor, create the reports. Even we have some visual representation. We can do the troubleshooting as well. So we have long lists that we can do from the control plane. And again, the data plane is there that is responsible to pass the data. Okay. So now you can see that we have autonomous architecture that evolved to cloud-based architecture. And finally, that is our interest for this particular course, is the split MAC architecture, where we have the wireless LAN controller, WLC. Okay, so now here in the diagram you can see that you have two access point. One is the autonomous, that evolved from autonomous architecture, and then we have lightweight access point where they have given their brain to the central location, that is the WLC. So from WLC, what are the things we can do? We can go and we can do the RF management. We have the association and roaming management, client authentication, security management, QoS, etc. There are so many things that you can go and check from the WLC, and you can manage n number of access point or the data plane devices. Again, it depends that which version of WLC controller or LAN controller we are using. According to that capability, we can manage the number of lightweight access point. Now, what data plan device is doing? That they are doing the RF transmit, receive, MAC management, encryption, etc. So now I have one comparison chart. Here you can see that autonomous WLAN and lightweight. Autonomous, just name suggests that they are autonomous access point, configuration of each access point, independent operation, managed via Cisco Works, WLSE, WDS, access point redundancy. These are the independent things. Then managed from the WLC. So they are the lightweight access point configured via Cisco LAN controllers, dependent on Cisco LAN controller, management via Cisco WLC, Cisco wireless LAN controller redundancy. So in this case, in this architecture, we may have primary, secondary, tertiary WLC as per the failure scenario. All right. So here you can see that in this case, the APs, we are telling them as a lightweight access point, and they have to go and register with the central authority, that is the WLC. Now, still the question arises that how? How the lightweight access point will go and registered with WLC? What about the traffic? How the traffic will move uh, from one client to other client in case both are registered with WLC? So all those things and the protocol between the LAP and the WLC, we will go and discuss in the next recording. We have discussed that the access point and the controller, they have to communicate. So how they are going to communicate is, so they are going to build the CAP WAP tunnel. Now you can see the full form of CAP WAP is control and provisioning of wireless access points, and there are so many RFCs that you can go and refer. So here you can see that CAP WAP is defined in these RFC 54151617 and 18, where you can go and learn more about this CAP WAP tunnel. So let's read this as a CAP WAP as a short, but you can see the full form as well. Now, when the lightweight access point and the WLC, they are forming the tunnel in between. At that time, we have two different type of tunnel. We have tunnel for control messages or control plane, and then we have the tunnel for data plane as well. Now, if you correlate this with the SD-WAN, and we are thinking now that now we are using SDN and SD-WAN and SD-LAN solution, but this WLC is quite a bit old technology which is using the concept of SDN. Even for example, Cisco Prime, then WLC and other mechanism also was there to manage the infrastructure. In terms of that, we have some central authority who is managing the infrastructure like SDN or SD-WAN, etc. If we go and learn more about the CAPBAP information, we'll find that, yeah, truly the tunnel that is building between the WLC and rest of the APs, they have exactly same type of certification process that we have, say, in case of vSmart, that's the control plane, and vEdge, that is the data plane device. So here you can see that CAPBAP, they are using UDP port number 5246. They are using secure authenticated DTLS tunnel, because we know, say in case of SD-WAN, we have both the option. Either we can use TCP or we can use UDP. Most of the other SD-WAN technology, they are using UDP-based IPsec tunnels or UDP-based tunnels. In our WLC, we are using UDP-based control tunnel and data tunnel. Now, for data tunnel, the DTLS is optional, means the secure tunnel is optional, means this at least the encryption is optional. If we want, we can use. If we want, we do not use. So here you can see that, but are not encrypted by default. So tunnel in between them. So tunnel is there, but the encryption is optional. If you want, you can use it. Now here you can see that we have two tunnel. We have the data tunnel, we have the control tunnel, and uh, in this manner, the access points, they will go and communicate the WLC. That's the one part. Now what will happen in this case? In this case, uh, behind the scene, what is happening? So these tunnels that you are seeing in between the WLC and the access point, they are using IP address. So that means they are IP based tunnels. Since they are IP based tunnels, so what they can do, and there are two things. First thing, that the VLAN. So whatever VLAN I have in the distribution system, obviously this WLC is connected with switch. So those VLANs information will get passed under the tunnel to the AP's access point, and these SSID information again will go and pass to the distribution system to the switches. Okay, so in that way the communication will happen. So you don't need trunk link here. So that's why you can see that I have the access link. So I don't need trunk link, and then I have to do encapsulation dot 1q, etc., etc. But that's the enhancement, because you're creating the tunnel. So obviously it will send and receive the packet depending upon the tunnel source and destination. In this case, the tunnel source and destination is the IP addresses of AP and the WLC. So suppose if you have more number of tunnels, in other words, you can think that if you have more number of access point, then you have more number of cap web tunnels, and then the communication will happen like this. So this is the communication channel that we have. Okay. So now once you have the WLC, so what are the role, what are the activity that WLC can do? So WLC can go and do the dynamic channel assignment, transmit power optimization, self-healing wireless coverage, flexible client roaming, dynamic client load balancing, RF monitoring, security parameters, QoS parameters, etc., etc. So whatnot means we can do n number of things from WLC, because that is the brain I have, that is the central mechanism to manage all the lightweight access points. Correct. Even you can see that we can do the wireless intrusion protection system as well. So this is the usability and use case of the cap web tunnel that we have, and this is the mechanism by which the WLC is talking to the access points. Let us continue our discussion and learn about the centralized wireless network architecture and Flex Connect architecture. Now we know at this point of time that that the WLC and the AP, they are going to have the cap web tunnel in between them, and then the communication will happen. Now before moving further, you can go and check the comparative chart from different type of WLCs that we have in Cisco. Uh, so for example, I have taken snapshot from one of the link from Cisco. Here we can clearly see that we have different type of WLC for different type of purpose. Although we have virtual controller as well, we have controller for ISR G2 starting from 2500 3650 5500 going to 8500 and 9. Now we have the 9800 WLCs as well. If we have more number of users, if we want to manage more number of lightweight access point, then obviously we have to move and we have to go to the higher end of WLCs. So it's just the evolution of WLC, how much clients we have, how much APs we have, what security feature, Flex Connect, QoS, etc. Depending upon that, we can go and choose one of the WLC for our organization. Now, once we are done with that, then we can go and deploy the WLC and we can connect the APs with WLC. That's the overall idea, and then the traffic will start flowing. Now we have this centralized solution that all these devices will go and connect or create the tunnel with WLC. Very much at this point of time, we can think that this is hub and a spoke type of topology, where you have your hub as WLC and then you have the spoke. So spokes, they are making the tunnel with the hub. Now there is one problem with this particular architecture. We'll discuss about that problem and the solution as well. Before coming to the problem, you can see that since you have your central authority to manage each and everything related to access points, so that's why the user identity means, again, the WLC is connected with the ICE and they are talking with each other related to users and profile and roaming profiles as well. Now, user identity or a user services or a user. So what are the user and its roaming capability? That can be managed from one place because everything is managed from one place. So that's the power we have. We have the centralized authority to manage each and everything. Next, in this diagram, you can see although the physical architecture, although the movement of data in the physical path is different. So here you can see that the actual movement of the data will be from switch 1 to 2 and 3. In short, that in between you may have a number of switches. On top of that, you have created the cap web tunnel. So again, you can see that from access point to the distribution system or the core layer switch, I have the cap web tunnel and then the traffic can go, but the physical movement or the data traffic movement via the link will be different. So that's one interesting thing we have, although we are not concerned about what are the configuration, what are the trunk VLAN passing to the intermediate devices, correct? Because those are, we can think that as transient devices. On top of that, I have my tunnel. So you can see that you have the benefit. Now what is the disadvantage? What disadvantage we have? Now if you see this diagram, you'll find that although I am local to this access point highlighted, so let me quickly highlight that. So I am local to this particular access point and I should not go to my hub and then I should come back, or I should not go to my central location and come back, although I can do this local movement of the traffic or movement of a traffic locally, right? So that's the problem we have, that if you do not give the local intelligence, so all the time the traffic will go, they will go and traverse this cap web tunnel, they will go to the central authority and then they will return back. Now, what's the solution? The solution is the Flex Connect wireless architecture. Now what will happen in Flex Connect, that we can understand from the diagram as well. So we have two type of architecture. First is the split MAC. Split MAC means you have your central authority WLC. You can go to WLC and come back. Again, you can see that you have cap web tunnel, and um, again the same thing you can see in the other diagram as well. So you can go to the WLC and then suppose if you have local printer to the switch system, you are going there. Although if you go and use the Flex Connect feature, what it will do, that it will give the device as a local intelligence. So what does it mean? It simply mean that for local transmission, you will not go and use the cap web tunnel, although you can go and directly use a printer, because to reach to this path, it's easy. Okay, so here you can see in the diagram that the traffic path during Flex Connect local switching, you are doing things locally. That's the power we have with the Flex Connect. We have a small tip here that Flex Connect was previously known as Hybrid Remote Edge Access Point, HRIP feature. To maintain connectivity between WLC and branch side LAP, the WAN link should have a round trip latency less than 300 millisecond for a normal data and less than 100 for the real-time traffic. Okay, so the idea behind is that when we are doing the Flex Connect architecture, so at that time we can do the local switching. Next, we have to learn about how we can implement the controller. Before that, we should understand that what type of interfaces and port available inside the WLC and what will be the connectivity from the WLC to the switches. We have four different type of port. We have service port, distribution system port, console port, redundancy port. Now the service port will be used for out of band management, system recovery, initial boot. This will always connect as a access port. So we are going to use this as a OOB, out of band management. Then we have the most important port, that is the distribution system port. We know this thing that distribution system port means that the WLC you are connecting with the switch. Now we have the capability, or we have the feature that we can do the aggregation. We can use link aggregation protocol, and we can group those interfaces and connect with the switch. Now these ports are always 802.1q because again we are going to pass multiple VLANs information via the WLC. Then we have the console port where we can connect the console port for recovery, initial boot, etc. And finally, in case we need multiple WLC for redundancy, for that we have the redundancy port. Now here in the diagram you can see that we have the distribution system. Obviously the WLC is connected with the uh, switch, and that's why you have the distribution port. We can have the link aggregation group. Service port is for outer band management. You have the console port, and if you want to have multiple WLC, so we can use the redundant port as well. Then from WLC to AP we have the CAP web tunnel, and then the information will go and get exchanged. Now these are the port, or these are one type of port we have. Again, we'll discuss more about other port analogy as well. At this point of time, we know that the AP and the WLC, they will go and form the CAP web tunnel, and the distribution port, they have the we should enable the 802.1q, and we should do the link aggregation protocol or link aggregation as well in between the WLC and the distribution switch. All right. So as per the model, you can see that which model have the distribution port and service port listed here in the table. Again, if we want if we have more number of APs, then we should go and check the higher end of the controller, and the capability increase, the throughput will increase, the overall performance will increase, but again the cost will also get increased. Now what is happening? So these are the ports we have. We have service port, distribution system, console, and the redundancy port. But internally, the controller must somehow map these ports to the equivalent logical port. So inside the controller, we have the equivalent logical port. So for example, we have the management interface. Now, what is use of management interface? Obviously, for the management related traffic like radius, authentication, WLC to WLC communication, web-based SSH session, SNMP, NTP, syslog, etc. Okay. Now, in this diagram, you'll find the clear picture about what we are talking. So here you can see that first we have the management interface, then we have the AP manager interface as well. We have the service port. We have discussed just now that service port will do OOB and various tasks related to service port. We have the dynamic interfaces as well. So what is happening here, that these VLANs that is coming from the switch side, they are going to map with the AP, and then again this AP somehow has to associate with the access points as well. This AP is the WLC. So let me again redo this. Switch will go and connect with the WLC, and WLC has a connectivity with the AP. In between WLC and AP, we have the cap web tunnel. All right, so what is the use of AP Manager interface? They are the dynamic interface used to terminate the cap web tunnel between the controller and AP. So here you're seeing this AP Manager, actually the use of this to terminate the cap web tunnel in between the AP and WLC. Then we have the virtual interfaces. Again, virtual interfaces are they have just the use case. So what use case these virtual interfaces have is that IP address facing wireless client. When the controller is relaying client DHCP requests, performing client web authentication and supporting client mobility. It is used in client mobility. It is used uh, in a way that the WLC can relay the DHCP information to the IP address facing wireless client. Okay. And again, this interface will be less of use, but yeah, we have the interface. Then we have service port interface. We have a study about this, that this is used for the out of band management. Then finally, you can see that you have the dynamic interfaces as well. These dynamic interfaces are, they have to connect VLAN to WLAN. That's the usability. Correct. So we have discussed about management interface. They are there for management traffic, different type of management traffic like HTTPS, SSH, SNMP, NTP, etc. And then you can see that management interface is actually important. So that's the one of the use. And then suppose the other use of this management interface is, say, in case of API manager interface is not available, so that performance or that task will be performed by the manager interface instead of. Okay, so that's the other use we have with the management interface. All right, so these are the interfaces. Here you can see that these are the ports, and here you can see that these are the interfaces we have in the WLC. So now let's stop here and let's go and do the initial setup. Next we have to perform the lab, and in this we are going to do the initial setup for WLC. I am using the virtual WLC here, and once you are in the first page, then you can give the username and the password, and then you click start. Once you go and click start, the next page that you will get, this will be like this. So let's do and complete this. I'll go and give the name, say for example virtual WLC 1, and the country I can go and select anyone. So let me go and select, say for example, any of the nearby countries, say for example, just an example and testing. So I can go and say select London. Then the time, I can see the time zone, and then I can go and give the NTP server. Then we can go and give the management IP. So that's the management IP in my case. Then the subnet mask for the management IP. Then the default gateway I have in my case. So that is say 19.1.1 or 11.1. Yep. Then the management VLAN ID. At this point of time, we can leave this as default. All right, so now we can go and click next. So I will go here and click next. Next, you can see that we have to create the wireless network, and then we have some of the advanced setting. Let me give the correct default gateway and click next. So what is the network name I have? So I can go and give cloud demo. Then what key? I'll leave this as default, but we have WPA personal and enterprise. Then the passphrase, I'll go and give the passphrase. Let me confirm that. Then what is the management VLAN? We'll leave this as management VLAN. If I have any DHCP server, I can go and give, and then we are very much done with this step. So now you can see that how easy is to do the setup. Now I will go next and we'll verify the advanced setting as well. So we'll go next. Here you can see the virtual IP address, the local mobility group, the service port interface, and these things we have discussed. Now the virtual IP address, it should be say some of the private address, because those private address will be used uh, locally. Suppose if I use any of the address which is not private, and that may be conflict, there may be chances to for the confliction. All right, so here you can see that we are giving the virtual IP address, and then the service port we are leaving this as default. Now let me scroll up if we have some other parameters. So here you can see you can go and uh, this is disable RF parameter optimization. You can go and enable it, and then you can see that client density low, typical high, traffic type is data. I can go and use at this point of time the traffic type is data only. All right, so here you can see that please confirm the setting and apply. So this is the setting that we have given: the management IP, the management gateway, the network name, security, passphrase, etc. So once we are okay with this particular summary, we can go and click next, and then we can go and apply as well. So this is the final page. Yes, okay, I want to apply this, and then we can wait. So once the setting apply, then we can go and log in with the management IP. So I logged in here with the management IP, and then you will get this first page. So now you can go and log in here. You can see the management IP 11.10, and then I can go and give the username and the password. So let me go and give username and password. Then we'll get the first page. So this is the first page that we have, and here you will see the monitoring rogues interface, wireless dashboard, etc., etc. uh, Interestingly, in this first page you'll find that we have the best practices as well. So suppose if you want to check the best practices, you can go and verify that in this page, in this first page, because we don't have any API association, we don't have any live traffic, so everything is showing blank. But if you go and click to advanced, you will get this page that we are very much familiar of. Generally, we are using this advanced tab to check each and everything related to the WLC. So in advanced page, you can see that you have the management IP, then you have the service port 00 software version, you can see 8.7, the name, the uptime, rest of the thing. Then the access point summary, you can see nothing is there, so that's why everything, all the counters are 0. But on the top, you can see that you have monitor WLAN. So suppose if you want to create WLANs, you have to go to this section, and then you have to create the wireless WLAN. Again, once you go and create there, then you will get multiple options related to the WLAN. We can go and check this later on. Then the information about the WLC. So here you can see the long list of information that we have, and you can go and click and check each and individual uh, tabs that you have. You have management interface, you have service port, you have virtual port. We have discussed about this, correct? And then we can go to the wireless. At the moment everything is blank. We can go and check the security. Again, you can see the long list of security we have. Management, then if you want to run any command, we have some of the command support that we have. So the page will look like this. Okay, so this is the initial setup for the WLC, and we should go and check the best practices that we have. So if we go and check the best practices, then we can see that what are the Cisco recommendations. So let me quickly show you that you can go and click on top home here. Once you go and click to the home, you'll go back to the first page that we have opened, and then here you can see the best practices. So best practices related to infrastructure security, RF management, Apple devices, ICE radius. Okay, and you can go and you can scroll and you can check all these best practices that we have. Okay, so this was the initial baseline setting that we have with the WLC. Let us understand that the discovery of the controllers. We have the document, and we'll understand with that document that what are the steps that AP is going to discover the controller, and then how the AP will go and select a certain WLC, that's the controller. So what is happening that we are going to boot the AP. So the first step is that you will go and boot the AP. So AP boot will happen, and obviously it will go and contact the DHCP server to get the IP. And suppose there are options that we can have the static IP assignment as well, but we have the option for DHCP server as well. Once it get the IP, then it will try to discover the WLC. Now for WLC discovery again, we will see this. I have separate slides for that in detail, that how WLC discovery happens. But the next step is that the AP will try to build the CapWeb tunnel with the WLC, and inside that CapWeb tunnel, obviously we have CapWeb control tunnel where we have the AP WLC control messages. Now the next step is that the AP will go and send the CapWeb join request. Now for that request, obviously the WLC will reply for CapWeb as a CapWeb join response. So once we have the CapWeb tunnel built between AP and controller, AP know who is the controller, controller know who is the AP, then it's the role of WLC that you will go and check the image version. So there should not be mismatch in the WLC image and the AP image. So in that case, the AP will go and download the image, and then again it has to reboot. Suppose if the image is okay, then from WLC, the config will get pushed related to RF, service set identifiers, security, QoS, etc. And finally, the device will go into the run state. Now here you can see all the steps that are listed from 1 to 7. Now in some occasions, due to some issue, that WLC wants to reset the AP. So in that case again, the AP will go and reset, and step number 1 will start. Okay, one point to note here, that while the APs they are downloading the image, it may take some time to download and upgrade the image, because downloading the image and then booting will take some time. All right, so what's the process for discovering the WLC? There are processes that AP may have knowledge of WLC, or with help of DHCP and DNS they are getting that information, or the WLC is in some other network, and then I have router in between who's relaying the information with help of broadcast. That's the broadcast on the local subnet. So for example, a broadcast on local subnet, what will happen? So suppose if your AP and WLC, they are in different subnet, then you have to go to the router in between, and you have to relay that information like IP forward protocol UDP 5246. This is the UDP port for CapWeb control tunnel. Then you have the interface VLAN, and you can go and give the IP helper address for different type of WLCs. Okay, so that's the one uh, option, or one way. The other thing, that inside your AP you may have the information of the WLC, and as per the primary, secondary, tertiary, the AP will go and check WLC1, then WLC2, then WLC3, and then they will go and contact or discover the WLC. We have option with DHCP. So once they are getting the IP address at that time, DHCP option 43 will be there to suggest the list of WLC addresses. It can use DNS as well to resolve capwap controller.local domain with the DNS request. Again, if nothing will happen, again the AP will go reset and it will start the discovery process. At this point of time, when we have the discovering of a WLC that is working well, so at that time we have selecting a WLC option also. So what does it mean? It means that AP will go and try for primary, secondary, tertiary, means as per the priority of WLC, they will go and join. The second thing is that suppose if they don't have any primary, if they are not able to discover any primary, secondary, tertiary, then they will go and check in the local subnet. So who is the master controller? According to that, they will go and choose one of the controller. And finally, they can go and check the least loaded controller as well. So as per the controllers and their connectivity, means the controller, how many APs are associated, they can go and select one of the WLC. All right, so these are the methods for discovering and joining process for AP and WLC. We have layer 2 and layer 3 roaming. So let's understand that. We have already discussed this earlier that when we are doing the roaming, say in case of autonomous AP, uh, the client here you can see in the diagram can go and connect with client 2 as per their signal strength. When the signal strength will go decreasing, then he can go and join the other available high strength SSID or the AP. That's the normal way that the roaming is happening. And the other important thing here is that in between that distribution system, that's the switch, he has the state information of this particular client, and then he can go and join. Now this is very normal, easy, standard process that the roaming will happen. Now the problem here is that we are not using this type of architecture in the enterprise network, because enterprise network we have n number of clients, we have n number of AP, we have good amount of WLCs, other controllers. So the methodology that we are using in the enterprise network is purely split MAC architecture. In case of split MAC architecture, what will happen? So let's try to understand that. We know that in split MAC architecture, the APs, they are going to form the CAPWAP tunnel with the WLC. And in that case, if a client want to roam, there are two options. First, that roaming can be layer 2, the roaming can be layer 3. So what will be the difference between that? And there may be chances that I don't have only one WLC. We may have multiple WLCs connected with wired network. So let's try to understand layer 2 roaming. What is the key feature about layer 2 roaming is that in that case, we are in the same subnet. We have the same big IP subnet. Inside that, I want to roam. So here you can see in the diagram that I have a user in 100.0 subnet, and he wants to roam from one AP to other AP. Obviously, you can see that these APs, they have CAPWAP tunnel with their WLC. Suppose I have two WLC and their connected network is wired switch network. Okay, so this is the use case. Now what will happen that when you roam, obviously from one place you have to deassociate, other place you have to associate. So you will go and associate. Now this roaming is quite good, scalable. Why? Because most of the things we are not changing here. So we are not changing, uh, and again it depends upon the use case. So if this is up to us that if we don't want to change the IP address of this client, so in the new when he is going to join the new AP, at that time also the same IP, and even the state information will be sync across WLC1 and WLC2. So in that case, we will get the seamless roaming type of capability, or the experience will be good because usually it will be less than 20 millisecond of the roam. Now the second option we have is the layer 3 roaming. Layer 3 roaming simply means that you are in two different domains. So suppose your exact IP is 100.0 and then you want to roam to 200.0. So you're crossing the subnet and then you want to roam. Again, the structure will be looking like the same, but the cap web tunnel you can see for AP1 and WLC1 and AP2 and WLC2, both are in different IP subnet. So what will happen now if this client want to move and he want to deassociate and associate with other AP, he can do it. But still, because the IP segment will change, here you have 100.0, here you have 200.0. So these WLCs, they are behind the scene forming the cap web tunnel over the switching system. So here you can see in the diagram that 100 is going to change into 200, and then finally they have the cap web tunnel in between that, just to exchange the state information of a client associated with AP1 with AP2. Correct. And you will find that naming of these WLCs are also different. So the initial client, when client is attached with one of the AP and he wants to roam, at that point of time that WLC is anchor, and where he is going and he's going to join the new AP associated with WLC, that will be the foreign controller. So from anchor, I am going to connect with the foreign controller, and then the roaming is happening as a L3 roaming. So here you can see with the help of diagram, it's easy to understand that how I'm connected with one AP and then I'm roaming, but again the state change is happening with help of cap web tunnel in case of L3 roaming. What are the steps we should do while doing the troubleshooting for WLAN? From where should we go and start the troubleshooting? Because we know that in troubleshooting we have either top to bottom or bottom to top approach. So both the things we can do. Now, when we are talking about, so for example, top to bottom, so obviously you are at the level of WLC, that's the top, and then you can go and check the cap web tunnel. You can go and check the access point, maybe access point related issue, maybe some physical issue, maybe memory, CPU, etc. Then you can go and check any authentication in between the endpoint and the access point. So you can go from top to bottom, you can go and check, or you can go from bottom to top and you can go and check. So what are the touch points? So whenever we are talking about the issue, we should go and check the touch points. So what are the things can be there? So here you can see at this in the diagram, you can see that you can go and check the channel feasibility. You can go and check the access point feasibility. You can go and check the IP reachability in between the uh, access point and the WLC, and then the cap web tunnel related configurations or cap web related issues that we can go and check. Then we can go and check the authentication, the ICE integration, how it is integrated with the WLC. Again, we can go and check in case of dynamic address assignment that the DHCP and the DNS servers are working properly or not. Okay. So let's discuss more about the approach that we have to use or we should use while doing the troubleshooting. So for any troubleshooting, we should define the problem. So we should know what's the problem first. Then to reach out to the solution, we should have the multiple ways. Say for example, if certain destination, say for example, if ISP is down, or say for example, a certain destination is down, a certain website is down, then what are the things you will do? Obviously we'll do the ping and trace route, and you can check the ping drop. You can go and check the trace route at which particular hop it is dropping. Now with ping, once you come to know that this is the point I'm unable to reach, then you can go log into that particular device and then you can check that from there what are the issues. So here also we should first of all understand the problem. Is ISP issue or it's a website issue, it's a slowness, loss, latency, jitter. Likewise here we can go and check, is it a authentication issue, it's a AP issue, it's a uh, uh, WLC issue, etc. Okay, so we should know first of all what is the problem. Once we identify the problem, so from problem definition we should identify the problem. So we can go and ask questions related to problem definition, and we should finally know that what's the problem. Then we can go and do the testing. Now the testing means that we should have the basic sets of command. So basic set of command related to the basic troubleshooting. Once we do the basic set of, once we run the basic set of command, then we should go and analyze that in depth, and then we can move to the solution. Now here again you can see that the analysis phase, again we have chance with our questions and with our analysis to redefine the problem statement. Okay, so finding the problem is 50% to solve the problem. That's the thing. If you know the exact problem, where is the problem, that is the 50% of the solution for any type of troubleshooting. All right, so define the problem, understand the possible triggers, know the expected behavior. If we are able to reproduce it, do not jump to the conclusion initially. Understand the client state. We know that if we are using the bottom to top approach, so what is the state of client means the state of the machine who is connecting with AP. So is the application slowness? Are they are getting some IP address or flap in IP address, or they are not getting any IP address? Do any problem with the authentication? Are they able not, are and they are not able to see the SSID, or maybe SSID strength or the signal strength is very slow or less. So those things should be added, and these things should go inside the uh, questions. So what you are doing, that you are going and asking that these questions, what exactly you are facing. So for example, application slowness, that means you have done the authentication, you have the IP address, you have the RF health, you can see the SSID. Again, application slowness can map to the RF health also. So if you have weak signal, then maybe the slowness of the application, correct? So we need to understand, here you can see this chart, that problem, then questions, and while you're doing the analysis, again redefine the problem. That's the important key we have. So let's know where is the process the client is currently at. Key item to know for the effective troubleshooting, needed to narrow down your problem scope. That's the key. Narrow down your problem. The controller keeps client state for all connected clients. Some items handle on the AP only probes, authentication, etc. We know this thing that yeah, these are the touch points. So you should know the touch point, narrow down the problem, reach out what exactly at which particular point the problem is there, and then solve it. So now again you can see that again if we go and break out this, so at what level, so we are going from the, say for example, if I start from top to bottom, so that means we are going from, actually this is bottom to top. So suppose I have client, and then once I have the client, obviously this client is connected with AP. So here you can see the AP related things that we can go and list. So listen for the beacons that uh, these are again related to clients, correct? So you can go and list out these informations. So you're listening for the beacons. The client can request probe, then they will get the response, the authentication request, authentication response. Here your authentication will go complete. Again, we are going to discuss more about authentication in upcoming section, in the security section. So where we'll go and learn about various ways of authentication and security feature inside wireless. So yeah, so you're listening, then you are sending the probe, and then the authentication is happening. That's the unauthenticated unassociated. So client want to associate with the AP. That's the process, or that's the phase. Then state two, where you have authenticated unassociated. So you are getting the network, that's the SSID. You click to the uh, join button, you want to join it, and then your password is working. So that means you're authenticated, but still you're unassociated. So what we can do: association request, association response, EAP over LAN authentication, encrypt the data, forward user data. So these are the 10 steps that you'll find that you have issue related to beacon, probe, authentication, association, or any type of authentication in between the user and the Redis server, end-to-end authentication. Next was the connection process. So we have discussed about this process earlier in the last slide. Uh, Probe, you're sending the probe, then you're getting the response. You're sending the association. Remember, authentication and then association. Then you can see that we have this process of 802.1x authentication. We are going to discuss this in the security section, more about the authentication and the security. Then exchange of encryption keys, DHCP, and then finally you will move to the run state. We know this is the final state, run state, where each and everything is working perfectly. Now again, if you want to know all the states more and more, so we have the policy enforcement module, that's the PIM in short, inside the uh, inside the split MAC architecture, the start till run. So here you can see step number one till the last step, start. So 1, 2, 3, 4, 5, 6, 7, 8 eight states we have. And if it is in run state, that means everything is working fine. So uh, initial start of the client authentication check, 8021x, that is again .1x requirement. L2 authentication completed. WEP, if you have the WEP key, we'll discuss about security later on. Then DHCP request, web auth request, and finally in the run state. So in between, you may have any issue that you have to detect at exactly what point you have issue, and then you have to solve it. This is the final flow chart. Here you can see on your screen that is start, check the authentication, then .1x required, then your L2 is completed. If it is not, authentication failure. If it is, then you will go and move to the web required. Web should be 100% successful. Then you will go and move to the next step. Next step, here you can see that you have the DHCP required. Again, DHCP required, then you have web required, web auth required. If it is fail, again, it will go and stop. So likewise, you can see the complete chart here, where you have L2 policy, .1x, web required, 8021x, OpenSSID, mobility, DHCPR, web keys, and again, if you don't have any .1x, then it will go to the run state. So it will go and complete the steps. Say for example, it can go like this, and this to reach to the run state. So it doesn't mean that always I have all the policy and it will go and across all the 20 steps or all the steps that we are seeing here. But yeah, these are the steps and these are the touch points where we should go and examine and try to resolve in between that. Okay, so this is the troubleshooting option, and how we can go and define the problem and uh, do the solution. So narrow down the problem, reach to the nearby touch point, go there and try to check exactly which technology the problem belongs to, and then try to resolve it. In 3.4, we have to learn about IP services. In that, we have NTP, NAT, first hop redundancy protocol, and then multicast. So let's start with NTP, Network Time Protocol. We used to give the same time, obviously the time and the date, to all the devices in the enterprise network infrastructure. Now, one of the most important use case for this is that nowadays all the devices they are doing authentication with respect to their certificates, and for all those certificates, all digital certificates, we need to sync the time to all the devices in the IT infrastructure. So that's one of the main use case we have for NTP. Now, how we are going to do that? We'll see that. We'll discuss more about that. But we may have some external server hosted in cloud, or we may have some internal server inside in premises, or we may have any Cisco devices that is working as a NTP master or NTP server. So all these options are available. There are some terminology used inside NTP. Say for example, what is a stratum? So what is happening that NTP device will form an association with NTP device closer to the time source. So you have your time source nearby, and that measurement is the stratum. So for example, that uh, a stratum 1 versus 2 means that if it is 1, that means your source is nearby. If it is 2, that means your source is 2 hop away. Source means the time source. Okay. Now, how we are going to configure the NTP? We have client server model. We'll see that in the lab section. So one is the NTP master and other will work as a client. We can do peer-to-peer as well. Now, peer-to-peer means, obviously we know peer-to-peer means point-to-point. So peered NTP device can get their time from each other depending on who is the closest. That is the lowest stratum. We'll see that all these things in the lab section. Now, NTP say control packet or NTP message exchange, we can do the encryption as well. So we have that encryption feature for NTP that also we can verify in the lab. Now here in the diagram you can see that you have the time source, and then suppose we are at router D. It's very easy and simple that we can go and simply give NTP server and then the server 1 versus 2. Now, for example, if there are two server and one you want to give priority, so we have this keyword called prefer. So first will be preferred and then it will go and check the other. The NTP can do the tiered approach as well. So what does it mean? That since you're getting the NTP information from the servers, that's router D, C can get all those information for D as well. So that's the tiered approach. So here you can see that for C, the server is nothing but router D. So I can go to C and then I can tell, okay, NTP server and the server IP is 51111. Okay. Likewise, we can go and do the configuration for router A, and I can tell, okay, for router A, your NTP server is router C. So that hierarchy we can follow. Uh, Suppose in case that you don't have any external time source or maybe internal time source, in that case, any router, we can make that as a authoritative source or the NTP master, and from there it will go and take the NTP information, or it will send the NTP information to all the clients. Again, in the diagram you can see that we can do the peering as well. So suppose if we want to have some fallback or redundancy type of thing, so we can go and do the peering configuration as well. So here you can see that router D, I want to make as a master. So NTP master is the keyword, and then 10 is the stratum number. We can go to the router D, we can set the time, whatever current time is there, and then we can make that as a master. Then for A and B, here you can see that A and B I can go and make as a peer as well. So suppose if the Ethernet link will go down, because they are peer, they will update their NTP information to each other. So this is the way that we can go and create the master, and obviously we can go and create the client as well. So master will send and client will get the information. We'll see this in the lab section in the upcoming recording. Apart from that, we can go and do the authentication as well. Here you can see that I have NTP master, and then I can go and use NTP authentication, MD5 and then the password. Then I can go to the client side, and those client side I can go and tell, okay, NTP authenticate the key, the NTP trusted key, and what is the NTP server IP. Okay, so this way that master is sending the information to the clients, but the message exchange in between them is the MD5 encrypted, or MD5 actually authenticated. All right. We have some other commands as well. If you want to disable the NTP, we can go to the interface and disable it. If you want to do max association, means how many clients that a master has, so we can go and do the max association, 10, 20, etc. Just to prevent the interfaces, we can go and do the loopback interfaces. So in that case, if any of the physical interface is down, still the NTP is reachable via the loopback, and that's the standard configuration we have in the industry. If you go and check the NTP source, the AAA radius, or maybe TACACS authentication source addresses, TFTP source addresses. Generally, we used to use the loopback addresses because that will be always up, and any physical interface is down, is still that loopback will be reachable. Then there are some verification. We can go and type show clock. We can check the time, show NTP status. It will tell you the detail about the NTP information. And finally, we can go and check the NTP association as well. All right, so let's just stop here, and in next section we'll do the lab related to NTP. Let us perform the lab task. In this lab we have router R1. So let me show you that I have a router that is connected with a switch that is 105. The router interface is 00, switch interface is 00. So over these interfaces I'm going to enable the NTP. First of all, we'll go and check the time. So here you can see the time for router 1 is this. Then I can go and make this as a NTP master. Now my router 1 is NTP master. Then I can go to the switch, and then I can go to the NTP, and then I can give the server IP. Server IP is 10.111.1, and that's it. So I created master, and then I have this client who knows that how to reach to the server, what's the IP of the server. Then we can go and verify this. So we have two main verification command. One is show NTP association, and one is show NTP status. Okay, so these are the two commands that we usually um, use to verify. Now suppose if we want to do the authentication. So for authentication, I can go ahead and use the NTP authentication key, say for example MD5 and Cisco. Now from other side, what you have to do is you have to go and do this NTP, first of all authenticate, then NTP authentication key, and that's it. So these are the commands that we should go and use. So here you can see that you should use trusted key as well. Key numbers for trusted times of source, say trusted key. I can go and give one. And if you go to NTP, the options that you can see here, you have the authentication key, and then you can go and use this trusted key as well. So this is the way we can go and check the we can put the authentication in between client and the server, or in between master and the server. Now, other options, you can see clearly that you have authentication, you have max associations, you have peer command, you have server command, you have source command, etc. So now I can go and check show NTP association, and in the R1 also we can go and check show NTP association, show NTP status as well. All right, so that's the way that we can go and run and verify the commands related to NTP. We have done the lab for the NTP. That lab I have done actually over the viral, but we haven't seen the exact result that it should come. So then I have created this topology. Obviously, this topology I created for HSRP, another lab, but here I want to show you the NTP configuration. I have made this R2 as a NTP master, and this router 4 and router 5, although I have changed the uh, display, means this is a router, but I have changed the symbol. It is looking like a, PC or end machine. Anyways, I'm going to use these devices as a end machine as well, but R4, R5 and R2, they are part of one LAN segment. Even R3 is also part of LAN segment. uh, I have done the configuration related to NTP to these devices on 4, 5 and 2. So if I go and log into router number 2, say for example I am here, and if I go and show you show run section NTP, so you'll see that here's the master, and what's time. Time is this 18/20/20. Now if I go to R3 and if I go and check show NTP status, you can see that it is synchronized with this IP, and show NTP. What other options we have? Association. So here you can see the association as well. We can go and check show clock. It is getting time from the master. Likewise, I haven't done any configuration to R3. So let me go and, oh, this is the R3. So the we have done for R3. Let me see that if I have done the configuration for R4 and R5. So if I go to R4 and we see show run section NTP, yep, that's configuration is there. And if I go and check show run section NTP, NTP server and some clock period is there, it's okay. So everywhere you can see that this way we can do the lab. You can go and check the association, and you can go and check the status should show synchronized. All right, so let's stop here. In 3.4, we have to learn about network address translation and port address translation. Now, when we are talking about NAT, this is simply that you are translating one IP versus other. So there, actually, if you read the textbook, so it is given that you are translating private to public address, but actually it's not 100% correct. We can translate any IP to any IP, and that's the network address translation. But mainly, we used to translate private address to public address just to save the private address space, and even in this way, we are getting first level of security as well. So now we are doing the translation. At that time, you will find that we may have three model. We may translate, for example, many to few. So for example, many to few means you have many private addresses and then you have less number of public addresses. Or you can do one-to-one translation or a static NAT. So that means you may have a dynamic NAT, you may have a static NAT, And then finally, there are a chance that you are translating to one IP with multiple port. So that is nothing but port address translation. So these are the variations we have in the NAT, and then we'll learn different type of terminologies used inside the NAT. Obviously in Cisco, what are the things that can be used? Before that, we know that we have public address, that is the internet or routable address. We have private address for class A, B, and C. When we want to do, our aim is to do the private to public address translation. Uh, Somewhere it is written that you are translating unregistered address to registered address. So that's also true. Then what type of NAT we have? We have a static NAT, we have dynamic NAT, we have NAT overload, or we have port address translation. Now, I told you that we have some terminologies in NAT. So what terminologies are there? You have inside local, inside global, outside local. Wow. So what does it mean? How can I understand that what is inside local, what is inside global, outside local, outside global? So here in the diagram, you can understand, suppose this is the NAT router I have, where I'm enabling the NAT. I have my inside IP, and then I have my uh, inside global. Actually, this is outside IP, but technically it is as per the NAT document that this is your inside, obviously local, that is your private address, and then this is your inside global, that is the outside. Then when you are reaching towards the host B, that's your destination. So for that perspective, the NATed address. So here you can see this NAT. Uh, we are doing the NAT in this particular address. This is the public address from other side. So that will be the global, outside global. And then again, you'll find that your outside local address, actually, this address is represented by 99.11.12. So that is also the outside local address. So local, global means that's the routable from one side. Then you have local and global. Most of the time you'll find that the local and the global outside addresses are the same. Now, if you see the packet flow, so when you are sending the packet and you are doing the NAT and then you are sending to the destination, what is happening? So you know what is your source, you know what is your destination. Now this is the destination host, because I can't send packet to private address, correct? I should send this to this particular destination. Obviously, here you can see at the destination end, the NAT will happen and the packet will get delivered to the destination. So you have source and destination. When it came here to the NAT router, so NAT will change the source IP. So here you can see that source IP has been changed to this IP plus port, but your destination address will be the same. Finally, when it reaches to the destination where you have the 99 address, obviously this 99 address will get converted to 1.5, and what he will think that my source is 55. And then same way the reverse uh, route will happen. So this is, so from A to B, and then again B to A will happen in the reverse direction. So what you can think here that at each hop, because the NAT is there, or you can think that whenever you're doing the NAT, obviously NAT will change the source. So here source address is changing, and here when you are reaching to the destination, if you send the return packet again, the source will get changed. Correct. So what is your source here? Whatever destination for A, that will be the source for B. So that means the uh, B destination. So what will be the destination of B? That will be 10.1.1.10, but it should go to 55 address. Correct. So here you can see that destination, it will get reversed. So the source will be 192.168.1.5, but destination will be 55.1.1.1, and then the port number. How we can go and enable on the Cisco devices? We should go. So suppose if you have your Cisco router here and you are enabling the NAT, this is your inside, and obviously this is your outside. So you have to go and give the command IP inside and IPNAT inside and IPNAT outside to these interfaces. Then we have option. We can create the pool for pool of say for example public addresses where I want to do the translation. Then I can create the access list where I can put the private address, and then I have to go and give the NAT statement. This is for dynamic NAT. Then for static NAT, because I don't have the pool of addresses, for example, because I am doing the overload over the interface. So I'll show you the statement for a static for NAT overload and static NAT. Uh, Static NAT will be very easy. So let's check. Say static NAT will be very easy, the one-to-one. Okay. Then you have NAT. So for example, overload, where you want to do the um, translation with respect to interface with various port number, and then you have the dynamic NAT where you have many to many. Remember, many to many translation or many to few many translation. So here you can see that this case dynamic NAT, that I have pool of public address like this. Then I'll go and create the source like this, and then I have to go and give one NAT statement. So what will be the NAT statement? Let me show you the NAT statement in the next slide. All right, so let me go to the next slide. Here you can see that you have the NAT statement. Let me erase this. And so here you can see that this is your, say for example, this is your access list. This is my private, and this should be first thing. Then this should be second, that you should define your public address, and then you have this NAT statement. So what you are doing basically, IP NAT inside source. So this will call this IP, and then you are translating to this IP, that is 2. So 1 to 2, inside to outside. Now how to do with respect to overload? So for that, let me show you that as well. And obviously we are going to do the lab, so it will be much more clear. Uh, Here you can see that in this case you have interface, you don't have this pool, but you have the interface. Over the interface you are doing the overload. How we can verify it? We have show IPNAT translation, show IPNAT stats. If you want to debug, we can go and do debug IPNAT. If you want to clear the translation table, then we can go and do the clear IPNAT translation. Okay, so let's stop here, and in the next section we'll perform the lab. Let us perform the lab task. So in this lab we have the small network, and IP that I'm going to use here is 10110. That's the gateway. This is dot 3, this is dot 4. These routers I'm going to use as a host machine. They are not doing the routing, but they're working as a host. And for outside I'm going to use 200.1.1.1.0, where at this point I have dot 1 and this point I have dot 2. Okay, so it's very simple topology, and this device is going to work as a NAT device. All right, so let's do that. I have already assigned the IP address. I haven't enabled the NAT on any of the devices, so let's do this. All right, so what we can do as per the diagram, R1, the gig 01 will become outside, 02 will become inside. So I'll go to router number 1, and here I should go and do the configuration. So let me do that. Say 0/1 is working as a IP NAT outside, and then interface gig 0 slash wow. So let me do interface gig 0/2 should work as a IP NAT inside. I'm running this configuration, this lab over the virtual machine, so that's why we are getting some sort of CPU hog errors. That's okay. So I have two interfaces assigned as a outside and inside. Then I should go and do the configuration for NAT. First of all, I want to do the NAT uh, dynamic NAT configuration. So where what we need to do, we need to create the ACL entries. So I can go and create IP access list, and then I can give a name. So for example, my host having IP range of 10, and let's do like this. I can give a standard as well because I know that I have the ACL where I want to use only IP addresses. And then I can go and give the name. So for example, host 10. Then I can go and give permit 10113 and then permit 10114. These are the two IP I have here. 10113. You can see that gateway is 10111. And then I have 10114, its gateway is 10111, like that, and we are using no IP routing. That means if you go and check show IP route, you'll find that your routing is disabled. They're working as a host machine. Alright, so I have my ACL created what I want now. Next, I want to create pool of IP addresses. We have IP address, for example, um, this point, this external interface is 200.11111, but let's see that I want to use say 200.111.5 to 10. So this is the pool of address I want to use. What we can do that I can go here and I can create IP NAT, and then here you can see that we have pool. So let's create that IP NAT pool. Name of the pool is say for example NAT pool. Then what will be the address? So let's go and give the address 201.5. You can see the start address it is asking, and then it is asking the end address. Then I can go and give the net mask 255.255.255 dot anything. Say for example 248. Okay. Okay, it is telling that it should fall inside 240, so that will be 16 or the 14 valid addresses. All right, so once we have this, then what is the final thing that we need to do? Say IP NAT, and then you have to use the statement. So what is that? Say here you can see that IP NAT, what is your source? That will be the ACL. And what is the ACL? That was host 10. And then what is the pool name? We have the pool name called NAT pool, and that's it. So let's see that my access list name is correct. So host 10, that's 100% correct. And then we can go and verify the NAT configuration. So I can go and check NAT pool, NAT pool. All right. So now we have the correct NAT configuration. I can go here to host number 3 and then host number 4. So if I ping say 200.1.1.2, it should be reachable, right? And if I go here and check the NAT, show IP NAT translation, So let's see. It is not showing any NAT. Show run interface gig 0/1. Let's see the NAT inside and outside. So this is the outside, and if I go and check 2, this is the inside. First of all, let me check that from here I am able to ping to my gateway or not, and this is working. Then let me go and check that from here I am able to ping to my router outside interface or not. That is also correct. Then from here, do I am able to ping to the NAT address, that is 200.115, and it has some problem. So let's see. And show run interface gig 0/1. So here I can see that I have this address and this subnet mask. If I go and check my host section, alright, so I'll go and try to change this ACL, but you can see that we are doing the correct methodology to do this. Say 10.1.1, for example, 0. Let me see, do I have option to give wildcard? So I'm taking complete range here, and let's see what's the final result. So I should go and remove few of the statement from here. Let me go and use IP access list standard host 10, and then I'll remove 10, 20, 30. Alright, so let's quickly see that what is the configuration. So permit 0, these wildcard bit. Wow. So let me do this one more time. What I want here, I want to permit, and I want to permit 10.1.1.0 0.0.0.255, and then if you go and check show IP access list, you can understand why this is coming, because the wildcard that I have given was wrong. I should give the correct wildcard, otherwise it will obviously do like this. So we'll go here and we'll remove this line that is 40, and then we can go and verify. Finally, our access list is this, and then we can go here and try to reach the destinations. Say for example this is okay, they should be reachable, 200.1.1.1, but what about 200.1.1.2? And suppose if it work, then we should have a NAT entry over router 1, show IP NAT translation. So what are the verification commands we have? We have show IP NAT translation, and then we have show IP NAT stats. Okay, so what it is telling, that you have 0, 1. So let's see that I have interface 0, 2, that is inside, 0, 1 is outside. Then we have the ACL, and what's that? Uh, 10 pool, NAT pool. Then you have this NAT pool where you have this start IP, this end IP. Okay. Now at this point of time, my IP that I'm using here is not routable. It's not reachable. I don't have the reachable IP address. So what I will do that this scenario should work is that I'll go and I should use the NAT overload configuration. So what does it mean? I should go and use IP NAT, and we have the, let's see that what we have IP NAT source, and source is the list, and what was that source list, say host 10. Then I'm going to use the pat. So the interface, now what interface we have the interface uh, gigabit ethernet, and that interface is nothing but 0/1, 0/1 overload. Now we can go and check the NAT configuration. So we can go and check sure and section NAT. Let's see. So now we have two statement here, and one statement is related to dynamic NAT, one statement is related to PAT. So if first statement will not work, then it will go and check the second statement. So now if you go and check 200.1.1.1.2, still it is not working. And if you go and check the show IP NAT translations and strats, so NAT translation is not working. And then we'll go and check the strats as well. So you can see that the stat is also not working. Now, what wrong we have done here is, so if you go and check the syntax, you'll find that, let me remove this statement first. And then I'll go and use a IP. Even let me remove the upper statement as well. 0. Okay. So what is wrong here? Why it is not working? When I'm using this IP NAT, I should use source list. That's the complete statement actually. And then the host, and then we have the pull. That pull is nothing but the NAT pull. That's it. So this is the valid configuration now. You should go and check. At least it should start translating the packets, correct? So if you go and do the ping for 2222, now if you go check show IP NAT translation and show IP NAT stat translations. I have built the lab over the viral, and in viral we are seeing some issue that NAT is not working properly. Although we have done the configuration, the same configuration I have done in GNS. Here you can see my laptop, all the same type of devices, and only thing that the interface is different, but same IP schema, everything is same, even the configuration and all the rules that I have created, each and everything is the same. Now here you can see that we have IP NAT inside, we have IP NAT outside. So let me show you that I have serial interface, and then I have fast Ethernet interface, and then I have this NAT configuration, then I have the access list 10 configuration. So we have all these configuration that we have studied in the previous recording. I just wanted to show you the verification command. So if you go and check show IP route, this is working as a host machine. I can ping to my gateway, that is 10111, and here you can see the diagram that this interface F00 is 10111, then this is 200.1111, and then you have the outside IP that is 200.1112. So let's do the verification. If I go and ping 200.1.1.2, you can see I'm able to reach. And if I go here and check show IP NAT translations, so here you can see the translation. I have one entry coming from this. The protocol is ICMP. If I go here to this device, that is the outside device, and if I go and enable say line VTY024 login local, and then if I give the username and the password Cisco, and then if I go here and do the telnet 201.1.2, connection refused by the host. But if I go and check the translation history, you can see that it tried to convert the IP, and on top you can see that I have inside global, inside local. So inside local to inside global, and then outside local and outside global are almost the same, correct? So in the same way, we can go and create the PAT as well. So what was the command for that? Just for a revision, show IP NAT, and we can go and give source, and then we can go and give the interface. We know that the interface I have 0/0, I can use overload. Okay, what are the verification commands we have? We have show IP NAT translation, show IP NAT stats. So these are the command and the verification. Better we can do the lab over the GNS3. In 3.4c, we have to learn about FHRP, and we have to understand the theory, and then we have to perform the lab task as well related to first hop redundancy protocol, that is the hot standby redundancy protocol HSRP, and then VRRP. All right, so let's start with HSRP. Uh, First of all, why we need first hop redundancy protocol? We need first hop redundancy protocol because you can see this diagram here. You'll find that okay, uh, I can go and reach to the switch, and then I can go out, or I can do anything, correct? The problem here is that suppose if your this link will go down, then what we can do? Obviously, all the devices in the network, they will lose the control. Why? Because you have only one path, you have only one dependency. So you don't have triangle in a network, or you don't have loop in a network, or you don't have redundancy. Suppose if you have this type of connection, and then if these devices can work as an active or a standby or primary or secondary, if this link is down, still you have the way that you can go and reach outside, correct? So that's actually the concept, or that's actually the need behind creating the first hop redundancy protocol. Now, doing so, there is one other problem. Suppose if you want to use this path via this switch, so what will be the gateway address to the host, because generally we used to hard code the gateway address. So either gateway address will be this switch physical interface, so this interface here, or maybe this interface here. Suppose if your switch is down, this end host machine, they can't dynamically change the gateway. So rather than, what is the strategy here is that you should use some virtual gateway, or you should have some virtual router in between these physical devices falling in the same network, and that virtual IP we are going to give as a gateway address to the client. So either if first or maybe second switch will go down, there is no impact in a network. So we have the label of redundancy. Now we have multiple protocols. We are going to discuss about hot standby redundancy protocol. Here you can see that you have switch 1 and switch 2. One is working as a active, one is working as a standby. Rest other devices are the listening router. As per the highest priority, so there is priority. So for example, 200 versus 10, so higher is better. As per the highest priority, one of the device will work as a active, and then rest of them will work as a standby and listening. In a group, we can go and put say 16 devices. So here you can see that you have priority from 0 to 255, and default is 100. Higher is better. So what does it mean? It means that although you have the virtual IP, and suppose his priority is 200 and this priority is, although it is written 100 and 150, but let it be, this is 100. So the traffic will go in this direction. Now what will be the fallback? If you have LAN interface will go down, obviously they will do some sort of re-election, and this device, because one is unavailable, so you have one other path that you can go in this direction. But again, there is one question that what will happen if your WAN interface will go down? Okay, so there may be chance that your switch will go and reboot, your this interface will go down, your WAN interface will go down. What will happen with the active traffic? What will happen with the flow of the traffic? How it will converge? How there will be the fault tolerance, etc. Okay, so we can discuss that. Never mind, one by one. First of all, when we have the two routers in a group or two switch in a group, we can go and create, or we can do the HSRP configuration. Then they will go and elect who is the active and who is the standby. And the message that they are going to send across in between devices are, say, initial, learn, listening, speak, standby, and active. So in active state, we have this devices that is actively, they, means they will form the HSRP uh, neighbor relationship. We can't tell that neighbor relationship, but they will form the HSRP in between them, and one will be the HSRP active, one will be the standby. So here you can see that in the active state, an interface in an active state is the live gateway and will forward traffic sent to the virtual IP addresses. Host will use the virtual IP as their gateway. The active router will respond to the ARP request for the virtual IP and the virtual MAC. So far we have discussed about virtual IP, but we have one other concept as well, that's the virtual MAC. Now the Hello Packet Exchange for HSRP, we have is speak, standby, and active. Okay. All right, so let's quickly discuss about the virtual Mac. And once you go and do the basic configuration, I'll show you that virtual Mac in the next slide. So you can go and go to the interface, or you can go to the interface VLAN. You can go and use this command standby. You can define the priority. You can go and define the virtual IP, etc., etc. We'll see all these things in the lab. Then here you can see that this is the diagram, although our lab diagram is a bit different. I'll show you in the lab diagram. So these things I'm going to configure in the lab. Instead of interface VLAN, I'm going to use any Ethernet interface or any physical interface. So you can go and do the configuration. Now, important thing here, you can see that the ARP response will come from the virtual MAC. So this particular virtual MAC, what is the format? So here you can see this is the format 000.0C07AC, and then the group number. This XX is in the hex that will represent the group number. So suppose if I go and give the HSRP group as 10, if you convert 10 into the hex, it will come 08. So that's why the final MAC address is 000 AC07 AC08. Okay. We have this. If you want, we can do the MAC address manual configuration as well. If you want, we can do the authentication configuration as well. Then we have the concept of print. So what is mean by print? Suppose this is active and this is a standby, and it will go and reboot. So this will become active, but suppose if will come back online. So if you enable the print feature, that means when the active will come, the system will detect, oh, he has the highest priority. So for example, he has a priority 200, he has a priority 100. So this guy has the highest priority. That means again he will become active and he will become the standby if we do the print, if we enable the preemption. Otherwise, active will be active, standby will be a standby. After the failure, standby become active, he will be the active. Okay. So we have the command. We can go and use a standby one preempt. If you want, you can disable the preempt as well. Apart from that, we know that we have the timers for HSRP. By default, that will be 3 second and 10 second. 3 second of hello timer, 10 second of dead, means you are sending 3 packets. Fourth packet, you are not getting response. You'll make that your HSRP group partner is not active, maybe some issue, maybe you have a split brain issue, etc. They're using the multicast address 224002 and the UDP port 1984 for this particular hello exchange. If we want, we can give the time in milliseconds as well. So if you want aggressive timer, if you want fast convergence, you can go and change the hello timer. We have a few of the verification command that we can go and check show a standby. We can go and check show a standby brief. All right, so we have few more slides related to failure as well. So let's complete these slides, and in next session anyways we have to do the lab, so I'll go and discuss more and more in that. Now here you can see that tracking. Say for example, this link is down. Suppose his priority is 150 and this guy priority is 130. So obviously he is active and he is a standby. Now what you can do, you can track the interface that is going to WAN, say 223, and then you can decrement the priority, for example 60. So if you decrement the priority, if this link is down, what will happen? This priority will become 90, and this is what 130, 130. So that means the traffic will go in this direction. And that's the use of the live tracking, or that's the use of the tracking, that you can track the interface, you can decrement the priority, and the standby will become the active and the traffic will go in that direction. All right, so these are the points you have. At this point of time, you can think that how we can check this link. Obviously, this link is tracked. If this link is down, automatically it will go in this direction. If this device will go, obviously it will go in this direction. If this is down, you should do the track and then decrement some sort of priority. So this direction will go in, and this traffic will go in this direction. All right, so these are the concepts related to HSRP. Let's stop here and perform the lab task. All right, so let's do the lab. I have created this topology in GNS3. Here you can see that I have router 2, I have router 3, and then I have one router. I have changed the display, means I have changed the uh, look for these devices. It's a router, it's showing you as a cloud. Then I have this routers 4 and 5, but it look like they are the host or end machines. I have assigned the IP addresses as per this schema 10110. This is obviously the LAN segment that you can see behind R2 and behind R3. And then I have a static route going or reaching towards R1 from R2 and R3. Okay, so let's do and enable the HSRP over R2 and R3. Obviously, I'm going to use F00 for uh, these interfaces, and then I'll go and assign the default gateway for R4 and R5. So let's do this. If I am inside R5, let me check that what gateway I have given to these devices. This IP default gateway is 10.1.1.2. That's not correct. Means I should change this. I will go and change this because I want to use the default gateway as the virtual IP. So before changing anything here to these devices, let's go and do the configuration for the HSRP, hot standby redundancy protocol. So we can go to F00 and then you can use the keyword as standby. Then you can see that you have options: authentication, delay, IP, MAC, preempt, priority, redirect, timers, track, use BIA, burnt in address, and version. All right, so what we want to give the group, and then I want to give the virtual IP, say for example 10.1.1.250. I don't want to make this secondary, so leave it. So now I have assigned the virtual IP here. Then what I will do that I'll go and give the priority as well, because this R2 I want to make as the active at the master, you can think, and the other one will be the backup or standby. So what configuration we have done? We have done only two configuration: standby IP and the priority. I can go to R3. You can see that they try to move from speak standby active, and if I go and check show a standby brief, so he don't know who is the standby, but his state is active. Great. So let's go and do the configuration to R3. We have R2 and R3 connected via the LAN interface. I can go and do the debug as well, so we can see some of the packets. I can go to the fast Ethernet interface and priority I'll give 100. Now you can see that the state disable to init, redundancy, this is the group, disable init, and now you can see the other messages. I'll pause here, you can have a look. Init to listen, passive, active, the group, this become the backup because it has a lower priority. Then it is telling who is the active, what is the VIP IP, what is the router ID. Uh, then you can see all these messages. Now it is sending the hello packet after every 3 seconds. So since the debug is on this device, I'll go back here and we can check the standby. If I can get the detail. So what I can do here, that I can enter. Here you can see that what's the virtual IP, what's the MAC. We have discussed about this because we have used the group 10, so that's hex is 0A. This is by default running V version 1. The hello and dead timer, the active router is local. Now if you go and check the brief, then you can see who is the active, who is the standby. So it's very easy to actually configure at this point of time what you want. I want to go to these devices and I want to use the IP default gateway as 10.1.1.250. So these devices, they should have the proper gateway. All right. Now what we can do that we can go and test it. So I can go and ping to the R1. R1 has one loopback interface. So what does it mean? If I go to R2 and if I can say for example ping 1111, Let's see if it is reachable. Otherwise, I'll go and create a static route from R2 to R1. Sure, and let me check the routing section. In R2, I can't see that I have any static route. So I'll do one thing. I'll go and create the a static default route for the device 200.1.1.1.2. And if I ping now, yep, like that, if I can go here to R3 and let me undebug all to run section IP route. If we have any routing, no. And what IP we have here? So we have this 201. I can go and create IP route 000 and then the gateway 201.1.1.2. And if I ping 1111, if I can source as well, reachable. So now if I go to this guy here, that is one of the client. I should give the client instead of the R4. So suppose this is client 4, and if I ping 11111, that's the outside. Let's see if I'm able to ping. Yep. And if I do the trace route for 1111, let's see how it is going. So first it is going to the gateway that I have. This is the router from where I'm going, and then I'm going outside, correct? So what we can do here is that we can do the ping, and subsequently we can shut down one of the interface. So what I'm going to do, I'm going to shut down the R2F00 interface. So I'll go to R2 interface F0/0, shut it down. So in that case, the HSRP will go change, and you can see standby brief. Both sides you can see now it is unknown, but if you go to R3 and if you go check show standby brief, so he is the active, although his priority is less. Now we haven't done the print at this point of time, so if I go here and interface F0/0, if I do no shut, and you can see that this is still active, although his priority is less, and this guy here is, let me show you the full output. Let me just this. So still it is in speak because we haven't enabled the print command. So still it is in standby. You can see state is a standby, although the priority is high. So for that reason, what we can do, we can go to 00 and standby 10, and we can go and enable the print command. I don't want to use delay and other thing, but if I do the print here, now you can see the selection has been changed. I should go and do the print, oops, here as well. So I can go to R3 and I can enable print here as well. Now if you go and check the output, he is active because of the print command. Now likewise, if you want to go and check this interface up and down, so that also we can track serial 00 as well in the this present scenario. So what does it mean? My priority is 200 and this guy has priority of 100. I will decrement the priority by 110. So what I can do, I can go to interface 00 and standby 10. We can track the serial interface 0/0, and then we can decrement the priority by, say for example, 110. Correct? Now if I go and make this interface down, So you can see that this is now unreachable. The traffic should redirect and it should go. So let's see that what happened actually. So standby brief. Now this is still showing active, but if I go here to R3, if you go and check show standby brief, what's the priority? 110. And this guy, what's the priority? 90. Okay, so that means the traffic should go, and here you can see that this link is down. So that means now this is the active one. So the traffic should go from here and then it should go and reach to here, although we have the different IP to the subnet, so it's okay. But if you go and let me stop the ping. Now if I do the trace route for 1111, you can see that how it is going. It's try to reach to its fixed gateway. Let me see what's the gateway it has. Show run section default, that's true, and show IP interface brief. So what should be the order here? That it should try and check 1.3, means when I'm doing the trace route, so it should go by this, but actually the problem here is to announce the network in the bottom. So from R3, if we go and check the R3, from R3 I should go and ping 111 and source serial 0/0. Oops, let me see what source it has. 0/1. Yep. So we can see that main idea I want to show you here, that this guy, that's the router number 1, is become active, although it is showing active, but its priority become 90, and this guy is tracking the interface and he is the active one, means now its state is showing a standby. Let's see the configuration. Standby. We'll do the troubleshooting. So what is there? No configuration. And let's see, show run interface F00, where we have done all the configuration. So we haven't done much configuration on R3, and probably that's the reason that is not showing you the result. So even we are seeing the troubleshooting as well. We can go here and give the command standby 10, and your priority by default will be 100, we know that, and then a standby 10 to the prompt if the state is changing, and then we can go and check show. Now you can see something is happening here. Now if I go and do the first route, now you can see that it is going by that path, correct? So that means if I do the ping now, okay, a little bit less, it is happening. And if I go and do the interface 0/0, no shutdown, because prompt is enabled, so this link will become active. We'll get the message and do show a standby brief. And now if I do the shutdown, so it is down. So see, for some time it is unreachable now, but now it is going from the other side. So now it is this in a speak state. And if you go and check the standby configuration, this is the active. All right, so this is the way that we can go and do the configuration. There are a few configurations as well, like if you want to change the timers, if you want to use the authentication, but this is the main thing that we use to uh, do or perform with respect to HSRP. Next, we have VRRP. VRRP is nothing but Virtual Router Redundancy Protocol, very much similar to the Cisco HSRP. The difference is that this is the industry standard and HSRP is Cisco standard. Almost they are same, but there are a few differences. We'll see that what differences they have. First of all, you can see their timer is 1 second, Then you can see that the MAC address is 224.0.0.18. The VRP print is on by default. VRP cannot directly track interfaces. It can track an object which is tied to an interface. Okay, so you can see that there are some difference, and again we are in the existing WAN. If you go to SD-WAN, specifically Cisco Viptela SD-WAN, in that we don't have HSRP, but we can run VRRP, and there we have the customized VRRP that I have explained in my SD-WAN course that you can refer. So VRRP in the existing WAN, VRRP in the SD-WAN, both are very different. Now this VRRP is very much like HSRP. It is working as a gateway, so we can have the virtual IP, we can have the priority. Again, higher priority is better. We can go and tune the timers. We can have we can go and enable the authentication. We have the reserve MAC address, which is different. There we have the different MAC address. Here you have 4 times 05 E00 dot 01XX. Okay, and here the name of the primary, say active, and the standby is master, and the backup that will go and verify uh, in the lab section. We can go and use no VRRP print, because by default this will be on. You can go, if you want, you can disable. You can go and check show VRRP. Very much same type of output you'll get that you have in HSRP. Now we have one very interesting topic here, that do VRRP and HSRP can do the load balancing. Because for load balancing we have Cisco proprietary protocol, that is GLBP, that is not in this particular course, but we have discussed earlier in section maybe 1 or section 2 that how this GLBP is working. uh, GLBP is not that popular like VRRP or HSRP, due to some GLBP. They have some reason behind that. They have some internal reason. The active forwarder or the standby, they are not able to do a load balancing in failure scenario, etc. Means they have some internal issues with GLBP. You will find that most of the places we are using either HSRP or VRRP. Now suppose you want to do the load balancing. You know that one of the router is active, one is a standby, and suppose if you have thousands of client or endpoint, you want that 500 will go via one router and 500 will go via other 100, the 500 will go via other router. Then how we can achieve that? So what I'm telling here, let me try to draw, and even you can see the configuration. That's the manual load balancing configuration we have. So what I'm telling here, that say I have these two devices, and they are part of, say for example, VRRP or maybe HSRP. Now we know that one is active and one is standby, or one is master and then backup in case of HSRP and VRRP. And suppose if you have 1,000 users or 1,000 clients, then obviously as per the standard configuration, 1,000 of the devices will go via one gateway, one active gateway. So there is no load balancing. Rather, what we can do, that we can create group. So here you can see that inside VLAN we are creating one group, and then we are creating other group. So one group is having higher priority, other group having lower priority. Obviously the VIP is different, virtual IP is different. Likewise, that means that as a whole, this will be the active for 500 user, and this will be the active for 500 users, and as a whole they will work as an active load balancer. Okay, now once you have this configuration and you want to check it, verify it, you can go and check show standby brief. So in that output, what you will find, that you will go and get the output related to both the groups. So here you can see that you can see the first and the second device, active standby, standby active. Now this is not the limitation, but actually this is the feature, that we can do the manual load balancing across the routers. All right, so let's stop here. We'll do the VRRP lab that we have done like HSRP, and then we'll check this load balancing methodology as well. Let us perform the lab task. Same lab setup, we'll go and enable the VRRP instead of the HSRP. So let me go and fix the screen. I have VRRP, HSRP enabled on router 1 and 2, so I can do this thing. No standby, say 10, like that. If I can do, interface should be fast Ethernet and 10. Then I'll go and remove the HSRP from R3 as well. So first of all, I will go and do the basic configuration, and once I will do the basic configuration, then we'll go and do the load balancing configuration as well. All right. So here we are in the router number 1. We are in the correct interface. I can go and enable VRRP10, and we can see what options we have. So I have this IP, say 10.1.1.250, and that's it. Then VRRP10. What other things we have? We can give the authentication, the prompt, priority, shutdown timers track, and track is event tracking. So here what I can do, that VRRP 10 and the say priority 150, that's the higher priority. Then we can go and check to show VRRP brief. So here you have the master, and we'll go to the other side. Here we can go and make this IPs 10.1.1.1.250. By default the priority will be 100, so you will see that you need to backup. Now if I go here and check, so the priority, the prompt, the master address, the group address, so we can see that is the master. And if you go here and check do show VRRP brief, so here's the backup. Okay, so here you can see that the master address, and you can see the master address, and then you have the group address, etc. So it is working fine, there's no problem. It will work. Now what we want here is that I want to create two group. So for example, one IP will be 250, other I'll create 251. R4 I will put in one group, R5 I will put in another group. So I'll create two group, 10 and 20, and let's do that. So now what I will do, that I'll go to R2. I already have the group that is this, whose priority is this. I will go and create one more. So for example 20, and the IP is 10.1.1.251. That is going to be the default gateway IP for 50% of the clients. And then the VRRP 20, the priority, say for example 50. So 150 and 50. Likewise, I'll go to R3 and VRRP 20 IP is 10.1.1.251, and VRRP 20. By default it will be 100, so we can understand this, that will be the master. Now we can go and check show VRRP brief. So here you can see backup master, correct. And if I go here and if I go and check show VRRP brief, so here you can see that master backup. So it is working. Only thing that we need to do, that we should go to the client and we should change the gateway address. Rest each and everything will be the same. Now if you want to see the VRRP detail, you can go and check like this. All right, so let's stop here. You can see that this way we can go and do the lab related to VRRP. In 3.4D, we have to learn about multicast, and we have to learn about multicast routing protocols as well, such as PIM and then IGMP. So let's start. Now, before starting multicast, I'm going to give you a brief introduction about what is multicast MAC address, the basic stuff related to multicast. So for example, we know that we have three different type of packets, say unicast packet, broadcast, multicast, even we have anycast as well. That's actually the type of communication. So unicast means that one-to-one communication, and there are such protocol, for example, OSPF, BGP, EIGRP, and other IGP protocol. They are basically destination-based routing protocol, and they are using. You can tell that the unicast-based routing protocol. Then we have broadcast. Now, broadcast means one to all. So someone is sending message to all. Then we have interesting packet type, that is the multicast, and that multicast is one to group. Again, we have anycast as well, that is one to nearby. Okay. In this section, obviously, we are going to focus more on multicast. So multicast means that the method of communication is from one to group. Now here, a very important fact is that if we compare unicast routing protocol and multicast routing protocol, the basic difference is that unicast routing protocol, you are building destination based routing, or you are doing destination based routing. In multicast, we are doing source based routing, means someone is the multicast source, and then you have the multicast client. Those clients want to join the multicast source feed. That's the basic difference, and we'll understand more and more about that. So you have to define the group who are interested to join the multicast source. So multicast source is sending the feed, and we'll see that how the feed is sended. There are different methodologies, and then my host, they want to join the feed. Okay, so it's something like a reverse routing tree we are creating, and actually this is nothing but RPF. We'll see that in next section, but let me still focus on basics. So let's continue the basics. We know that we have class A, B, C, D addresses. D is there 224.0.0, 239, 255, 255, 255. That is reserved for multicast address. Then we have the link local addresses used for control mechanism or to find the neighbors. Say for example 224.0.0.0 up to 224.0.0.255. Then we have public and private address ranges for multicast. Here you can see all the link local addresses. A few of them we have used earlier. So for example, OSPF, uh, hello packets, and then the DRBDS selection. For that, we have different multicast link local address, then RIP, then EIGRP, then others as well. Right. So now basic question here is that in multicast, we don't have multicast MAC address. So the question here is that how multicast they are framing their multicast MAC address, correct? We know that MAC address is of 48-bit. So what is happening that whatever IPv4 multicast address we have, they are taking 23 bits from there, and then they are adding 25 bits of this address. So 25 plus 23, you will get 48 bit of MAC address. Now how it will be? So here you can see that this address 00, obviously this is in hex. If you convert this in binary, so 0 means 40, then 1 means 0001, then again 0 and 0, then you have 5, and then you have E, and then last 0. So now you have 8 plus 8 plus 8 plus 1, that means 25 bits. Now what is happening that we are going to add last 23 bit of the IPv4 address. So 8 plus 8 plus 7. So that means up to here. So if you go add this here, So you will get this, correct? Now, this address again, if you go and convert into the hexadecimal, so you will find 0 1 0 0. Then you have to check this. What is this? So 1 2 4. So that means 5. Then 2 4 8. So 8 plus 4 plus 1. Like that, you have to do the calculation. I'll show you that what it will look like, or how it is look like. You can see here that now the finally it will be looking like this. So this is the multicast MAC address, and here you can see the mathematics for that. So in decimal it is looking like this. In hex, because we are concerned or we are looking for hex format, MAC address is in hex format, so it will look like this. Okay, now while doing this methodology we have one problem. What problem we have? So for example, this two address 225 and 231, if you go and convert their MAC address, you will find that the MAC address is same. Why so? Because again, if you go and take 23 bits, so here you can see that 23 bits, so 8 plus 8 plus 7 and 8 plus 8 plus 7, these 23 bits are common, and again first 25 bits are also common because that's fixed. So this 25 plus 23, if you go and add, you'll find the same MAC address for different IPv4 multicast address. Now we have that problem, and truth is that there are 5 different bits. That means there are 32 multicast IP addresses for which we have single MAC address. Okay, why? Because you have 23 bit, that is you are taking from IPv4 address, and then because multicast address should start with 224, so that's why you have these 4 fixed bit. So you have this fixed 23 bits and then 4 fixed bit. You have 5 variable bits that can be anything, and the combination of these 5 bits can have 32 multicast address. So that's the problem we have in the multicast, but the arrangement of the bits and the IPv4 multicast address is in a way that this is not a bigger issue. So it's not a big thing in multicast. All right, so these are the basic things that we have discussed. That's what is multicast and what are the address family, how we are going to construct the multicast address, and what are the common IPv4 multicast address we have. So let's stop here. In next section, we'll discuss more about the multicast routing. Let us discuss about multicast routing protocol or multicast protocol. We have different protocols. We are going to discuss about that one by one. We know that we have a multicast protocol, and if we go and learn a little bit deep about that, you'll come to know that okay, although we have multicast protocol, but still we need IGP, interior gateway protocol, and the multicast protocol. Both are working hand on hand to provide the final multicast feed from source to the receivers. What protocols we have? We have protocol independent multicast. We have multicast OSPF, distance vector multicast routing protocol, core based trees. Now to enable this on Cisco devices, we have to run a command IP multicast routing. Again, when we'll go and study about PIM, we'll find that they have PIM, dense, sparse, dense mode, etc. Means different variations are there for that protocol. Now, earlier in this uh, section, we have a study that they are going to use reverse path forwarding, or they are going to look that exactly where is my source. So unlike destination protocol like OSPF or EIGRP, multicast is going to form the tree, and that tree will be based on the source. So not based on the destination, but based on the source, they are going to form their multicast tree, and that methodology is reverse path forwarding. Sometimes we'll tell this, okay, we have variations of PIM. So for example, dense mode, so we are flooding and then we are pruning. Or we have other methodology where we are flooding the feeds, and then in whatever link, I don't have the multicast host, so we used to prune that, because obviously I don't have the receivers, so why I will flood those feed in those particular link or locations. Now here you can say that we have different parameters like S and G, source, comma, group. You'll find a star, comma, G as well, that is for RAN debut point, and the group. Group means the multicast address. Source is multicast source. All right, then upstream and downstream. These are the concepts. So upstream means that the link that is going towards or reaching towards the multicast server or the feed, actual feed. And downstream is where you have the receivers. So the link that is going towards the receiver. Here you can see, say for example, for router 1, the link here that is going to the multicast source is the upstream, and then these interfaces are the downstream. One condition is there, that you should have multicast host in the downstream. Otherwise, there is no point of having the downstream if you don't have any multicast host. Okay, so how it is building the tree? First of all, it will send all the feeds, and in that location where there is no multicast host, they will prune those links. They will not send the feed on those links. So that's the flood and prune. At least the prune methodology we have. Now here you can see that we have multicast protocol like PIM, OSPF, multicast OSPF, etc. Then other concept we have is IGMP. Now this is not the PIM, or this is not the multicast OSPF, etc. IGMP is a protocol that is specific to the host or those type of group they want to join the multicast server or multicast source, correct? So for that we have the Internet Group Management Protocol, IGMP. And now you can see that you have version 1, 2 and 3. Now most popular is version 2 and 3. So what is happening in this case? Say, remember, if you see this diagram, you'll find that, okay, you are sending the feed, but you should have interested receiver or receivers who will show the interest for that particular multicast feed. Suppose if you have 3 to 4 different type of sources who are sending the multicast feed, obviously one host can take only one multicast feed. So in that regard, there should be membership for that particular source, and that's the key we have. All right. So let's discuss that how this IGMP is working. Now it's very easy to enable. You can go and enable the IGMP. Actually, when we are going and creating the when we are enabling the multicast, it should enable, or by default in Cisco switches, this multicast is IGMP is enabled. But if you want to change the uh, version, then we have command here. You can see that I can go and change the version, say IP IGMP version 1, because no configuration is required to enable IGMP, except then you have to go and enable IP multicast routing. Okay, so let's try to understand that how this IGMP group protocol is working. So for example, IGMP version 1 router send out query every 60 seconds. Remember the words here, you can see that IGMP version 1 routers, say your end machine, they should have gateway. That means they will connect it with switch, and the switch will go and connect with the router. So now that router, that the nearby router, the gateway router, who is very near to the host or the receivers, the router is sending query every 60 seconds in case of IGMP version 1 to determine if any host need access to multicast server. So because router has built the tree, router know that with help of PIM how he can reach to the multicast source. So he is sending the query. Now this query is the multicast address 224.0.0.1. Now what is happening after that? Interested host must reply with a membership report. That's important. So host, they are replying with membership report for that query, stating that what multicast group they wish to join. Correct? So router is sending query and host, they are sending the membership report, just they want to join. Now there is problem with IGMP version 1 because they does not allow host to dynamically leave a group. Instead, if no membership report are received after 3 times the query interval, so router is keeps sending query, 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 and you are not sending the membership report, then router will come to know, okay, these guys are not interested. They have turned off their receiving, or they have turned off, or they are not interested to receive the feed. It's something like when we are using, so for example, radio or FM channel, we tune to go to different band, and whatever band we want to use, that particular feed will come and that music will play on. Now, suppose you're not interested and you don't want to join any group, so that means you will not respond for the query. Now, this is with version 1. Now if you go and check version 2, you'll find that there is enhancement in version 2 related to leave message. So what is happening in version 2? The queries are sent from the router as a general query or group specific query. Additionally, host can send a leave group. So now what is happening, the routers, instead of query, they are sending group specific query to the host, and host, say once they are joined, obviously they have their membership report while they are joining the or they are responding the query. So what the host can do now, that the host can send the leave message as well. Okay, I'm not interested, I'm turning off my receiving capability, I don't want to receive it. Then it will be stopped. Now all versions of IGMP elect one router to be designated querier for the subnet. The router with the lowest IP become the designated. Again, if you go and if you check some more details, suppose in that group, if I have 4 or 5 routers, so they will go and select who will send the query to all the host, and which is the router who will get all the membership report, and then he will forward that message to the multicast source, or who is sending the multicast feed. IGMP version 1 is not compatible with version 2. If any IGMP version 1 router exists on the network, all routers should running version 1. So version 1 and 2 are not compatible even in the CCNP core. The syllabus is to know understand version 2 and version 3 as well. Now, so version 2 is running by default, and it's most of the places you'll find version 2. But still in version 3 we have enhancement. So what enhancement we have in version 3? Version 3 enhancement in V2 by supporting source-based filtering of multicast group. So now we have the filtering for the source. Now, essentially, when a host respond to an IGMP query with membership report, it can specifically identify which sources within the multicast group to leave or join or not to join. Okay, so that means that uh, we have even more granularity inside version 3, where we can do the source based filtering as well. Now here you can see that you have multi-cast source, then you have the router who will send the query, and then the host, they will send the membership report. That membership report is nothing but they want to join or they're willing to join. We know from this that who is the upstream. So FA01 is the upstream, and then downstream you have 3, 2, 3, and 4. But in 04 you can see that there is no multicast host. That means the downstream interfaces are 2 and 3. FA02 and FA03 are the downstream. How we can go and enable it? By default, version 2 is up and running. Once you enable IP multicast routing, you can go and check show IP IGMP groups. If you want to have any static group, you can go and do that. If your IGMP wants to join any specific multicast group, you have both the options, correct? And suppose if you want to filter, so we have the filtering option as well. Here you can see that I have created access list for 10 and 11. These are the multicast address. And then in IGMP access group we want to join only 10 and 11. Rest anything will come, it will not join. Okay, so let me quickly log into the router and I'll show you this configuration in CLI. Alright, so we have this topology. I'll go and show you all the commands configuration in router 2. So let me go here in router 2, and in router 2 what interfaces we have? We have F A00, and I'm just showing you the configurations how it look like. So first of all, I should go there and enable IP multicast routing, and then I can go to the interface and I can go and check uh, IP IGMP version, and say for example by default version will be there. So if we go and check this, oops, show IP IGMP, you can see that you have groups, interface, membership. One of the important command we have is the membership. Okay, so at the moment nothing is there, so that's why most of the things are empty. I can go here and okay, let's see that what are the things we have here. You can see that group, interface, membership, SSM, UDLR, VRF. Okay, leave it. So I'll go here to the interface, save 00 IP IGMP version. So for example, 2. Okay, and then obviously we can go and check show IP IGMP interface, say FA0/0. These are the important commands. So here you can see that the internet address, the IGMP is disabled on interface. Okay, multicast routing is disabled, TTL0, no multicast group, interface is up and running. Later if you go and enable the PIM, and you can go and check the mroute as well, we'll check that later on. Okay, so I want to join any of the group, say IPIJMP, join the group. So let me see if I can see here. Okay, IPIJMP. Yep, you can go to the interface and then you can join the group. Say, uh, as per our example, 226 1 say 5.10, and we'll leave that source show IP IGMP interface FA0/0. Now here you can see that IGMP is enabled, version 2, the query interval, the timeout, max time. Okay, so I can see that join interface is this. Now again I can go to that interface and I want to use the IP IGMP join, and if I go here and check what options we have, so we can go and use the static group as well, and say 226 1.5.11, and we can go and see this. All right, suppose if you want to filter, so you can go and use the filter as well. Although you can see that the static group is not working, because if we want to do any manual methods, at that time only we are using the static group. But I'll go and use the join group one more time to the interface, F00 IP IGMP join group 226 say 11511 and then 12 and then say. Okay, so you can see that you have these groups, and now if you want to filter, you can go and create the access list 10, say permit these addresses. So I want to permit 10 and 11, and then I want to use this IP IGMP access group, say 10, and then we can go and verify the output. So just I'm showing that this is the way that once you apply this filter, so it will not go and join, although it is showing here in the configuration, but it will not go and join the other group, whatever not uh, mentioned in the ACL list. Right, so let's stop here. Next important topic, we have PIM, that is protocol independent multicast. Now here you can see that PIM has variation. It can run in dense mode, sparse mode, and sparse dense mode. That's the Cisco proprietary. Now we should understand that why and what is the use case of dense mode and then the sparse mode. Now dense mode is something like you are doing the flood and prune method, means you have the multicast source. He is flooding the multicast uh, traffic throughout the network, and then the receivers, uh, if you have receivers, they will join that. If you don't have receivers, it will get pruned, correct? But what is happening in the sparse mode is that is the intelligent way of doing flood and prune method. So in this case, you have one authority termed as a rendezvous point, RP. So what will happen that RP will get selected, and now it's the responsibility of rendezvous point or the RP is to do the flooding in the network. So it's something like you are saving the bandwidth, you are selective throughout the network. You know who has the authority to do the flood and prune, to build the multicast tree, correct? So in this way, we can save the bandwidth. We will not unnecessarily flood the multicast traffic throughout the network. So it's a bandwidth savior methodology. It's efficient, but again, there is use case that at what time we should use the dense mode, what time we should use the sparse mode. So here you can see that the key point is that when we are going to use the dense mode, so suppose in a network, if we have the large number of multicast hosts, so in that case, actually it's very easy. So everyone will send the multicast feed, and then pruning will happen. It's very easy, and uh, it's like you can think if you want to compare, then you can compare that, okay, so for example, RIP versus OSPF. RIP is something, a router RIP and then network command, but OSPF define the area, limit the LSAs, do the things in efficient manner. They will do the SPF calculations and all, correct? Although in other hand, the sparse mode, again, the thing is that you are doing it efficiently, but the use case is that when you have the limited number of multicast hosts. Okay, so both have pros, both have cons, but I recommended that we should use the sparse mode, at least in the enterprise network. All right, so here you can see that in PIM dense mode, you have the multicast source. He's sending the feed to all the throughout the network, and where you don't have the host multicast receivers, so you will go and do the pruning. So here you can see that now finally we have the tree structure that is built towards the receivers. So sender and receiver, source and receivers. Okay. This is the dense mode. Easy to use, very easy to build, but it is consuming the bandwidth. Now the next we have the sparse mode. In sparse mode, suppose if we have two multicast source here who is going to send the feed, first of all they will go and select the rendezvous point. So here you can see the selection of RP will happen. Once you have the selection of RP, rendezvous point, then it's the responsibility of RP that he will send the feed to the selected interfaces where you have the multicast receiver. Obviously, this is the efficient way to build and maintain the multicast routing or multicast feed. Great. Now you can see that you have version 1 and version 2. How we can go and enable it? We can go to the interface, and then we have option either we are running PIM in the dense mode or a sparse mode or a sparse dense mode. Now you have this RP option as well. So RP can be identified manually. Suppose This is your RP. You can go and run the command, manual command, and we have the auto RP in Cisco as well. So if you want to do it manually, the command is ippim RP address 192.168.1.1. Again, if you have the multicast source, so these are the feeds. We can go and create the ACL, and with the RP address, we can go and map this ACL entry. Correct. So this thing we have seen earlier as well in the previous section. When we have created the ACL just to limit the number of multicast source, and then if you want, you can map with the RP as well. Okay. Next, the verification and troubleshooting commands. So we can go and check show IP IGMP groups, show IP IGMP neighbors, show IP PIM, who is the RP. Then we have debug command, debug IP IGMP, debug IP PIM. Okay, so let's do one thing. Let's stop here, and in next section we'll continue from here, and then I'll show you this CLA command in the GNS lab as well. Let's continue. So we have some commands to do the verification and debug as well. Once we build the multicast tree, then we can go and check show IP mroute. We have already discussed about source comma group entry, and if you have the rendezvous point, you'll find the star comma G entry as well. We have the upstream and the downstream interfaces. Suppose if you go and run show IP mroute in dense mode, you will see the output like this. So here you can see that you have the source, and then you have the multicast group address, the uptime, then incoming interface, the outgoing interface, who is your RPF reverse path forwarding neighbor, and here you can see the interfaces. Okay, so there is flag as well. Suppose if flag is not mentioned, this is gens mode, and if you go and check the flag, so let me show you that. Show IPM route, and here you can see the flag is showing SC, that is for sparse mode. Okay, and you can see a star comma G entry for the rendezvous point. So if you are running the multicast in the sparse mode, then you will see output like this. Okay, so there are some notes as well. You can go and check the upstream and then downstream interfaces. Uh, so notice that SG pairing is labeled as a star comma G entry in the sparse mode. We can have multiple source share with the same multicast tree. The rendezvous point is 10.1.1.10. The flag is SC, that means route is running in a sparse mode. Then you can go and check who is the outgoing interface, who is the incoming interface. So it's just like the dense mode. The incoming interfaces indicates the upstream, means where is your multicast source, and the outgoing interface showing is the downstream, that where is your receivers. All right, so let me quickly log into the lab, the same lab we have, and I'll run through few of the important commands just for just to know that the commands are supported and what type of commands we can run in the P mode. Let me go and start this lab. Again, I'll go to R2. We have done some of testing. I'll go to R3, and inside R3, so first of all, we should go and enable IP multicast routing. See, that's the first command. Then I can go to the interface, and we can go and run IP PIM, and here you can see that the mode. So we have dense mode, we have a sparse mode, sparse dense mode. Here you can see sparse dense mode, sparse mode, dense mode. So let me go and use this dense mode. Once we go and run the dense mode, then here you can see that DR has been changed, who is the neighbor. So I can go and check show IP PIM neighbors and show IP. Actually, this command is quite useful. Show IP PIM neighbor. It will show you whoever is your neighbor, and even we can go and check the interfaces as well. Okay, so now you can see the DR and DR priority. Now next, what we can do, that suppose if you want to go and check the RP, so we can go and assign that uh, RP address rendezvous point. So I can go to IP PIM and the RP address. What is that address? Say 192.168.1.1. We can give the ACL as well. I'll show you the ACL formation in this command. So for example, ACL 10 and then permit 226, say 11, 10, 11, 12, etc. And then I can go and assign this to IPPIM RP address 192.168.1.10 and then 10. Okay, so these are the commands that we can go and run. We can oops, we can go and check that what commands we have used related to PIM and related to RP. Okay, so we have enabled the PIM in dense mode, and then we have enabled the RP as well. If you want to check show IP M route, you can go and check like this. All right, so you can see that all the addresses that we have given, for that we have a star comma G entry, and you can see the flag as well. Now flag is telling that we are running SJC. So S stand for obviously sparse, and then we have the flag J and C. J stand for join the SPT. You have a small s as well. You have big S as well. C is connected. Okay. Uh, show IP PIM and the neighbor. Show IP PIM interfaces detail. We know that we have one interface here. So here you can see that PIM is enabled. PIM version is 2, and everything related to PIM. I can go here and make this um, as a dense mode. So IP, remember whenever we are doing say IP PIM in dense mode, okay, so at that time there is no selection of RP, but at the moment you'll go and give the RP address. So here you can see that you are seeing all this rendezvous point and all. That's the reason we are seeing this. So what I'll do here, I'll go quickly and I will remove this statement and this statement, and again I'll go to interface F0/0 IP PIM in dense mode and interface serial 0/0. Let me see that what interface we have. Interface is serial 0/1. So IP PIM in dense mode. For dense mode, nothing is required. Simply if we run that much command, that is good and enough. So I can go and check show IP M route, and since this is running in dense mode, so you will see now I should clear this clear IP M route. Wow, VRF clear IP. So you can see that VRF is there and we don't have VRF related to that. I just wanted to clear these multicast entry. Alright, so I have cleared the entries and now I can see that we have the DC, day for dense. Because we have enabled this feature on router 2 as well, and if you go and check, we are getting the um, feeds from router 2. So if I go and check if I have some configuration related to IGMP and all, so you can see that he is willing to join the IGMP group. We have some access protection as well, and those entries actually I'm getting here. Okay, but the idea of concept behind this, that we have the D comma C entry. And now if I go and assign the RP, so IP PIM RP address say 192.168.1.1, and then if you go and check mroute, so you can see the flag will change to sparse. So it is changing from dense to the sparse mode. All right, so let's stop here.